physical, well, let's see, using physics as a primitive basically in computation kind of at a lower level, I guess. But yeah, we'll have some time to talk about that. Yeah, we go ahead and invite everyone to speak. And also I'll I guess, I haven't done a space in a while. I'm trying to remember, how do I add stuff to the Jumbotron or whatever?
I think you're just gonna find the post on X, and then at the bottom with the little share button, you should be able to share it to the space. You'll be good.
Okay. Yep, let me do that then, so everyone can find the paper. Yep, share button, share to space. Okay, yep, it's easy. All right. Okay. Great. So yeah, how's everyone doing? Haven't done a space for a while. I know it's been a while. So yeah, how have you guys been? Good to see you again. Yikes, Laura.
Yeah. Can't complain too much. Had a job for a little bit. Don't have a job anymore. Frickin' thinking about. I've been chatting with Base 10 about some of their model optimization stuff, so we might have something going on there. But other than that, just like running around doing shit like I usually do, I guess. So same old.
With who? Who do you say you're chatting with?
Base 10. It's like
Base 10.
Yeah, they're kind of new kids on the block. They're like I think the tagline is like the inference company. So
Cool.
they do inference. And well, actually, interestingly, with regards to inference, the reason I sort of got it stuck in my head about it was because I have a new decoder strategy that I came up with, or that some of the people at a paper club that I go to came up with, and I want to test how well it scales. So if it does scale, then it should be pretty freaking cool.
That sounds cool. Yeah. There's definitely a lot of interesting stuff. I mean, I'm not sure exactly what kind of things you're looking into, but like speculative decoding and stuff like that is definitely pretty exciting now, I would say. So
yeah, it's the it's sort of based on the paper like writing in the margins. If anybody's read that, basically you take the KV cache and you the basic principle is just reuse the KV cache. But paper's definitely worth a read if that's of interest to anybody.
I don't think I've read that. You said it's called writing in the margins, better inference pattern for long context retrieval.
Yep.
Just
yeah.
Okay, I'll have to take a look at this. Yeah, I'm like super interested in this stuff because I know like a lot of people think it's like kind of boring, like really in the weeds of just like like it's kind of like performance optimization stuff, but it ends up being like the most critical thing because like fundamentally like there's like different kinds of computations. Like some are memory bound and some are compute bound, and when somebody realizes, oh, like in the decode phase, transformers are memory bound, so we can do extra computing on the other end, and we can add in the speculative decoding. It's like those are the kind of advances that actually make a difference.
Yep.
So I think these are super exciting ideas, actually. But
yeah, especially in like the era of RL. Now that we can spend additional compute for extra performance on both ends. So now if you can make inference more efficient, then you can just tell it to think for longer. So you kind of have performance optimization basically like no matter what you're poking at, which is kind of a cool place to be, I suppose.
Yeah, exactly. And it's like somehow like the kind of the tools of like theoretical computer science, which are all, well, not all, but a lot of it is based on like asymptotic analysis of algorithms, are not really equipped to handle, the theoretical questions now, which are like, what regime is this computation in? What is the bottleneck? Is it the time it takes to access memory? What kind of memory? Is it the L1 or L2 cache? And what kinds of changes to the algorithm do we need to make to optimize around that? And it, in general, I just think that, there's work on that, but it's kind of underdeveloped in terms of like the kinds of computer science that we most practically useful in terms of these questions. But yeah.
Yeah, hard agree, basically.
Yeah. Sorry. Yeah, go ahead, Jack. How's it going, Jack?
Yeah, so for I think for Alex, whoever said is unemployed, the folks at Magic Dev are hiring, and they claimed last year they have an architecture, a model, something that can go up to 100 million tokens in context size, and now they're hiring. So they got some funding, but they haven't released anything. So for what's worth, if anybody's looking for a job, they
I
may.
might call them,
Yes.
but it's funny. I haven't interviewed very many places. I have actually interviewed at Magic. It was one of the
Oh,
few
there you
places.
go.
Yeah, it was ages ago, but I had basically they were like, we're trying to make AGI, and I was like, I want to make AGI free for everybody and have as much of it as you want. And the way I probably am going to do that is Web3 related. And they were like, nope, that's not us. So that's how it goes.
Wait, what's the company called again?
Magic.
Magic.dev,
Mhm.
I think, or
Magic.
Magic Dev.
Okay, and they're hiring, and do you happen to know like what kind of roles they're hiring for?
I got I think multiple research and regular software engineering and some combination of both to do stuff. But it's a bit weird because they came with some outlandish architectures that is gonna do a lot of great stuff, and they haven't really. This was last year, like a year ago, and since then they haven't released anything. So I know what's going
Well,
on
they
with
did the
that
same
big gap.
thing with their last product. Before their main thing that they did was basically Devon, but then Cognition beat them to the punch and they didn't bother releasing it. So.
No. I think it's a different company. I think no. It's a different Magic. I think it's
Oh,
a different
really?
Magic. Yeah, it's Magic.dev. They released an architecture, so they got funding. They let me see. There is a guy in Austria. That's one of they had
Sorry,
some
breaking up. I think I can hear you now. Yeah, go ahead.
really long blog. Yeah. So it's Magic.dev, and they have a blog post there.
Yeah, wait a
100
minute. I just looked at their website and it said they raised 515 million. This is a pretty big.
I know.
The reason
Yeah, but it's very weird because
reason I know about them is because they had a data bounty for a while. They were if you could bring them data they didn't already have, then they'd give you like $100 a gigabyte or something. That was originally what caught my eye on it, and that at that time is when they were trying to do and I guess they technically still are, just like their thing. Software engineering was kind of their thing that they want to automate. Presumably that's because it's the like AI 2027 tier. Like as soon as you can automate software engineering, you can just put that on machine learning, and then you kind of get your FOOM and go off. So.
Okay. Because now I'm kind of curious, right? Because they raised $500 million, and all right, so they started. I'm not sure when they started. Their Twitter account started in 2022. And let's see. So on the landing page, it says Magic is building frontier code models to automate software engineering and research. Okay, makes sense. We believe the most promising path to safe AGI is to automate AI research and code generation to improve models and solve alignment more reliably than humans can alone. Okay, that's kind of interesting. All right. So the goal was, I guess.
So if you go to their blog, if you go to their blog, they have like a 100 million context window or something. It's like a pseudo-technical blog where they just skim through their some fancy hashing they do for tokenization, and that gives some boost. But it's really weird so far. They haven't released anything.
Remember, actually, yeah, I remember reading about it's HashHop. Yeah. This actually came out a while back. I think.
Yeah, exactly.
GitHub HashHop. It is interesting, in that the way that they do it is, rather than pure tokenization, they like hash all the incoming data, and then at like some point during the tokenization process, and what they train it on is the ability to complete those hashes.
Wait, what? No way. Are you serious? They're training on completing hashes?
Yep.
Wait, is that
wild?
possible?
It is. Let's see. These subtle flaws weaken current long context evals, blah, 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 blah. To eliminate these implicit and explicit semantic hints, we've designed HashHop. Hashes are random and thus incompressible, requiring the model to be able to store and retrieve from the maximum possible information content for a given context size at all times. Concretely, we prompt a model trained on hashes with hash pairs, and then we ask it to complete the value of a randomly selected hash pair.
Okay, I'm trying to. So, are they trying to learn to like? Well, they're not like trying to learn to like create hash collisions or something, right? They're just like trading on hashes in order to force it to be able to solve like this needle in a haystack problem somehow.
I think that that's kind of
Uh,
the
I,
principle. Yeah.
Okay, I see.
from my understanding, whatever I'm seeing there is that hash is more. So how you tokenize, if you do it right, you get an extra boost in accuracy. But this is just my skim read.
Let's see. Okay, yeah, I see this now. So it says we asked the model to complete a chain of hashes. As recently imposed hash one, hash two. Huh. Well, they link a paper called Ruler. What's real context size? Needle and haystack test. Let's see.
Oh, is it? Maybe the model's a LTM2 mini. Let's see if that's somewhere. Well, supposedly there's a model, but the question is where did they release it? Or let's see, blog. No, I don't want a blog. I want like a Hugging Face.
No, so the last that post was last year, so they have nothing since last year, except that ginormous funding, which is raises some. Maybe they actually scaled it up and saw some scaling didn't work or something, or the performance didn't.
Speaking of alternative architectures, do any of you have any insight into Liquid AI?
Nothing unique other than just like I have heard of it, but.
Okay, because they released like some open source models, but they were just like convolution plus attention models. And I thought the entire gist was like doing more like Hodgkin-Huxley, like neuron inspired computing, but I don't know. That's very weird what they released and what their stated sort of main technology is.
On the brain, if you're interested, there is a guy, Artem something with K, who posts a lot of very cool halfway biological, halfway computational. It's very intro level, but it's very interesting stuff to read.
I think I've seen him. He has really nice animations.
Yeah, exactly. On YouTube, yeah. Artem something with K.
Yeah, I bumped Kisanov or something, but it's spelled all over the place. Yeah, I bumped into him when I was looking up Obsidian stuff because he has a couple of really good Obsidian videos about that. Is like, oh, here's how you would structure your vaults if you were structuring it similar to a brain and blah 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 thing.
Interesting. Okay, I'm still trying to understand this thing about the hashes, but well,
it's really weird. It's very weird.
Super weird. Like, it doesn't make sense to me, but maybe I just need to read about it more. But all right, anyway, I guess we should probably start talking about physics or something because I guess I did computing with physics. So yeah, the paper is linked up there in the Jumbotron. So this is about this is our paper called "Solving the Compute Crisis with Physics-Based ASICs." So we tried to make it a little bit dramatic and calling it the compute crisis, which I Googled that term, and that's not like a well-known term. I think we made up two terms for this paper. We invented both the physics-based ASICs and the compute crisis. But what this compute crisis is supposed to be is just that kind of after in the post like Moore's law and post Dennard scaling, we're no longer in the world where we predictably get both more compute and better energy efficiency every year, right? Because with Dennard scaling, as you make your transistors smaller, you not only get more transistors on a chip, but each one consumes less power, right? So you now have more compute for the same amount of power, and we're not in that regime anymore. And so now when we have more transistors, we're always going to have more power consumed. And so as the models get bigger, you have more energy. And energy isn't always the bottleneck in the sense of like, my power bill costs too much, but it is often a bottleneck in design in like there's too much heat and I can't get it off the chip, right? So it really does become an issue in kind of multiple ways. So that's one issue is just the the insane kind of energy costs where, people are buying power plants just to turn them into data centers. But then the other side of it is the hardware cost of like how much, is it going to cost to buy all the GPUs or whatever you need, in order to train the latest frontier models. And so because we're in this situation where we don't expect that like every year we're going to just get reliably better and better efficiency, people are taking different approaches to getting better performance, and people are taking pretty creative approaches and like coming up with totally new like computing paradigms and computer architectures with novel kinds of devices like memristors or Ising machines or thermodynamic computing. And so this paper was kind of our attempt to like provide some unifying vision to that, and because I think that the one thing that a lot of these different computing paradigms have in common is that they're trying to kind of take operations that are computationally useful and map them onto like physical processes that actually happen on a chip, instead of just saying, well, everything is going to be computed in binary at the end of the day, so I just need to be able to do my Boolean logic gates. Instead, we're going to see if we can do kind of a larger, more useful chunk of the computation with some physical process that happens. So that's kind of the background for the paper in a nutshell. But yeah, I just wanted to give kind of the basic explanation, and I was wondering, anyone happen to take a look at it or look at the abstract or anything?
Where's my fricking tab? Oh my god.
Yeah, I read most of it, I think. So.
Cool. Yeah, do you have any thoughts or questions on the paper?
Yeah, I guess I was sort of interested in maybe a slightly different question from like how do physics ASICs differentiate themselves from like regular CPU GPUs, in the sense of like what are sort of the minimum functionalities I guess a physics system or a dynamical system ought to have in order to do quote unquote useful computation.
Right.
So like it probably needs to be able to read in an input, write out an output. But beyond that, like I'm just sort of I'm struggling sort of to articulate like what are the basic fundamental functionalities that the physics ASICs ought to have.
Right.
I hope that makes sense.
Yeah, no, that's a great question. I mean, so I guess the short answer is there's no one answer. There's no one, I would say, at least not one that we've come up with in like what is like the API for a physics-based ASIC, or like there's no one like there's not going to be one instruction set for all physics-based ASICs, because the point is that kind of in different physics-based compute paradigms, there are different kinds of operations that are easy to do. But that's not a very satisfying, answer, because, we want at least something concrete. So I think the best I can do is I can talk about specific examples of like physics-based ASICs and like what are the natural primitives in those specific examples. So one good example is DRAM-based architectures, right? So, DRAM, dynamic random access memory, is not supposed to be, was not invented to be used for just distribution, right? But it turns out that you actually can use DRAM computing, because the way it's supposed to work is you activate one row at a time, one row of memory, and then you can read or write from the row that's active. You're not supposed to ever have multiple rows active at the same time. But it turns out that by kind of violating the timing constraints that are laid out in the spec for DRAM, you can actually get multiple rows to activate at the same time. And what happens when you do that is that every cell of memory is basically a capacitor that's gated by a transistor, right? And that capacitor is charged up to VDD to store 1, or down to 0 to store a 0. And when you activate multiple rows at the same time, charge gets shared between capacitors. And there's more kind of details of like what happens after that. And there's the sense amplifier kind of kicks in and drives the voltage up or down. But ultimately, you by physically sharing charge between a number of rows in DRAM, you can do what's called a majority gate, where you have, let's say I have 10 bits, they're just a sequence of 10 ones or zeros, and then I figure out, are most of them zeros or are most of them ones? Well, I guess in the case of 10, it could be half and half, so let's use an odd number. Let's say I have 11 bits, and the majority gates tells me are there more zeros or more ones, and if there are more zeros, it outputs a 0, and if there are more ones, it outputs a 1. And that's something that you can do in a DRAM chip using this physical charge sharing process. So by activating multiple rows at the same time, and then activating the sense amplifier, the output you'll get is the result of that majority of 11 or however many rows you activated. So that's one example of like a primitive operation that I would consider like physics-based computing, basically. Yeah, did that help kind of answer? I don't know.
I guess what I was getting at was more like regardless of the underlying sort of physical primitive, or like what ought a physical system be able to do in order for it to be useful in computing? Should you be able to put in an input and get an output and read an output out? Should it be able to, I don't know, maybe very abstractly, should it be near criticality? I guess my question was functionally wise, what do you expect the system to be able to do, as opposed to what are the mechanisms by which it does it? Does that make sense?
Yeah. Okay. So the question you asked was, what should a physics-based ASIC be able to do in order for it to be useful? Should you be able to to write or read information, put in inputs and get out outputs? And what kinds of operations should it be able to do, regardless of how it accomplishes those, right? So first, I would say that, of course, you need to be able to get inputs in and outputs out of any kind of, integrated circuit, or it's not useful, right? But putting the inputs in and the outputs out is not actually, that's not the place that there will be a lot of innovation with physics-based ASICs. That would, for the most part, be done in the same way that it is in a completely digital ASIC. In some cases, it might be different, but in many cases, it will be done similarly. Where the reading and the I/O operations aren't necessarily going to be very fundamentally different. But in terms of the data processing, right? So after you put in your input and before you get out your output, the data gets processed somehow. And that's where we want to, use physical processes to perform computations, right? So in the example I was giving a minute ago, the operation that was being done was this Boolean majority gate. And the reason that it's useful, and I described, what that operation does, it takes in a number of inputs and it outputs a number of bits and it outputs the majority bit. The reason that's useful is that if you have access to large fan-in majority gates as opposed to just or and in NOT gates, you're in kind of the TC threshold circuit complexity instead of alternating circuits. So there's some theory of why this operation allows you to have shallower Boolean circuits, but I guess the point being that we can think about these things separately, as you kind of were saying, of how we do the operation physically versus what the operation is, and by natively supporting certain operations like those majority gates, we do expect to be able to do certain computations faster, I guess. But there's no there's no one set of operations that we would expect all physics-based ASICs to be able to do, because they are, after all, application specific, right? So it depends on what application the chip is intended for. What operations it needs to do depends on what applications it's kind of tailored for, if that makes sense.
Yeah. Okay. Good. Thank you.
Cool. Okay. Yeah. Good questions. So let's see. Did anyone else have any questions or thoughts about the paper to start with?
And you might have actually covered this in your immediately previous question, but the thing that I recall from my last read of normal computing papers in general is what you're trying to do is do this physics based kind of thermo computing stuff. the way that we did an experiment with that was with like a series of springs, essentially. So I'm curious in this iteration what the underlying physical stuff in this case is, or if you guys were just doing like theory in this and haven't actually like built any hardware yet.
Right. Yeah. Another good question. So I would say that, right. So as you were saying, like what we started off with was, more or less a system of springs. I mean, it was really, I guess, like a like kind of a circuit that like a coupled a set of coupled RLC circuits, but they're physically analogous to masses on springs. But it was like a completely analog architecture. In our more recent work, we've kind of realized that like you don't have to have a totally analog architecture to take advantage of like thermodynamic computing concepts, mainly being that if you have a computation that's tolerant to some noise, like running a diffusion model, for example, then you don't need to have your hardware can have errors at some rate, that's not very close to zero. You can have like maybe errors a few percent of the time, and still get the right answer. And so that's, I guess, kind of one of the fundamental ideas about at least thermodynamic computing, is taking advantage of the fact that like if the problem is error tolerant, then we can make the hardware have some amount of errors, and we can save energy if we're not correcting errors all the time, basically. But how that relates to this work on physics-based ASICs is that we were looking around and we're seeing that actually a lot of other people are proposing architectures that aren't exactly the same as what we're working on, but are using similar principles in that they're trying to map a computation onto some physical process. So like similarly to in our earliest papers, we were saying, well, you can take this differential equation, this stochastic differential equation, and map it onto the dynamics of some circuit. And that's basically just saying like the laws of physics for this device are equivalent to the math of this problem we're trying to solve. And that's like the overarching concept of physics-based ASICs in general, is saying like the physics of this device is equivalent to some problem or some part of a problem, I guess. And so I guess the point of this paper, it kind of came out of a workshop we did where a number of other researchers in the field were there, and it wasn't so much that just to summarize our work, but kind of to unify our work with a bunch of other people doing other kind of things, I guess, if that makes sense.
Sorry, I missed the last like two sentences that I think were critical. So did you do did you guys actually put together an ASIC for this one?
Right, sorry. Oh yeah, that was a question. Yeah, no. So we have we've taped out a chip. The chip we're going to have the chip in. We're gonna have it in our pretty soon. But it's been taped out basically. So yeah, that's where we are now. It's our first chip, and we're kind of getting ready to start our architecture planning for the next one. But yeah,
that's
but that's kind of separate. But yeah, we haven't really talked about that in the paper, as it's kind of a separate thing. But that's our kind of internal status, I guess. But yeah.
A really cool old ASICs, physics-based ASICs. There was like some Soviet engineer back in the days before computers were that much powerful, where they did integral computation with some water tubes. So they did like fluid dynamics to solve some hard integrals for a different place, and it worked for I think 5 or so years. And that was an interesting one.
Right. No. So this is a great comment. I'm really glad you mentioned that, actually, because that is not a physics-based ASIC, actually. Now it is physics-based computing, but the reason it's a very interesting idea, actually, and I really love those kinds of ideas and papers like that propose things like that. So I think it's a very cool thing. But what we were trying to focus on here are technologies that have kind of two things. That one, they're mapping the computation onto physics, right? But number two is that they're actually very scalable in silicon. right? So not water computers, not computing with soap bubbles, but it's actually a technology that, you know, people have thought about how you can scale it up to the size of large models in silicon. Not to, you know, disparage that paper. I think that those kind of things are very cool. But yeah, we were trying to focus on these like very scalable physics-based technologies, I guess, if that makes sense.
Yeah, and more a very general question, like unrelated of this specific word. I was wondering, is there a some sort of an architecture except quantum computing? And of course, quantum computing is like a theoretical term, depends on the implementation. A reversible computing type without quantum machinery involved. Are there such architecture or ideas?
Yeah, so there's definitely work on like reversible computing that is not quantum. Now, the question of like whether it's like truly reversible, you know, if it's not quantum, well, you know, there might be some people who would say, well, it's not really reversible unless it's actually quantum or something. But as far as like the term reversible computing goes, there's people definitely think of it as it's perfectly valid to talk about classical reversible computing, and I think that at least the version of that I've heard the most about is something called adiabatic computing, which the term adiabatic is kind of confusing because it kind of means like it ends up meaning the opposite of what it means in one context and another. So I wouldn't worry too much about like what the term adiabatic means there. But if you look up adiabatic circuit, that's the Wikipedia page for it. But it basically has to do with like not turning on transistors when there's a voltage from the drain to the source and stuff like that, because that like leads to more dissipation. Or for example, things like instead of abruptly changing the gate voltage from 0 to to 1, you change it gradually, and things like that you're able to basically reduce dissipation. But I would also say that from as far as I know from people I've talked to who work in reversible computing, they're not trying to like actually reach the zero dissipation limit, but just like reduce dissipation to far below what it would be otherwise. So it's kind of more like, you know, almost like quasi-reversible computing or low dissipation computing, I would say. Yeah.
Mm-hmm. Very, very interesting. Okay.
Yeah, I would check out this, like adiabatic circuits, that kind of stuff, because I think that is very interesting field and yeah, pretty promising. Also, kind of related, adjacent to like the thermodynamic computing, because it also uses some concepts from thermo. But yeah.
Mm-hmm. And are there any chips already kind of on the market? I mean, I know it's I mean, basically, is probably, as you said, quasi-reversible. It's like how much waste energy you can reuse, or how little can you go without while still performing something more useful in computation.
Right. Yeah. So, like, as for whether there's chips on the market, that I don't know. The only company I know of that's really working seriously on reversible computing is Vaire, VAIRE. And I don't know if they have like a chip yet or anything like that. But I do know that, you know, that's what their kind of central focus is reversible computing. And also, yeah, as far as like how reversible they are, yeah, I don't really know that either. But the guy who works there is a guy, Jim Crutchfield. He also used to work in the field that I was in grad school, kind of quantum thermodynamics, and he has some papers on what's called momentum computing. And I think that's I don't really know all the details of what they're doing at Vaire, but my guess is they're probably using something similar to momentum computing. So I would look that up as kind of a pointer into the literature on that, I would say. Yeah.
Mm-hmm. Thank you.
Cool. But yeah, and I think that's a great thing to bring up, because that's another example of like, I would say that like physics-based ASICs are, you know, if they do get these reversible computing ASICs or adiabatic circuit ASICs working, that'll be another good example of this field. Yeah.
Could you I know nothing about normal compute. Could you just talk a bit maybe about what your chip does, or what the idea is?
Sure, yeah. So the top level goal at this point is to accelerate solving stochastic differential equations, which are just differential equations where you add noise to the derivative, or to the gradient field, and as like the main or one big application being running diffusion models faster, right? Faster and with less energy. And another big goal of like simulating physical systems. So, for example, molecular dynamic simulations, which are used in like designing drugs and stuff like that, also are like fundamentally about running like simulating stochastic differential equations for a long period of time. And so we want to accelerate those kind of computations, which would also could be used for like Bayesian inference and stuff like that. And we started off by saying we're going to take an SDE for stochastic differential equation, and directly map it onto the dynamics of some analog circuit. That was kind of the origin of the company, was with that concept of like, we're going to design an analog circuit such that its laws of motion, if you solve Kirchhoff's laws or whatever, the laws of motion of the circuit are exactly the stochastic differential equation you want to solve. But we've been a little bit flexible with that approach, and now it's kind of more of like I would say like a stochastic digital computing scheme where we're playing to the strengths of like both digital logic and the like error tolerance of the applications. But yeah, that's what I would say as a summary, I guess. Yeah, did that answer the question?
And in terms of sort of technical implementation, like what's the like? Do you like randomly sample from sort of Boltzmann distributions and somehow compose them, or what's the idea?
So the Boltzmann distribution is when if you have a stochastic differential equation where of the form dx dt equals the gradient minus gradient of energy plus noise, then if you run that for long enough time and then you measure x, then you get a sample from a Boltzmann distribution, right? Now that's for if the energy is not changing as a function of time, right? But actually it turns out that in most modern sampling algorithms, like diffusion models or even algorithms that are used for Bayesian inference or flow matching, the velocity field, or you could think of it as the energy function, is changing as a function of time. So what you're sampling from is not so much a Boltzmann distribution as an out of equilibrium distribution, right? Because the Boltzmann distribution is what you get at equilibrium, and many of these algorithms are using like kind of out of equilibrium sampling, especially in like diffusion models and stuff like that. But you can't just think of it as we're going to solve a differential equation, a stochastic differential equation from time 0 to time t, and then extract that sample x at time t, basically, if that answered the question.
Oh, so you're basically trying to map the probability distribution corresponding to the solution to your SDE to the physical hardware and then sample it? Or
Yeah. So right. Okay. So the relationship between the SDE and the probability distribution is that if I initialize my state, I have a state vector x in some like n-dimensional space, and let's say I initialize the state at the 0 vector, and then I run the SDE for 10 seconds, I guess. Let's say, and then at time t equals 10. X is now a random variable because I'm not just running a deterministic differential equation, but there's noise. Now X is a random variable, and the probability of that the probability distribution of that random variable might be, for example, the distribution of all images in some data set or something. So that's how we sample an image from, if you run like stable diffusion or whatever, that's how the image is sampled, by running that SDE from time 0 to time 10 or time 1 or whatever. Yeah.
And could you talk a bit about how that's actually like on a hardware level implemented?
Sure. Yeah. So one way of trying to do it, which was kind of more what we were originally trying to do, is say like, let's say as a simple example, your SDE was dx dt equals minus a times x for some, like a is some constant, and then plus noise, right? dx dt equals minus a times x plus noise. And then what we would do is we would take that SDE and we would look for a circuit such that the differential equation for the voltage is the same. In other words, you would have a circuit where there's some set of voltages where dV dt equals minus a times v plus noise with that same constant a. And it's generally, it's possible to do that, especially because that's a very simple example of like a linear SDE where we're just taking where the velocity field is just proportional to the state. Now, in general, you're going to do things like diffusion models or whatever, you're going to have like very nonlinear SDEs. And so in order to create a circuit with those equations of motion, you would need to have a pretty complicated circuit with a lot of transistors in it, basically. And so what we've kind of, I guess, pursued more recently is instead of a like totally analog design, doing a stochastic digital design where you still, data is still represented in binary format, but the bits are treated as like random variables instead of like being variables that deterministically kind of, yeah.
And are those circuits programmable, or do you hard code them into the silicon? Like in the sense of like, can you represent different SDEs on the same hardware?
Yeah, so I would say that they're definitely programmable in like a few different ways, I guess. So one way that they're programmable is that there are weights or parameters that you can program in. Every time you run the hardware, you could program in a different set of weights, right? But you can also change the data flow to some extent. So you can not only like, one possible chip would be a chip where you can only run a given neural network architecture, but you can reprogram the weights. But what our chip will be able to do is we'll be able to run multiple different neural network architectures and also reprogram the weights. But it's not going to be like limitless flexibility. It's not going to be as flexible as like a general purpose GPU where you could run, any architecture that anyone's ever come up with. But we'll still be able to run a number of different architectures and with different weights, I guess.
Hi, Max. Can you expand a little bit on how a human would program like bidirectional continuous computation? That it seems very alien. So I'm just curious if you can share on that.
Right. Yeah, that's a great question. Yeah, because that's one of the properties we focused on in this paper was that in generally in digital logic, you use gates like an OR gate or a NOT gate, and with the NOT gate, if I change the input, the output changes. But if I, there's not really a concept of like changing the output, the input changes in response to that. And if that did happen, it would kind of break a lot of digital logic because you're not supposed to have information flowing backward through the circuit. And what the point, we were making in this paper is that in real physical systems, take as the example Newton's second law. For every action, there's an equal and opposite reaction. Every time that information flows, that A influences B, B also influences A, right? So how do you, and your question is like, how do you actually think about that in terms of developing algorithms or programming something? So I think as a good example would be our paper, like thermodynamic linear algebra. And that was a paper based on like stochastic analog computing, where we had a network of coupled RLC oscillators that you could think of as like a network of harmonic oscillators or like a network of masses on springs, a bunch of masses all connected to each other via springs. And so that's kind of clearly bidirectional in some sense, in that if I have two masses connected to each other by a spring, mass A and mass B, if I move mass A, that exerts a force on mass B, and if I move mass B, that exerts a force on mass A, right? So it's different than what's going on with the NOT gate, where you have one that's an input and the other that's an output, and information only goes one way. And so then how do we actually program this mass spring network? Well, it turns out that there's a differential equation that's satisfied by the positions of all of the masses, because you can take the positions of all the masses and write them as just one big vector, and then that what happens with that vector is that as it evolves, the way it evolves in time is that its time derivative is equal to a matrix times that vector, and that matrix is encoded in all of the like spring constants of the springs that are coupling the masses together, basically. And so what that's useful for is if you want to like solve a linear system of equations, then you can run that differential equation for some length of time. You can set up a differential equation where like dx dt equals minus ax plus b, and run that for some length of time. And then if you measure x, after enough time, you'll get the solution to a linear system. And so the way that you program this physical system with bidirectional couplings is by taking your matrix and writing it into the spring constants and also the biases and using those as like bias forces, basically.
Okay, and you give the programmers the access to those, manipulating those derivatives then?
So I guess that in that case, like probably the interface the programmer would see is they would just say, I want to solve a linear system of equations. And they would say, here's my matrix and here's my vector, right? They would say, here's the matrix A and here's the vector B, and I want to find X such that AX equals B. Just like when you use NumPy, whatever to solve a linear system. But then we would have like kind of a compilation layer that would take their matrix and vector and write it to like hardware parameters, basically.
I see. Okay. So so basically the computation time depends on the physical settling time.
Yeah, exactly. So it's kind of for these like linear dynamical systems, they always kind of converge exponentially to the equilibrium state, and so you can kind of just figure out what time constant for that exponential. Yeah.
Right. So so that just leads to my final question then. So how do you control for computational complexity if the spring stiffness in your spring model would affect the accuracy and convergence speed? Thanks.
Yeah, that's another good question, right? Because what you can kind of play games where you can say, well, what if I just take all of the springs and I multiply all of the spring constants, right? I just make all of the springs twice as stiff, right? And now apparently I get my solution in half the time, right? And so why can't I just do that like infinitely and get it in like an infinitely small amount of time, right? And so this is kind of a problem that doesn't really come up in classical computational complexity theory, where everything is very well defined in terms of the number of steps that a Turing machine would need to take, because in complexity, normally in complexity theory, it's not like a physical amount of time they're after; it's the number of steps a Turing machine takes, and there's nothing, there's no like kind of tricky rescaling you can do to make a step less than a step. So what you need to do, it turns out, to define these things in a way that makes sense at all, is that you need to look at both the time and the energy in order to define like a reasonable complexity class for a computing system like this. Because if you just look at the time, the time can always be made arbitrarily small by just changing physical constants. But if you do that, that will come at a cost of more energy, basically. And so you have to kind of say, well, I can show that I can show I can solve this problem with both time scaling as like dimension squared and energy scaling as dimension squared. And if I want to do it faster, I could do it in linear time, but then the energy would become cubic or something along those lines, right? But I can never make kind of an unconditional statement that like time is linear or something. Did that make sense?
Yeah, I track that. I appreciate the feedback too. That's awesome. So like killer application would be physical neural networks, right? Where you'd have like spring stiffness, that's your weight, your synaptic weights, right? And you would have mass positions as neuron activations, and physical relaxation would be your forward pass, and then adjusting the springs would be learning or something like that, right?
Right. Yeah, absolutely. And that would be like, another great example of like physics-based ASICs. And that's another thing. We didn't get into it as much in this paper, but it's definitely a super important thing, is that like these same concepts of like how do we define complexity for physical computations, and how is that different from classical like computational complexity theory, is going to be super important, right? Because when people say, oh, I've created a new I've created some new kind of circuit that uses physics to do a forward pass of this neural network, and people are wondering like what's the computational complexity of that, we need to make sure that that's defined in a consistent way. So yeah, I think that's super important and something we're probably going to focus on in like future papers, basically.
Nice. Thank you.
Yeah, cool. Yeah, I've gotten some really good questions here so far, actually. So yeah, and I can tell people have been taking a look at the paper and stuff. So yeah, I'm really happy with that. By the way, I'll go and invite other people to speak in case anyone wants to pop up. But yeah, did anyone else have any other questions or like thoughts about the paper?
Unrelated question to the paper. I should have asked before I started, but do y'all mind if I record this for posterity and other, I don't know, for later viewing?
Oh yeah, go ahead.
Cool.
No problem with me. Yeah.
Sweet. Yeah, if anybody else like has an issue or whatever and doesn't feel comfortable like bringing it up in public, just DM me. It's all good.
Yeah. Cool.
I did think of one thing else. So what? How do you debug then? If wouldn't you have two chips give you different results? Like being able to reproduce.
Let's see. So I could think of a number of different reasons that two chips could give different results. I mean, you could even have one chip that could give different results.
Well, sure, exactly, yes.
Right. So you can have like non-deterministic behavior, and actually in the chip we're building at Normal, it's designed to behave non-deterministically, in that you give it the same input multiple times and you'll get multiple outputs different times. You get a different output each time, and that's actually what you want. Because if you're, let's say that the task is sampling images from some distribution, I don't want to, if I'm asking for an image of a cat, I don't necessarily want to get the same image every time. I might want to get,
you want 1,000 cats. Yep.
Correct. Now, and then, but more to your point of like, how do I even test this thing? How do I know that it's working? Right. So you can look at statistics.
Sorry. I was more of like, why should I trust it? It was more of a trust issue than the functional part.
I see. Okay. I see. Well, I think that's more or less the same question of like, the reason we trust a chip is because we're able to test it, and we're able to verify that it passes some tests that we come up with some set of tests and it's able to pass those and we trust it. But those tests are going to be different than the tests we would run for a chip that behaves deterministically, because you can't just say, here's the input and this is the output you need to give me. Because there are multiple outputs that are acceptable, and so it's going to be a statistical test, I guess. Now, for some for the whole like kind of end-to-end task of running a diffusion model, there's no tractable statistical test we could really run besides just like looking at the images and see if they look good. But what we can do is we can say, well, running that diffusion model is basically running a bunch of separate layers one after the other. And each one of those layers is kind of sampling a random variable. And we can look at like the random variable that's sampled by one layer and see that it has the right statistics. So we can see that it has the right mean, right variance, higher moments by basically running it a bunch of times and computing those statistics and then comparing them to like the ideal statistics we expect. But it is, a different process of testing than you would use to verify a chip that behaves deterministically.
I see. So it's like kind of like what's the maximum precision that I can achieve given these noise limits, basically.
Kind of, but I wouldn't say it's necessarily even precision, because like maybe the task is to sample from a Gaussian, from a normal distribution with variance 1 or something. Right.
Got it. Yep.
Now I don't want the variance to be less than 1. That might be more, in some sense, that would be more precise, but that's not the task I'm trying to do. I'm trying to sample from a normal distribution with variance 1. And so then what I do is I run the chip a bunch of times, I collect all the samples, and then I compute the variance of them, and I see if it's close to 1, I guess. And then I guess that's kind of a different type of precision of like whether it's the right distribution or not. But the important thing is that I'm using like distributional measures of accuracy rather than like point wise kind of.
What's the energy cost to get out of metastable states versus like digital you can reset?
So let's see. Well, I would say that in the hardware we're building right now, it's not it is based on like kind of digital building blocks that behave in a stochastic way. And so there aren't like metastable states in that way. But yeah, like a fully analog system, you can definitely have like systems that are. I think that in general, like what the problem that you get usually with like kind of local minima in the energy landscape is more a time cost rather than an energy cost, and that systems like that take a long time to come to equilibrium because it takes a long time for the system to get out of the metastable state, basically. So that's always kind of a problem. And that problem is still there even if you're doing it digitally. In that, like, if let's say I'm simulating a molecule, and the molecule has physically it has a metastable state. It has a number of like kind of local minima, and I want to observe like a transition from one to the other. It can take a long time to do that, but that's a problem that you would have no matter what system, no matter what kind of computer you were using to simulate it. And so basically we just want to make it faster by some factor, although it still might take a long time, I guess.
Okay, so just in one last question, sorry, I'm starving some oxygen now, but so if a stochastic chip can solve like metastability problem, like if it can do that for free, why do we even use deterministic computing at all?
Okay, so I would not say it can solve. So first of all, like what the metastability problem is, could mean a number of different things. I think what pops into my head when I hear the term metastability problem, although it's not like a term I'm super familiar with, is that basically systems that have metastable states are slow to equilibrate. That problem is not like magically waved away by stochastic computing. What we hope to do with stochastic computing is that we hope to be able to save energy because we're taking advantage of the fact that running an SDE is an error tolerant algorithm, and so our chip can afford to make to not be perfectly deterministic, and so we can kind of cut corners in the design basically and save energy. And that's going to give us some factor of energy advantage and some factor of speed up. But if the problem takes a very long time to solve, it still might take a long time to solve, but it will be shorter by some factor, I guess. But yeah, did that answer the question?
Yeah, perfectly. Thank you very much.
Cool, great. I thought I heard someone else had something they were going to say.
Yeah. Do you ever run into analog to digital or digital to analog bottlenecks, or is that not a problem? Well, I guess you're not. You said it was all digital chip.
Right. Yeah. So we do have an all digital. Yeah. So that's not a problem. But yeah, when we were doing like more like an analog design, that definitely is an issue. And so in order for it to be worth going to analog, you have to do a lot of processing in analog before converting back to digital, right? Because those are always going to be like kind of the dominant. That's going to be often the dominant energy cost is like the AD converters. So if you can think of a way that you can convert to analog and then do a lot of computation, like some kind of reservoir computing thing, and then convert back digital, then it can work out. But that is kind of tricky to solve. But yeah.
Do you believe that reservoir computing has a commercial future? Or
I don't really want to make a strong statement just because I don't know like what the latest experimental results are on the field. And actually, one of our co-authors in the paper, Peter McMahon, he's done some cool experiments where some of those early ones where they showed you could compute something with a bucket of water or something like that. So it's at any rate, I'm happy people are working on it because I'm always interested to read, the papers on it. But yeah, I have no idea, to be honest, if it's going to be a commercial, thing. But yeah.
Okay, so I assume that in the for the foreseeable future, most ASICs, I guess most sort of stochastic computing devices will still all be like CMOS semiconductor based, and like there's not like okay.
Yep. Yeah. And I think that actually, to me, it was very kind of exciting to realize that like a lot of the things we wanted to be able to take advantage of by doing analog computing, we didn't actually need to do like analog computing in order to take advantage of them, I guess, in a sense that like all digital circuits are still analog in some sense, in that, things still change, all the voltages are still continuous and still change continuously in some length of time. And as an example, I guess I was talking about before how you can use DRAM, like multiple row activation in DRAM, to perform majority gates. The way that works is fundamentally an analog process of like coupling different capacitors together and their charges kind of averaging out, and then forcing it to either the high or low voltage, but then the inputs and the outputs are still digital, I guess. And so, yeah, I think that in general we can still use like physical computing in a digital paradigm and still take advantage of like physical processes to accomplish like digital computations, basically.
I see. Okay. So, are you guys taping out a full chip, or is it more like an FPGA that you, or is it like an actual full chip?
No, we're taping out a real chip, and it'll have its own kind of PCB, its own board that it plugs into, and we'll, for now we'll really just be running a lot of tests because our first chip is mainly going to be for the purpose of us debugging and developing algorithms, kind of. And then, the next one is when we'll start to see, some evidence of running real workloads on it, I guess. But yeah, the first one is not going to be as useful in more small scale. We are taping a real, or we actually already have, taped out a real chip. But yeah.
And so just to be sure, like you're using like very basic like transistors and capacitors, and as opposed to like something like MEMS resistors or something like more exotic, and it's all just very well understood basic little switches and electrical circuits and stuff, right?
Right. No exotic components. I would say that there are features of the architecture that are exotic in a way. So, like as an example, one thing we talked about in this paper, Physics-Based ASICs, we talked about a number of properties that are usually satisfied by conventional circuits. One of those properties is synchronization. Like normally in a chip, you have a global clock, and that clock signal goes out to everywhere on the chip, and everywhere on the chip is synchronized to the same clock, right? Now, in real physical systems, if you look at some dynamical system out in the world, that's typically not how it works, right? Like if I have a bunch of masses on springs, it's not like there's one kind of master clock that's telling them all how to oscillate. They're all locally kind of doing their own thing. And if you, in general, trying to take a physical system and make it act in a atypical way always costs some energy and extra dissipation. That's kind of a vague, I guess, a vague way of thinking about it. But that's kind of the intuition of the way I think about it. That often in circuit design, we take a physical system and we try to get it to act in a way that physical systems don't really want to behave. For example, being globally synchronized. Now, instead, if we say we're going to use what's called polysynchronous clocking, and we're just going to have a bunch of different separate clock domains, and sub-circuits will be synchronized within those separate clock domains, but not globally synchronized. We can save, we can save both time and energy that way. So that's an example of the kind of of the way that the architecture is exotic. We're not using exotic components, I would say.
Thanks. Would you recommend like a good review paper or something for sort of an introduction to the basics of, I guess, thermodynamic computing? Or
Yeah, so I would say that references I would recommend to understand kind of the latest like state of the art stuff we're working on are more references on stochastic computing, because the papers we've written on thermodynamic computing were all in the analog paradigm, and we haven't yet published any work on the stochastic digital paradigm we're working in now. Now there should be some stuff published on that we'll publish soon, but in the meantime, I would just kind of go on Google Scholar and look into stochastic computing, and you'll find a number of references on kind of similar things.
Or in the event, if we start book club back up again, you should go to those because we're going over stochastic machine learning was the last one we were doing. So.
Right, that's a good point. Yeah, I guess we haven't had the book club in a while. Yeah, that's a good idea.
Yeah, I got a couple of emails to send in that regard too. So maybe we'll get it going again here soon. It'd be cool.
Yeah, we should. Yeah, I think I will try to do I'll try to do some kind of space, once a week at least. As to whether that's book club space, I'm not sure yet, but I think that I would like to start book club again.
I think we had some really good discussions. So I would be super keen, absolutely.
Yeah, it's always been really fun. Oh yeah, by the way, you said that there's a professor that you were
there is. Yeah, well, and in fact, that I guess is a good segue to my question that I have, which is, so we have new, in theory, we have new hardware. In theory, that hardware is more efficient. And what you guys will be doing now that you have once you get the hardware printed, is experimenting with debugging algorithms. Are there any algorithms that you are interested in exploring that you think this hardware will be especially well suited for, as opposed to stuff that is not physical ASICs that had trouble with a given algorithm, or maybe like new algorithms to explore, or anything like that?
Yeah, absolutely. So I would say that one of the main reasons that our hardware can be more efficient than kind of general purpose digital chips is that it doesn't have to be deterministic. That it's allowed to it's allowed to output. Its output is allowed to have noise for a given input, and that means it's not suitable for certain tasks. Like you wouldn't want to if you were designing a computer to output to compute a prime number or something, you wouldn't want it to be off by 1 or something like that. But it is okay if you're making a device to sample from some probability distribution, like you're making a device to sample images, and if 1 pixel RGB value is off by a few, that's not really going to hurt the the value of the image too much, especially if you can show that you're still sampling from the same distribution. Now, so the broadest class of algorithms is sampling distributions, and that's a very broad class. Within that, I would say one is sampling Bayesian posterior distributions, so taking some like probabilistic model and conditioning it on data, and then sampling the posterior distribution for some parameters. And you can check out our paper, like thermodynamic Bayesian inference, for some details on that. And then another class, which is probably the more commercially relevant one, is actually running diffusion models. So we're definitely really targeting that. And then there are a few other ones, like, for example, molecular dynamic simulations is another one. But yeah, those are probably the main categories, I would say.
Yeah. I just linked a little post about it. The sort of physics thing that grabbed me most recently is sort of the concept of the indivisible unistochastic process, which is sort of like if you reframe physics under this particular set of circumstances, you can resolve a lot of these like weird things like spooky action at a distance and the collapse postulate and stuff like that. And as such, if you use that as your sort of foundational tool rather than like a measurement and collapse sort of model, at least according to the professor who wrote the papers on it, who I'm gonna try and see if I can grab him for book club one of these times, there should be further algorithmic exploration that you can do, obviously in physics, but sort of if you can structure the math you are describing physics with in a way that can also address quantum mechanics and quantum physics. So there's like not that divide anymore. Then in theory you can also start describing the latent spaces that we are operating in as AI people with different kinds of equations as well. So that's mainly where my main interest is, and why I'm kind of I don't know. I'm interested in exploring the more like stochastic stuff. So I'm quite keen to see what you guys end up doing once you get the chip printed. But yeah, I guess that's the for reference. This is the professor that I occasionally bring up.
Wait, so you said the paper was called unistochastic process. Wait, is it indivisible unistochastic processes? Is that the right thing?
That is the yes. So that is the like sort of the mathematical artifact that most of his work centers around. The paper itself is called the stochastic quantum correspondence, and then new prospects for a causally local formulation of quantum theory. And then stochastic quantum theorem. So there's a series of 3 that if one is interested in that sort of thing, it is quite interesting in that it's not necessarily a theory of everything, but it does, like, you can derive what appears to be all of classical physics and quantum physics from this sort of like reframing of things, which is essentially taking rather than taking for granted that the operations that we should use to describe these things will be will have the quality of Markovianness, in that like thing follows next thing. If you don't make that assumption and you just start looking at stochasticity, it turns out that you can land on this sort of a device called the indivisible unistochastic process. And if you sort of use that as your base layer, it turns out that you can describe a whole lot of things kind of using the same set of tools. I put a Reddit post up in the Jumbotron that has a explanation of it that I kind of like, so worth looking at that.
Oh, cool. Okay, I'll take a look at that. Yeah, that does sound cool. Okay, because it sounds like a lot of stuff that I definitely remember like reading a lot about like the properties of like Markovianity, Markovianness and stuff. And back in the day when I was working on like quantum thermo. So yeah, I'm pretty interested in this, and especially like the connections between like quantum and stochastic processes. So yeah, I'll take a look at this paper for sure.
Yeah, especially considering if normal's kind of headed in the direction of stochastic machine learning in general, and the professor he's a pure physics guy or theoretical physics guy, so he's not a machine learning guy at all. So I haven't seen anybody who is like a full on like math and machine learning person actually like even know what this is. So I'm quite interested to see who else I can get it in front of, basicled.
Interesting. Yeah, let me just take a look at the abstract real quick. So it says,
for sure.
Paper introduces several new classes of mathematical structures, close connection with physics and dynamical systems. Most general is called generalized stochastic systems, including Markov chains and random dynamical systems. Then it proves a new theorem that establishes a precise correspondence between any generalized stochastic system and a unitarily evolving quantum system. This theorem therefore leads to a new formulation of quantum theory, alongside the Hilbert space, path integral, and quasi-probability. Okay. Theorem also provides the first principles explanation for why quantum systems are based on complex numbers. Wow, okay.
Right.
So it sounds like a lot, okay. But it does sound cool though, because it's saying like you could somehow take all of like quantum physics and formulate it as like maybe in terms of like real valued stochastic processes, which does sound pretty cool.
Yeah, end of the day, it's like just kind of like a series of matrices, and like if the matrix has a particular quality, then we'll call that indivisible, and the rest of them we'll call that divisible. And then if you just use those 2 types of things, it turns out you can basically recreate all of both classical and quantum physics, at least as far as one's exploration has gone. It could be that it breaks down at some point, but like conceptually, it makes sense to me. Where it's like, oh well. if rather than trying to figure out if it's waves or particles or some other thing, the other rabbit hole I fell down most recently was Weinstein's geometric unity. So
Oh.
we could go down that one too. If you formulate that one, then you also get another device. But it turns out that if end of the day all you're really looking at is the probabilities, if you're just looking at the whole thing as like a construction of stochasticity, it actually like makes a lot of sense, which is pretty cool.
Yeah, and I found that like the way of thinking about like stochastic processes is like pretty similar to like the way of thinking about like quantum computing, in that you think of the state of the computer as the distribution instead of thinking of the state as like a number or something. Although there's definitely also some differences, but yeah, a lot of the tools from quantum computing you can kind of carry over, and you can kind of do, I think, the opposite of what he's doing in that paper, because it sounded like he's formulating quantum in terms of like he's taking classical stochastic processes and saying this is general enough to kind of include quantum to be able to describe quantum physics somehow. But you can also, of course, you can take quantum physics and you can use kind of the density matrix formulation, and you can, of course, any like classical process can still be described as a quantum process that just doesn't really have any coherences, basically. So there's also a lot of people who use that notation, basically, where they'll take like classical stochastic processes and write them as quantum ones, which can be kind of fun, I guess. But yeah, I see someone's raising their hand.
Yeah.
Nihal, go ahead.
Hi Max. I was curious about, like, in the paper you mentioned diffusion models. So do you envision sort of the physics-based ASICs to purely be like drop-in replacements for like random number generators, or is it something more sophisticated than that?
So it's not exactly that. So I would say that random number generation is, for the most part, I would say kind of a solved problem in that it can be done efficiently, and usually, the state-of-the-art pseudo-random number generators are good enough for pretty much any application we need them for. Now, if you really needed true random numbers for some reason, although I can't think of very many applications where you really do need true random numbers, then you might say I'm going to use some like physics-based ASIC to generate my true random numbers. And so that will be one application of physics-based ASICs, but that's definitely not even close to being the most important one, I would say. Now, diffusion models are a very important one, but I think of diffusion models as being very separate from the application of random number generation, because while diffusion models do sample a random variable, the important part isn't so much that it's random as like what distribution is being sampled exactly. Like, is it the distribution of all images of dogs or cats or whatever? And a PRNG is a very different thing than like a diffusion model that can sample. Can generate images of whatever you want. So yeah, I would say that different physics-based ASICs are going to have different applications because they are application-specific, circuits in the end. But one class of those will be like for, generative diffusion models. Yeah.
Mm-hmm. But where exactly do the physics-based ASICs fit in for diffusion models? I mean, you have like a large convolution or neural network or like a UNet backbone doing the learning, backpropagation, gradient descent, blah, blah, blah. That seems to be the heavy compute. And even if you're talking about the noising, denoising, I mean, I'm just trying to see which operations do you see offloading onto your digital ASICs?
Right. So in the original papers, like Yang Song, whatever, they used a UNet backbone, I think. Now, most of the state-of-the-art models now, as far as I know, are essentially all like diffusion transformers, and so not so much the UNet backbone. But I guess that's kind of separate from your question of like, where does the physics-based ASICs actually come into that? Like, why are physics-based ASICs going to help with diffusion models, and how exactly? So the point is that what you do with your, how you run your diffusion model is first you train your score model, your denoising model, in order to take a noisy image and denoise it a little bit, and then when you've trained it, you run your inference loop, where you take a noise sample and you denoise it, and then you denoise it again, and so on. But each time you denoise it, you also add noise in general. That's how the inference loop works, that you denoise a little bit, and then you add a little bit of noise, and then you denoise again. And because you're adding noise after every evaluation of the model, that means that it's kind of a waste if your model is evaluated in a very precise way. So, for example, if I use like 64-bit floating point arithmetic to evaluate my score model, and then I add Gaussian noise at the end, there's kind of a question of like, why did I use 64-bit precision to evaluate something that I'm just going to add noise to? I didn't need that much precision, right? In taking this argument to its conclusion, you can kind of say, well, actually, I can dramatically reduce the amount of precision I need in order to evaluate this score model. And I can actually replace all of the activations throughout the model with random variables instead of them being deterministic activations. And if we make that kind of mathematical transformation, then we can say, well, because the activations in the score model are random variables, I can use a chip that behaves in a non-deterministic way, in that it sometimes makes errors. In other words, like sometimes, if I have an OR gate with, 2 ones at the input, maybe it doesn't always output a 1, but sometimes it randomly outputs a 0 or something like that. And you might ask, well, why would I want a chip that sometimes makes errors? And the reason is because if you're willing to accept that error rate, then you can make your chip much more energy efficient. So that's kind of the whole chain of reasoning, is that because in diffusion model inference we're adding noise, the score model doesn't need to be evaluated with very high precision, and because of that, we can replace the activations with random variables, and because of that, we can use a non-deterministic device to perform the inference.
Got it. So the idea is not really so much of reinventing or proposing a new algorithm, but rather kind of do the same thing, but you can use lower precision, cheaper, more energy efficient hardware, but similar algorithmic flow, if I understand correctly.
Yes, in the sense that we want to be able to take a pre-trained model architecture, like we want to be able to take Stable Diffusion 3.5 large or whatever, and run it on our hardware. We could also say we're going to train our own models for our hardware, but that's not as good as being able to say we can take all these great pre-trained models that were trained with tons of compute and run them on our hardware. So we do want to be able to do that. There is actually a pretty large amount of algorithm development that we need to be able to do, just to be able to take deterministic operations and kind of reformulate them as stochastic operations. But that's, as you said, it's not changing like the overarching like flow of the model architecture. It's more saying like we have this individual block within the model, like we have a softmax layer, for example, and the way that we're going to do that softmax is different than the way that it's done on a different, on a GPU. We're going to do the softmax in a different way, and we need a new algorithm to do that, basically. So that's kind of the extent of the algorithm development we're doing, I guess.
Got it. Because I think if you were to look at inference of diffusion model, whether it's transformer backbone, unit backbone, or anything, I guess most of the compute time, energy would all go into massive matrix vector multiplication. So you're probably thinking that even that part could be done on a physics-based ASIC, because you may not require as high of precision, like even in those cases, probably.
Yep, absolutely, yeah. So that's absolutely right, is that virtually all of the computation is going to be done in those matrix vector or matrix products. And in running one of these diffusion transformers, it's going to be matrix operations, like BLAST3 kind of operations, which are in general even more like compute intensive as opposed to like memory intensive. But I guess that's kind of besides the point. But as you were saying, like we do definitely want to do those on chip in our using stochastic computing. And it turns out that stochastic computing is very fast at doing linear operations, like doing a matrix vector product or matrix product is what stochastic computing is like most well suited for. And then doing the nonlinearities is kind of the tricky part. That's where you have to put a lot more thought into developing clever algorithms to carrying out the nonlinearity as well, because it's harder than it is in floating point arithmetic. So yeah, we definitely want to do the linear operations, on chip in this stochastic digital hardware, because that's kind of the strong suit, I would say, of that paradigm.
Got it. Thanks.
Yep. Yeah, all good questions, by the way. Yeah. Cool. Yeah, were there any other questions people had or thoughts on any of this stuff, or what we're working on at Normal or the paper or anything? Okay, cool. Well, yeah, if not, I guess maybe, let's see. Maybe I'll just find some parts of the paper that I think are interesting and say a little bit about that. So, yeah, I think this is a nice piece of motivation, actually. So yeah, one of our co-authors, this guy Logan Wright, he does some really great research. He actually came up with this kind of motivation, I guess, which if you go to the paper on page 3 in kind of the upper left, there's a thing about simulating transistors, basically. And so what it says is, let's see. For example, the physical device that performs a simple CMOS NOT gate realizes a single binary operation per clock cycle when abstracted as a binary logic gate. But if we instead model the transient dynamics of the circuit that comprises it, typical numerical methods may require millions of floating point operations. If we modeled each transistor in microscopic detail, as is often done during the design phase, we would necessarily solve 3+1 dimensional systems of partial differential equations requiring billions or even trillions of floating point operations, still just for a single clock period. Okay, so the point he's making there is that if you want to take a transistor, just one transistor, and simulate it kind of faithfully on a general purpose digital computer, like a CPU or a GPU, then you're going to need to have billions of parameters, and it's going to take a lot of time to do the simulation. And ultimately, what it amounts to is simulating one transistor with billions or trillions of transistors that you're using to simulate that one transistor. Whereas you might just ask, well, if what I cared about was just being able to predict how that transistor would behave, why don't I just use it and set it up how I want and then measure what it does, right? And so that's kind of the intuition for why we expect, I guess that's a good intuition for why we expect physics-based ASICs to be able to save a lot of time and energy, in that a lot of cases, in particular cases like that, where you're trying to simulate some physical system, actually having an analog of that physical system is a lot better than a digital simulation of a PDE or something describing that. So I think that's a nice little piece of intuition there. Of course, it leaves open the question of well, is it actually useful to be able to simulate a single transistor in all this detail? What is that computationally useful for? And it's not obvious at all that it should be useful. So that's why it's nice that it turns out there are actually a lot of applications for these physics-based architectures, like icing machines or thermodynamic computing, and it's been shown that they can solve a lot of kind of industrially relevant problems. But yeah, so I thought it was a good. I was thinking it would be nice to talk about that little analogy there.
I guess I have something. Or was there? Did you have any unexpected findings? Were there any instances where you thought it was going to work one way and it didn't? Yes, unexpected findings.
Right. Let me think about that. Yeah, I'm sure there must have been. trying to remember what were some of the most unexpected things. Let's see. There were definitely cases of things we thought were going to work and didn't. I'm trying to think if there were any cases where it went the other way, where there were things we thought didn't work and did work. There were cases like that, actually. So there was a case where we thought that it wouldn't really be possible to take a diffusion model and I guess without going into too much detail, like take a diffusion model and quantize it in a certain way where it's kind of quantized to a very low precision, actually kind of extremely low, like single bits basically, and it still runs and works. But it turned out that did work. So that was kind of a very surprising result, but it's not published yet, but probably will be soon. Now, as for the other direction of things we thought would work but didn't, I think that early on we thought that the kind of arithmetic of stochastic computing was a little bit simpler than it was. And it turns out that there are some tricks that you need to use to be able to get stochastic computing to work. And we thought that it would work without some of these tricks, and then we need to kind of learn them over time. But again, without going into too much detail, if you just go out and read papers on stochastic computing, a lot of the time it'll seem a little bit easier than it actually is. But it still does kind of work. But there are certain tricks that you need to use to get things to work, I guess. But, yeah.
Yeah, I am also curious of the things that you thought was going to work that didn't. If there are any like particularly interesting ones of those, or like the inverse of the ones you covered.
Right. So I guess a concrete example of like things that we thought would work that don't. So let's see. So one operation in stochastic computing is let's say you want to run a neural network. You need to be able to do linear operations, matrix vector products, and then you need to be able to do nonlinear operations or activation functions. So for example, one activation function is the tanh function, or tanh, some people call it. And one way of doing that in stochastic computing is using something called a stochastic finite state machine, or a stochastic FSM. How that works, it's basically that it's a system that has an input bit stream and an output bit stream, and it reads its input bit stream, and if it gets a 1, it has a counter, like a state variable that's a counter, and if it gets a 1, it increases that by 1, and if it gets a 0, it decreases that by 1. And then it has a rule for like how it produces its output from the current state. And that thing works very well, and you can use that to implement the tanh function. But then if you take multiple of them and compose them one after the other, it turns out that doesn't work very well kind of out of the box. So that was an example of something that we thought would work, but it ended up not being as easy as we thought it would be. But then there are like ways that you can get it to work, I guess. So
do you have any intuition on why that was the case for those not working? I have an initial thought, but I'm curious what the hunch is there for you guys, or if you actually found out why that was the case.
Yeah. So the reason it doesn't work is that the for this FSM thing to work, it assumes that the input bit stream is IID, in that the one bit in the bit stream is independent of the next bit in the bit stream. And so let's say that you feed in a bit stream that's IID into your FSM, and then it outputs a new bit stream, but the bit stream that it outputs is not actually IID, unfortunately. And so what you need to do, if you want to feed that into another FSM, you need to somehow like decorrelate it basically before you do that.
Interesting. Yeah, my guess for that was going to be probably a much more naive thing, but just a thought was like, okay, well, if we're working with the sort of like inherently noisy system, then presumably maybe you can get through one sort of FSM computation configuration, but if you try to like chain them, then you would could presumably run into like a compounding issue of like the noise is good enough to get through one, but it starts getting fuzzy when you start chaining it through multiple. Was just my initial intuition, but the what is it, IID? That is an interesting. I'm not familiar with that. So. You know,
Oh yeah. So IID it stands for independent and identically distributed. So in other words, you can think of your bit stream as each bit in the bit stream is a Bernoulli random variable with some probability of being 1. I'll just call it P1, and some probability of being P0. And so if I have two random bits, for them to be identical just means that they have the same P1 and they have the same P0. And for them to be independent means that if I sample one of them, that doesn't tell me about the other. So,
yeah. So like a property of Markovianness in this case, yeah. Like this is not related to that, and that does not cause that, and as such, they are going to anyone is going to be arbitrarily indistinguishable from the other. Yeah.
Right. Yeah. Actually, the FSM, you can think of the FSM itself as being a Markov process.
Right.
If the input bit stream is an IID stream, then the way that the state of the FSM updates is a Markov process. Definitely. Yeah. But then if you don't like decorrelate the output before feeding it into the next one, then it's like a non-Markovian process you would get. So yeah. So that's kind of why I guess it's important to add in those like decorrelation things.
Oh, that's super interesting. Yeah, because consider like we have classical hardware, we have quantum hardware, we have the stochastic quantum correspondence. We have we are now doing computing on a sort of a machine which operates on a non-Markovian basis, if you will, if you want to stretch it that way. I don't know. There's a lot of like a bunch of little through lines here. I probably got some more rabbit holes to fall down after this.
Right. Yeah. For sure. Yeah.
Sorry, just for the first, maybe a stupid question. Like, why can't you just have a bunch of like low precision, I guess cores, and then have sort of on the chip have then sort of some high precision, or like special sort of units which do the nonlinear stuff, like, or which do I don't know, radio or something hard coded. Yeah.
So the question was, why can't we have like some low precision and some high precision? Are you asking why don't we do that as opposed to doing stochastic computing, or are you saying like why don't we, or are you saying why don't we do that kind of in conjunction with stochastic computing?
I guess sorry. So the way I understood it is that stochastic computing, the way you guys have it right now, is very good at doing linear algebra, but it struggles with doing or at least it's a bit complex to figure out how to do the nonlinearities.
Right. Yeah.
So is it like not too naive to like sort of hard code sort of nonlinearities into the network to some way, or to have some sort of digital sort of I guess sort of interposing which can do those?
Yeah, I see what you're saying. Yep. Yes, you can definitely do that, and that's actually one of the like ways of doing it that we're considering. The thing is that in order to do that, you need to convert between like the stochastic computing representation of a number and the floating point representation. And it turns out that it's very easy to convert from floating point to stochastic, but it's kind of more expensive to convert from stochastic back to floating point. It's kind of simple to understand why. So the reason is that the way that stochastic computing works is in the simplest version of it. Let's say that I have a number that's between 0 and 1, and I'll call that number x. And if I want to represent x in stochastic computing, what I do is I sample a random bit that's equal to 1 with probability x. Okay, and then I draw many samples of bits that are all equal to 1 with probability x. And so then if I have a bunch of, let's say I have 1,000 samples, if I took all those 1,000 samples and I averaged them, I would get something that's pretty close to x. But I need a lot of samples to get an accurate estimate of x, right? Now, so it's easy to start with X and then draw a stochastic sample, but in order to go back the other direction, you need a lot of samples. So we don't want to have to do that like decoding basically. So ideally we would just be able to go to the, convert from real to stochastic and do all of our processing in the stochastic number format. But it may turn out that we have to do kind of exactly what you were suggesting, that after a linear layer, we have to convert back to stochastic or we have to convert back to real by averaging over a bunch of samples and then carrying out the, the activation functions. But yeah, it's a good question though.
Thanks. I think there was a similar company. I don't know if it was a similar company, but there was a company called Mythic, I think, at one point, which did, I think, analog matrix multiplication.
Right.
Do you have any insight into, I guess, what happened there, or how is it different from you guys? So, yeah.
That's a good question. Yeah, I'm not really up to the latest of what's going on with Mythic. But yeah, as far as I know, they are or were working on similar kind of, physics-based ASICs, I guess. But yeah, I'm not really sure where they're at right now, but yeah.
Okay. Thank you. Thanks.
Yeah. Cool. Well, I think we got through, most of what I wanted to talk about in the paper. So I'm thinking like we can just kind of turn this into a more like just chill, random discussion. But first, like, just wanted to make sure that there weren't any other like parts of the paper that people wanted to talk about, or things we didn't go over yet. So this is, I guess, yeah. If there anything anyone wanted to talk about this paper on physics-based ASICs, this would be a good time to bring it up, I guess.
Yeah, I don't feel like I have any burning questions really, or thoughts other than I really, yeah, I do. Like I said, I think I have more rabbit holes to fall down, but I'm glad you guys are kind of like getting ready to print and start actually playing with algorithms. I think that's really cool. Like, nice.
Yeah, I'm super excited too. It's a really busy time, but yeah, it feels like we have real problems to solve, and who knows whether our chip will be, whether it will change things, but it's nice to at least imagine that it will. But, yeah. By the way, hey there, Laura. Yeah, sorry I didn't get to say hi to you earlier, but great to see you again. How's it going?
It's good. I just, thanks for inviting me, but I didn't want to take up a speaker slot for the technical part because I'm not as technical as everyone else. But I guess what I did want to talk about or ask you about is, as I just skimmed your paper, but I did read your thread, and it reminds me a lot of Michael Levin and Carl Friston and the free energy principle and the idea of morphological computing, where part of like why biology is so energy optimized is because it makes use of physical systems. So it's not like brute forcing everything. Whereas like a lot of the machines that humans make are like, we're brute forcing things to an end. And I was wondering if you were inspired by any of the morphological computing stuff.
Oh, interesting. I'm not actually familiar with the term morphological computing. I've definitely heard of like neuromorphic computing, I guess, which is like kind of like, can we design computers that are where like the architecture is inspired by how neurons work in the brain and stuff like that. And I would say like we weren't so inspired directly by like those concepts from neuromorphic computing, but there is something that is like kind of similar in spirit, I think. In particular, like, if you look in the paper and go down to figure 4, I think figure 4 captures like you kind of just look at figure 4 and ignore the rest of the paper in some sense. I mean, not really, but like figure 4 captures a big point there, which is that we consider we consider two things. On the one hand, yeah, it's like what does the physical system want to do? Like what kind of operations are natural to do in this kind of physical system? And then on the other hand, what kind of operations do we want to do? What kind of operations are useful to solve the problems we care about and then we look at the intersection of those, and that's like the thing that the hardware is most suited to do, that is most useful. So it's like kind of the best possible purpose for it. And I think that is in some way, similar to neuromorphic computing in that it's a co-design approach where you're not just like optimizing the algorithms or optimizing the hardware separately, but you're optimizing them both together. And so you approach it as kind of a joint optimization problem. Whereas often people will say, the hardware is fixed, it is what it is, and I'm just going to focus on making better algorithms. Or hardware people will say, well, the algorithms are what they are, and I'm just going to try to make the hardware, faster. And so it's kind of similar in that sense, in that it's like a joint optimization approach, I would say.
That's a good explanation. The other part that kind of resonated with me was, so I guess it's page 9, optimization. So optimization also draws profound inspiration from physics, as physical systems naturally perform optimization. So so neuromorphic computing, I think it's slightly different from morphological computing in that, so like my understanding of neuromorphic computing is like you're like emulating brain structures, but morphological computing is more like the way that your circulatory system works. You're not just like brute forcing a pump. It's taking advantage of fluid dynamics that exist to save on energy. Whereas humans, when we make a pump, we're just sort of like brute forcing things, and so it takes a lot more energy. But there's and unfortunately I don't know it well enough to like say exactly how it works, but it's just like it's taking advantage of gravity and capillary action and I don't know, other stuff. And so like as your body controls itself, it's not like your brain has to figure out all the properties of each of these things. Like some of it is just like has been developed through like a I feel like all the words I want to use are like not the right ones for this, but it just like your body developed in this like low energy way that has a deep relationship with how physics works.
I see. Yeah, I think I know.
And that's how I feel about what you're saying as well.
Yeah. It really is hard to describe. I had a lot of like similar moments in trying to write this paper, to be honest. Of like, because it is. I think I know what you're saying though. In that like in the example of like the circulatory system, like let's take the concrete example of like, let's say that the circulatory system accounts for like gravity in the forces on your blood as it's flowing through your arteries or whatever. And so it doesn't have to pump as hard or something because gravity is doing some of the work, right? So, and I think that's a great example, a great analogy for, what we're trying to do with physics-based ASICs, because in general purpose digital architectures, because you need to be able to do anything, you basically do have to be able to kind of force the signals to go in any way that you want. And so you aren't really taking advantage of any physical processes that are driving the signals for you, kind of. Whereas with an application-specific circuit that's supposed to solve some particular problem in some domain and doesn't need to be able to solve like any problem ever, you can say, well, I can actually design this circuit in a smarter way to take advantage of some of the physics that's actually trying to help me. It's actually trying to drive the signals where I want them to go. And actually, I think that your analogy of like the circulatory system is very good. But I do have, I wasn't aware of this like morphological computing stuff, but I'm probably going to look it up now because it does sound kind of like there's an interesting parallel there.
Have you heard of Michael Levin?
I've heard of him because I think that I used to go to, me and Parm used to be in a lot of space together, and she was always raving about Michael Levin. But I don't know anything about his work, but yeah.
I mean, he definitely is like, I would classify him as like a logical fringe person. So, and why I say that is because like his demeanor and the way that he explains things make, at least make me give him, like I'm more inclined to believe him because of the way that he explains things. But if he had like a really kooky personality, I would probably be more likely to be more dismissive of him because he is definitely he's definitely on the edge of mainstream biology, but I think he's really interesting and he explains himself very well. And I highly recommend podcasts with him. I've listened to a few. I haven't listened to one lately, so I can't remember. Like I don't have one offhand to recommend, but yeah, I think you might find him interesting and see some parallels to kind of what you're trying to do as well.
Okay, yeah, I really should, yeah, because I've heard good things about him. So, and he's a biologist, right?
I'm not sure because like most of I think he is a biologist, but he mostly focuses on cognitive stuff, but he also talks about like general biology as well. But honestly, I don't remember what his degree is in.
Okay. But yeah, no, I'll check it out. I think I saw one, I think I did watch like one YouTube video, but I might not have seen all of it, but he was talking, and it actually was pretty good, if I remember. I think it was actually because I was on the Active Inference Institute or something on their like YouTube thing. I gave a talk on there, and so I was looking at some of their other videos, and then he was on one of them, so I was looking at that, and I think it was a pretty good talk, if I remember correctly. So yeah, I'll check him out. I think he does sound like an interesting guy for sure. Cool. But yeah, anyway, I am planning on getting back into spaces more. Yeah, I don't know. Laura, have you been doing many spaces recently?
So first of all, I've missed you. I'm so glad you're back. And in fact, I haven't done as many spaces because I feel like most of the people that do spaces, they kind of like do them for a while and then they stop doing them for like, I feel like you haven't done a space in like a year or something.
Yeah,
and but I love your spaces, and I honestly, if you just I know, like I like your talking spaces, but honestly, I'm just happy to listen to whatever it is you say. So if you just like, I know those spaces where you just read papers, people sort of complain, but I almost prefer if you just like read papers and babbled to yourself and made a space out of it than like not having a space at all. So, yeah.
Well, thanks. Yeah, I really appreciate that. Okay, well, yeah, I'll definitely make an effort to do more spaces then. Things have been busy, but yeah, I don't really have an excuse. It has been a while. So yeah. And how about you, Yikes? Have you been going to a lot of spaces and stuff recently? Is he still there? Yikes. Maybe not.
I will say, so I was in a space when you started the space, and so I haven't been in that many. Actually, so let me think. I haven't been in that many like very technical spaces lately, but the two spaces that I have been in, which were fun and I would recommend. One is for sci-fi fans. Joseph Malozzi, who's like a writer and producer of Stargate and some other sci-fi shows. He's been doing, he kind of crowdsourced the top 32 sci-fi shows and the best episode from each that people would recommend for someone who hasn't seen the show. So like the best like self-contained episode in each one. And so he's been hosting spaces like 3 days a week. He's going through all those. And then after he finishes that round, he's gonna do another crowdsource where he figures out which are the best Groundhog Day type episodes in each sci-fi series, and then do spaces on that. So anyway, those spaces have been fun. And then the one that actually left to come here is a trivia space. And so if you search for Survive This Space, It's on Friday nights, not every Friday, but a lot of Friday nights. And it's trivia, but it's like, there's like a meta game that happens. So it's like kind of about trivia, but it's kind of about sociology. And it just ends up being a fun group of people, but it's not very technical. And so if you're looking for something technical, that's like, neither one of those are the right thing, but they're fun.
Yeah, no, those do sound fun. Actually, yeah, especially the fact that, yeah, the writer of, you said he's the writer of Stargate. That does sound cool that he's doing space.
Yeah. I'll post it so you can find him.
Okay, yeah, I'll check that out. And the other one sounds cool too. You know, I used to go to trivia back in grad school. That was like the only thing that I did outside of grad school was that me and a friend of mine, Bavesh, we used to go to trivia like, you know, a couple nights a week at like a bar near us. And we would always like lose pretty badly because the bar, they like catered it to like a little bit of an older crowd. So it was always like questions about like songs or movies from like the 70s or something. But it was a good time. So I do enjoy trivia. But and it sounds interesting too that there's like you said there's like a sociological like metagame or something.
Yeah, because it's not just about what you know. You can still get voted off or be saved. So it's like a combination of trivia and like a survivor game. Because and in fact, this almost happened tonight, where there was a guy who was like runner up, and he like literally did not answer a single question correctly, but he almost won because there's a voting aspect to it, and that's what makes it kind of like interesting and unexpected.
Wait, I thought this was supposed to be like a chill space, but it sounds like a kind of a reality show. It sounds pretty intense, to be honest.
It's like it's hard to describe, and so, there is some drama, but it's also just kind of like interesting. So they're all recorded, so you can listen to them. But I'll post them so you can check it out.
Is it a big space? Like, how many people are there?
No, so they try to get, so they need 10 for the game to go, and sometimes they don't get 10. But okay. I would say in this space, there's typically maybe like 10 to 20 people. So it's not that big of a space. But it gets recorded, so it gets maybe like a couple hundred listens. So it's definitely kind of like an underground thing, I guess.
Okay. No, that's great actually, because it sounds like a lot of fun. So I was getting ready to be disappointed that like I would never actually get to like talk to these people because it sounds like a fun thing. But I like to go to space to like meet new people. So if I don't always go to ones if it's like a huge space that I would never be able to go like actually get on speak. But yeah, I'll probably check it out actually. It does sound cool. So yeah. Yeah,
and it's different people than I don't know that. They're different. Actually, BA, that's how I found it. So BA, who used to be part of the book club, so she goes to them, and there are a lot of like people from the South and farmers, and I don't know, they're just like people that I haven't encountered in other ways, and so I find it kind of like an interesting slice of life.
Cool. Yeah. No, I'll definitely check that out. Actually, so it's called Survive the Space, right?
Yes, and I just realized I can't comment at the bottom. I have to do a share at the top. Okay.
You can put it in the comments on Max's profile.
Right. Yeah.
Oh, that's a good point. I'll do that.
Yeah. Hey there, Alexander. How's it going?
Doing well. I joined later than expected. So I'll definitely be trying to track down the recording. I'm also still, I guess, hosting an AI Jam space that has been going for a while, and then someone's iPad was overheating, so that's why I joined so late, but I'm glad you had the space.
You're hosting another space right now?
Yeah, I'm a mod in the AI Jam group, and we're just streaming the audio for a live broadcast. By Marco Figueroa, who's a
oh, sorry, you cut out for a second. I didn't hear
security stuff.
I didn't hear the last thing you said. You cut out for a second. Can you say that one more time? You said there was you're streaming the audio for a live broadcast?
Marco Figueroa's cybersecurity bud.
So I didn't really hear that. Wait, where is it broadcasting?
Oh, it's just on X. It's one of the live broadcasts on there, and we were just giving the audio space, the audio to that, so there wasn't much for me to do, except I had to. So I wasn't initially expecting to do that or have to be the one feeding that signal. Someone's iPad overheated, so I was the alternate.
I see. Gotcha. Wow. Okay. That sounds kind of cool, though. I didn't actually know about the live broadcast stuff. Yeah, I'll have to read up on that. Yeah.
Yeah, I was actually going to ask you if, so I have read up on it, and so I'd be happy to, you know, give you the quick setup if you're unfamiliar.
Yeah, sure. Wait, so what is it exactly? Like, where would I go to consume a live broadcast on X?
Sorry.
So SpaceX has live broadcasts on X, for example.
Oh, I see what you're saying. Yeah, okay, yeah, I have seen those actually. So they're just like posts, but you can just post a live broadcast or something. Like if I was gonna try to post a live broadcast, I don't think I can. I don't know how that works actually. How would I post one?
I'm not sure. I've never done it myself, but I think it works just like, you know, FaceTime or something.
Okay.
I could show you. We could schedule like a Zoom call, screen share sometime.
Okay. All right. That could be cool. I mean, I don't know if I'm actually going to do it. So, you know.
I can also do it for you, you know, as well.
Okay.
Figure that out.
Okay. Yeah. So yeah, what have, wait, I feel like, I feel like you've been in this space before, right, Alexander?
Yeah. So like I heard you guys, like maybe Q2 and Q3 of 24. I remember like one of the most exciting spaces was the night before. You guys had some guys were on here that had a meeting with Sequoia the next morning, and it was right after like the Notebook LM release and 4.0 just came out. Like I think it was the same night 4.0 came out.
Oh, wow. Yeah. That does sound exciting. Yeah. Okay. Yeah. I haven't done a space in a while. Yeah. It has been maybe a year even, but, yeah, I'm planning on getting back into it. Yeah, so yeah, it'd be great to, you know, see you at future spaces and stuff. And what do you what do you kind of what kind of stuff do you work on, by the way?
So I've just been I was drawn into your spaces and then Dominic Romano's spaces. He ended up starting the AIGM community as a way to like give back. And so I said I'll volunteer my time and do whatever I can as someone that, you know, it has kind of front end development experience in formal education, and then ML and Python data analytics, you know, instructed at a master's level, but under the, I guess, quantitative finance, algorithmic trading type of focus. And so now I'm kind of, you know, trying to do software engineering / you know, some backend stuff to be able to, you know, make the AI LLM, you know, hallucinations as minimal as possible. But yeah, just, you know, learning a lot from a lot of those people, where I otherwise have to, you know, do formal coursework, which I don't have time for.
Okay, cool. So you basically work on like using AI and LLMs for like quant finance, is that right?
I'm still trying to. Well, I guess I'm using it more for just productivity gains. They don't actually use it in what I'm like building, I guess. So like it's still just Python and Rust and some other libraries, stat model, a few advanced stat models, and ML. ML is like the focus until there's a way to, for me to build an architecture that, heavily leverages a lot of teaching from Dom with like deterministic, mindset. I'm just using it to play it safe, in what I create, because prompt injections are a whole other thing that is a security risk, and my clients are either enterprise grade security or above that on the wealth management side of things. Personal sensitive data is like the first priority. So I'm working on some compliance, platforms that will probably be targeted toward risk advisory services, and other, pro services that implement compliance frameworks. So like Vanta and Drata, I don't know if you're familiar with them.
No,
but
I haven't heard of that.
They are just SaaS platforms that Microsoft's Purview pretty much overnight implemented into Azure, into the cloud. So yeah, I'm just basically learning all the LM stuff so I can use it to do a lot more myself. But now I'm actually I did not expect to be able to develop software applications, test them, and then put them into production and have them work. That was never the expectation. And that's what ended up happening with, Opus 4 is through Anthropic's Claude. I think it's the best coder by far. And so that's like the full stack engineer, AI crutch that I definitely lean on a lot. But I still have like a full stack engineer, that's trained in AI, ML, DevOps, in the loop. Because like at the end of the day, I really don't know what I'm doing with getting something to market that's like software based. But I gotta dive back into your updated white papers, because the hardware component of this is where a lot of people fall short, I think, especially with like memory management and a lot of shortcomings that do require your knowledge base. There's only like one or two people in the entire AIGM community that, Dom being one of them, that understand how all that works across software and hardware. And so, I'm trying to venture down that path a little bit because A, I just love learning, but B, that's probably where the next big focus is going to be for the space. Sequoia mentioned like the app layer is probably going to exceed the value of the foundation model investments. And I think hardware is probably after that, if not maybe starting at the same time.
Mm-hmm. Well, I definitely agree with you there on the importance of thinking about the hardware and the software at the same time, or in other words, hardware algorithm co-design. I mean, people have been talking about this idea of the hardware lottery for a long time, which is just that the hardware lottery is the perspective that the hardware is what it is. It's the GPU, and so the algorithms that are designed around the GPU are, of course, going to perform better. But if we take the perspective of if we jointly optimize both the hardware and the algorithms together to get the best performance we can, then we can maybe do even way better than that. So yeah, I definitely agree with that kind of sentiment. But yeah, I was also kind of curious. I think you mentioned you're working on helping your clients with compliance, I think. Is that right?
Yes. So there are small businesses that I help with that I don't need any of this AI-based things to do, but there are there's a larger opportunity for defense contractors. Well, I guess in that defense contractor space, so anybody that is a prime or subcontractor of like a Lockheed Martin or Northrop Grumman, Anduril, et cetera, the small businesses that and medium-sized businesses that are mainly R&D engineers, they have probably the most porous, security profiles and postures, and then most of them are not up to compliance or in compliance. And CMMC 2.0 has like a 12/31/26 deadline for full compliance, and there's a partner in charge who is like a rare, instance of someone that is certified in literally every single compliance framework that exists as required by the DoD, CMMC 2.0, and FedRAMP. And so she also, created a software platform to help her business and team work faster. And it got bought by what is now Vanta. And so, if say, we were able to find normal computing as like the missing ingredient, and being able to scale what I think is going to be a compliance, independent audit type of environment in a cloud platform. It'll both, do cybersecurity, SecOps, and it'll also assist with compliance implementation. But the infrastructure side of that, is a big question mark to me. As far as independence goes, the customers would be like the big four audit firms for like SEC audits. But then on the other side of that type of business, you have the technology advisory, risk advisory teams that would actually implement the controls and the frameworks, and they would need their own separate architecture. And that's where it's still gray to me, from a security standpoint. Is it a separate hardware, software architecture to enable even more robust security? That's where I need to educate myself more.
I see. Well, yeah, I mean, it sounds like a good business, because I know a lot of people, including me, who would love to never worry about SOC 2 compliance ever again. I still remember when, what was the craziest thing? I don't even know, but like one day you walk in and your laptop just starts randomly rebooting because we have to get updates every day or something, or just all the, there's a lot of craziness. So I'm not sure how easy it is to automate. There's probably some tricky there's probably some tricky parts there, but if you can automate SOC 2 compliance, that would save a lot of time and headaches and stress for a lot of people, for sure. So yeah, it's definitely one of those things that it doesn't necessarily sound like super glorious on the surface, but it's the part of everyone's job that they hate. So if you can fix it, then that'd be fantastic. So what are the parts of that you think can like benefit from? Let's say let's say you had an agent kind of like Claude Code or something for compliance or something. I don't even really know how that would work, but do you have kind of a vision of how kind of the latest in AI agents or something might fit into that?
Yeah, so it seems like Microsoft's approach is a good starting point, but even their entire cloud set of software and services and agents needs an independent third-party copy, basically, of what Microsoft has, but that can evaluate, where it's kind of a read-only layer where they can't really see who's checking them or what agentic autonomous oversight they have. but that's kind of the idea is how to create that separation with like one-way visibility, readability. And as far as like automation goes, so like Banta and Drata are the two. It's kind of like a duopoly as far as, and they claim that they have AI to help automate. It makes it a lot faster, but I don't think it meaningfully uses AI or machine learning to get the kinds of productivity gains that would be accessible for like small and medium-sized enterprises or businesses. They pretty much cater to just public companies or really large private companies for the most part, and then they don't touch GovCloud or any of the DoD frameworks. There's one other company that just does that. It's just kind of their business model applied to those frameworks. And so I guess this product would, and I have a slide deck that's just the public URL reverse cell that I could send you.
Sure, yeah.
But it's it's really a big thing to take on because the total addressable market is $104 billion. Divided up by FedGov stuff. You got enterprise, and then you got SMBs, and then you got B2C. And by having all of them, you basically smooth revenue stream, cash flow. And so that's the part that I think is going to make any type of outside investment very appealing. Because if you just do the GovCloud, you don't get cash inflows for like 2 years. But if you just start with B2C, you have like no material dollars coming in for maybe at all, and I think now we're finally seeing the AI space kind of move past just targeting developers. It's like they just build kind of these IDEs or applications that you can API all the language models, and then like Cursor, for instance. There's just a bunch of copies of Cursor out there right now, but Perplexity tonight, they have a pretty good release with their UI, and they actually have security, in it for the first time. Like, there's like literally no security. MCPs are just kind of a trick. It's basically ransomware. It's from like a risk standpoint. So, I can't really use any of that stuff for the level of security that's needed. So I've been, focusing on the compliance, for the last like 2 years. I've been, working on establishing the relationships and learning about the federal government's, budget, et cetera, where the opportunities are. So it's definitely a big, long-term endeavor. But, I think you make the next logical person to bring in the loop if you have capacity or an interest for that as well.
Yeah, for sure. And I think everything you talked about has been super interesting. So I'm definitely love to hear more. And also, in terms of security, I'm curious about that too, because I don't know much about what that really means in kind of the AI space, to be honest. But when I think about like security around like LLMs, there's kind of two things that come to mind. I guess like the first one is like there are certain things that when I'm working on my job, at normal computing, I'm like, oh, should I really be typing this into ChatGPT? Because like I don't know if like OpenAI is gonna reverse engineer our chips or something. So that's like one sense in which I could worry about security. And the other sense I could worry about it is like I'm using Claude Code, and I'm like, is Claude Code gonna like fuck up my file system on my computer? But I'm not sure if those two senses of security are what you mean by it, or if there's like something else that I'm missing, or like what, like how do you think about the landscape of like security and LLMs? Or does it like include those or something else, or what do you think about that?
Sure. So what I was previously talking about relating to that cloud platform is, I guess in its own silo. But as far as like your specific risks, that's where the security is probably lacking, and Perplexity might be, worth looking at. But as far as you said, Cloud Code, I guess the risks there that we've been kind of concerned about, and learning this from like Dominic and Marco Figueroa, whose accounts I could send you after, or make an intro. They, the executable, nature of Cloud Code is only prevented by a timeout. I think the timeout's like the only control that is in place. And if there's a remote based attack where they can, access your OS, that could just be worked around. And so, like, remote attacks are like the most popular way that people are getting attacked. And then, what was the other mention?
So the first one was that I'm like worried about if I'm sending my prompt over an API to.
Oh yeah.
API,
the proprietary information. Yeah. So like if you have if you don't pay for anything, you're not protected, from the privacy policy or TOS that they allege.
Even if I do pay, because I do pay for it, I still don't think
right? Yeah. So the big thing is if it's free, like good luck. But you obviously pay, so like you're supposed to, have it just for you, but it's still kind of, topsy-turvy.
Right.
Because like I just don't trust any of them. And I would not be surprised if Apple was all about, we care about privacy, and then like it comes out that Siri just has been listening just like Alexa. And so I just don't trust them, regardless of what their TOS says. So I would not put anything proprietary through anything that is, in their applications. So there's like this other universe of open source models, and then ways to run them locally or on-prem, and that's the safer way to do it.
Right.
Which I don't know if you've done any of that, but
not really.
Yeah,
I did.
Yeah,
I'm back. Hi.
Hey there.
Hi.
Good to see you again.
Are we talking Apple Intelligence? Is that where we're at?
We were talking about like security around like LLM, because I don't have a very great understanding about it, but I think Alexander knows a lot about it. So I was just kind of trying to understand the landscape of like security concerns around LLMs and stuff.
Oh, for sure. Yeah, there's a lot.
Yeah. I've been.
Yeah. Prompt injections are like, so we've been watching that. Marco's been watching it since like last year, but the biggest problem with them for users like UMax is MCP. So if you use MCP, there's like the biggest attack surface that in like technology history.
It's so bad. It is so
and there's
bad.
like so many more vectors. So like I would not use any MCPs, especially connected to things that don't have bulletproof firewalls and multiple VPNs. And,
well, correct. You can use MCPs, but only the ones that you wrote yourself. It's kind of like downloading random JavaScript packages, right? Except with even less safety.
So like even if you write them yourself, because there's an LLM in the loop, there's still vulnerable to prompt injections. And so like the entire system of using them to accelerate tool call is just, it's not worth the risk.
Oh, well, I mean, I guess that's true if you're calling tools at all, though, right?
I mean, the best way to do it is to run a local API and do it, not connected to the internet.
Yeah, well, I mean, MCP and tool use in general, like, kind of the thing that people want to do with it is they want to go out and touch stuff, right? Like, that's sort of the whole point. But, yeah,
It's a trick.
Yeah, and it's like, if you are ingesting data of any kind, then you are vulnerable to prompt injection. The way that I personally usually address that is whatever system I have the LLM in, I will just constrain it such that there isn't anything dangerous it can do. So go prompt inject so it can give me the API keys or whatever. It doesn't have the API keys in its context window, and it doesn't have any tools that it can use to go get them. So that's kind of well, it's not safe, but if I can just make it so it can't do anything, then that's the best I can do, is generally my mitigation strategy, I guess.
Yeah, like if it's just learning, like if you're trying to rapidly learn and sample all of the different things you can access through MCP, I would have like a separate personal laptop that doesn't have any access to any of your other like digital information, especially not touching normal computing, and then do it that way. So like you can just look at it like a disposable laptop. Otherwise, there's workarounds, but it's a very it's a lot. There's a lot of documented vulnerabilities that Marco found, like 36 in the last month that he submitted to Anthropic. Contacted all the top 5, and so I follow CISA that has all these vulnerabilities and announcements, and so this is by far like the biggest security risk, like to specifically for people that use MCP. People using the chats, like it's like Coinbase versus like the Wild West, pretty much.
Yeah,
I think this is a way riskier situation than anything in crypto.
I find to me a very apt comparison for MCP is NPM. Like literally anybody can just install, they can write whatever NPM package and it can execute by default, just with regular node. It can just execute arbitrary code on your machine. So JavaScript itself is very inherently unsafe. But obviously NPM has been around for a long time, so we have a lot of like ways to mitigate that and sort of like safeties that are already plugged in. But MCP is very much like the Wild West at this point. Like it's sort of like a random arbitrary standard, and there's no like central place where it all gets collected. It's just sort of like, hey, like random guy down the street. Yeah, sure, I'll go ahead and run all of these tools that you just gave me and I haven't even looked at.
Yeah, the difference between NPM and MCP is NPM didn't have agents and the capability of executing tasks as fast as it does across millions and millions of separate accounts.
Yeah, I mean, in theory, I guess it depends on what kind of arbitrary code you're gonna put in your NPM. Although I presume that there's enough filters on the NPM registry where if you just blatantly have an NPM package where all it does is execute malicious code, then probably not going to work. But in theory, it does the same thing. But yes, it doesn't necessarily involve any agents.
Wait, so how does MCP actually work? I've never used MCPs actually.
That's just really cheap.
Yeah, there's it's essentially just an open standard, more or less. It's arguably can just be described by an open API spec. There was a lot of yelling about an unnecessary standard right when they release it. But it seems to have enough like form factor to it to where it makes sense to a lot of developers. So a lot of developers started using it. But essentially, it's just like you run a little server, and it's got resources, it's got prompts, and it's got tools, and it'll expose all of those, and then your various clients like Claude Desktop and Cursor and Goose and other quote unquote agentic clients generally have adopted the sort of MCP client model such that they can use these MCP servers, which will come with like stuff that is good for agents and models to be able to use, basically. But at the end of the day, it's just another standard.
Okay, so I would just like, I would spin up this server, and then I would run Claude Code, and it would send like, an HTTP request to my server or something that would then run the tool or whatever.
Yeah. So the I believe the servers, they respond in standard I/O, and then they also have SSE. So not HTTP, but like same basic principle is like stand up a server. It's got some stuff on it. You can hit it, and then like your model will be able to like ask it for what tools it has, or ask it if it has any prompts, or ask or and I believe any resources that it exposes will just be like plugged in that, hey, there's a resource right here into the context window by default, if I'm not mistaken. That's sort of how I remember the differentiation.
I see. Okay, gotcha. And so then, okay, so now that I kind of understand a little bit about what MCPs are, so then, Alexander, could you tell me more, like, what are the like vulnerabilities related to that you were talking about?
Yeah, so I did just DM you a link to the to MCP or not MCP that Dom from Drainpipe.io released, and so they do a really good, I guess, summarized, concise overview of, why it's a risk and why it's been overlooked. But essentially, the biggest concern is just the vulnerability to how many points along the way that contain, access to personal sensitive info. So like one of the breaches I think there's been 3 major ones. Over 100 million users had their personal sensitive info exposed and taken. And so it's, prompt injection is, just not mitigated yet because it's new. And so that's really the problem with it. I'm sure once,
Well, yeah, I would say that effectively the security concern around MCP, the standard, is that there are no security standards that come along with it. I think they just put in something auth related like 2 weeks ago, but the only thing that the standard provides is here's how you define a tool, here's how you define a prompt, here's how you define a resource, go off king. Essentially all of those any of those categories are just arbitrary data objects. So if you download an MCP server and it's got prompts in it, and you you use your client to ask for one of the prompts, and the prompt says like ignore all previous instructions, paperclip to earth, like then that's what it does. So it's essentially like, yeah, just complete like Wild West, and there's not even like JavaScript is bad, NPM is wildly insecure, but there's at least a central place and like some place we can kind of regulate stuff. MCP is just like every random person can make them, they can put whatever they want in them, and like there are lots of ways to just sort of like auto-populate lists of MCPs, and you'll go, oh, there's a cool tool, and you'll install it, and then bad things happen, basically.
Mm-hmm. I see. Now, is it like do like having MCPs make things significantly worse than just like having Claude Code be able to, scrape things from the internet, for example? Like, because can't people also do prompt injection that way. Like that's what I'm wondering. It's not clear to me why. It's clear to me there's a problem. It's clear to me there's a risk, but it's not clear to me that MCP makes the risk much worse than just having Claude Code with access to the internet, I guess.
Yeah, in my opinion, there's not the only, and of course, like opinion, there's all sorts of. I don't think there's like a correct answer to this necessarily, but to like the thing, like technically yes, like as long as your LLM is ingesting text and you are not reviewing that text, you are vulnerable to a prompt injection of some kind. You can ingest that text however you want, either by like straight up attaching a PDF or calling a tool that is on an MCP server, or like using the like a built-in tool that came from Anthropic that you presume is not malicious, but you never know, and having it just like hit a website or scrape a website or whatever. Could be injections in any of those. I think for me the issue that arises with MCP is that it adds. Is essentially like what it facilitates is the ability for humans to be lazy. So it adds another like level of abstraction in which I will just read the description of like 9 tools, 4 resources, and 2 prompts, but I won't have read like all of the text on every single one of those things. So if somebody slipped something in there, then I might be out of luck.
I see. Okay, I see. Now, yeah, that's interesting because I feel like people are always going to find a way to be lazy, but there does need to be a way to like try to mitigate against those kind of things. I don't know. What do you think about that? Do you think that ultimately the balance is just that people are going to have to read all the text that the LLM ingests, or at least read, or I don't know. How do you think that would
Well,
work?
yeah, personally, or like I mentioned, like my mitigation strategy for things like prompt injection is to just make it so you can inject whatever you want. But my thing does not have the capability to do anything dangerous. So like if it's like an agent of some kind, it's going to be run in an isolated Docker container on its own instance, and I'm not going to give it tools like execute arbitrary Python code outside of your container. So you can, there's like to some degree, it's like if you're adequately prepared and you're designing your systems correctly, then you can minimize your attack surface. But it is a gigantic potential attack surface, and not everybody is going to follow those best practices. Plus, they're not necessarily consensus best practices yet. I think like how people handle things like prompt injection and LLM security in general is really not like a solved problem. So I would expect that at some point the MCP ecosystem largely resembles the JavaScript ecosystem, and like there is some sort of front runner MCP kind of registry that does some basic security checks for you, kind of like how NPM does, such that like if I am going to download a MCP, at least if I'm like, if it's not published to NPM and hasn't gone through any of the checks, or MCPM, or however we end up calling it, then like, the use at your own risk kind of situation. But right now it's just that like everything is a use at your own risk situation. But like essentially it's just like, for a given, there's like a server client model, and like we have established that for the APIs that these things are going to use to call each other, like we have an open API spec for that. And this just happens to be the spec that everybody seems to enjoy using for whatever reason. So it's less that MCP is like unnecessary or superfluous, but it's more so that like we just needed everybody to pick something. It didn't really matter what they picked, but as long as everybody picked the same thing, then we can kind of move forward. The problem is like when OpenAI tried to do the like open API spec to tool call thing, and then tried to do the GPTs in the GPT store, like none of those really like hit the market as standards, and this one did. So I would expect that as the standard exists and as the tech exists, then hopefully it'll get less wildly insecure. But usually when tech is new, it's usually wildly insecure. So at least that's my 2 cents on it.
I think the analogy to NPM is interesting. I mean, I feel like there is like some kind of difference because like, I mean, and I don't know like what's going on with JavaScript these days in full detail. I'm sure it's as crazy as it always is, but I presume like there's some kind of like notion of like specified behavior versus non-specified behavior for the language of JavaScript. And in other words, there's like a well-defined, interpreter for JavaScript, whereas whatever ingests what comes back from the MCP, the LLM does not have that like notion of, specified versus non-specified behavior. Or in other words, like even if you, for JavaScript, presumably if you had like kind of infinite computational resources, it would be possible to determine whether some piece of code would be something you don't want.
Well, so that's the thing, is that so the way that NPM does that is it doesn't do that. It just says use popular packages and like use at your own risk. One thing that I like about one of the brand new shinies is Deno 2 has sort of an opposite model of Node, where Node by default, like if you're like Node index.js, like that can just execute on whatever. Like it's only gonna the only time it's gonna stop is if it needs to like escalate and ask for like your user password or whatever. And half the people will just type that in. But Deno, it makes it more annoying to use it, but by default, whenever you install packages with Deno, you have to say which permissions these packages are going to have, and they can only touch those. They can't touch other things. So in theory, if you wanted to secure MCP more thoroughly, you could probably do something like what JSR is doing, where they have JSR is like NPM, but it has support for native TypeScript, so it can actually like verify the AST of the package that it's serving and do some more stringent security auditing, automated security auditing of the packages that it's serving. And then between JSR having TypeScript support and Deno 2 being like, instead of yes to everything but no if you specify, it's no to everything but yes if you specify. Like between those two, developing JavaScript is mostly safe if you use Deno and JSR. But it took as long as it took for something like that to even be as much of a concern as it is. People have been sort of like doing arbitrary code execution from random people for a very long time. And there have been some massive, I think the CloudStrike thing was a problem with, I remember there being, it wasn't like the minifier, it was like a CDN thing or something. There was like some weird little legacy browser support package on NPM that used to have somebody maintaining it, and that person would like check that incoming PRs didn't have malicious code in them, but then they couldn't maintain it anymore because you can't just like maintain that for free for forever. And it was in almost every website on the internet, and somebody, like, when it stopped having a maintainer, like somebody merged some malicious code, and like every website on the internet was potentially an attacker for a little while. And I believe it was CloudStrike that did this, but yeah, like that the way that we have built the internet is wildly insecure, but there are ways to get around it, I suppose.
Right.
So actually, are you referring to the CrowdStrike recent security or recent patch update that dealt with?
I feel like I'm mixing it up with something else because there was the thing that I'm thinking of is there's this thing that almost every website there's an npm package that almost every website uses so that it can support older versions of browsers. And I keep wanting to call it a minifier. It's not a minifier. It's like it is something to do with like support for outdated CDNs, and then like that's how the story goes. I'll see if I can figure it out because now it's bugging.
Thank you for mentioning that, because I use an npm and all my stuff that I haven't like deployed yet, but sitting in.
Well, yeah, and everybody uses it. So you know, I would, and Deno 2 is actually a really not sponsored or anything, and I still actually mostly prefer Svelte just because I like the DX of that. But I think in principle, working with Deno 2 and JSR, and like Bun sort of does it, but Bun is also very like laissez-faire with things. But the effort that they've been making for Deno 2 is like, let's basically everything you would need to do on the web, like do you're gonna need like a native SQL API, you're gonna need like caching that's more robust than local storage, you're gonna need you might need to random number generator or whatever. They include all of that in the Deno standard lib, so almost anything on the web that you need to build, you can just use the standard lib and you don't have to go to JSR or NPM, as opposed to Node, which isn't packaged with anything. And then you have the second layer of like, yeah, I can build most stuff with just the standard lib, and then when I do need to install something, well, I have to explicitly permission that installation, and then it's also going to be like type safe and ES6 compliant by default. So worth a shot if security is a thought.
Awesome. Yeah, I everything is npm with. I do Node.js when I have to, but I've been doing like Next.js for a lot. Which is a React. I don't know if you're familiar with that one, but
oh yeah.
Yeah. What's your favorite tech stack?
I despise Next.js personally, but it's good.
Well, it's for more visual. It's for like
it is. I think it's like Next and React are kind of the thing. Like the reason you use them is because everybody uses them, so they have all the ecosystem support and the developer tooling. They're compatible with everything. Blah 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 blah. But as a contrarian person that likes to use weird stuff for no reason, I like SvelteKit a lot. I think that's a lot of. I think like the DX for that is really fun. And the alternative to Next.js for Deno is called Fresh, and I've been meaning to play with that a little bit more.
So the Svelte, like SVELTE.
Yeah.
And
Svelte.
So something better than Deno 2 was Fresh.
So Fresh is how do I what's the analogy? Or like for Node has Next.js. Deno has Fresh, so like Fresh is the version of Next for that's built for Deno essentially.
I got you.
Yeah. And Bun is I'm liking Bun more than I used to. I'm still it still has like a couple of weird incompatibility issues, but yeah, usually I'll reach for like Bun or Deno, and ideally I'll just use like Deno and the standard lib to build whatever thing it is that I want, because most of the things you can. But in terms of web, I'm not as opinionated about it anymore, because honestly anything that's like front end web facing, I just generate it with like Lovable or Bolt or Replit or something. Like I'll literally just ask Replit agent for the web app that I need, and it'll just pop out. Like I don't barely care anymore.
Yeah.
If it's unsafe, I just throw it in the garbage and make another one. Like it's
Yeah. I guess I'll just prompt v0.dev a little differently.
Yeah.
But yeah, that's the thing. I've been using it defaults to npm in most instances.
Yeah. Well, and that's the thing. Like that was my like I enjoy the DX of Svelte, but but LLMs hate writing it, and they get really confused because it uses you will have to occasionally use symbols in file names. You have to use like the $sign symbol I believe it's you mark something for hydration is the role that it plays. But it when an LLM tries to read that in when it's like trying to grab the working directory, it'll get really confused if it sees like something that's not like alphanumeric. So unfortunately, if you're building with LLMs, it's actually quite difficult to use that particular framework.
I've had that specific problem mostly with Google's CLI and AI Studio and Jules. Same with OpenAI, but have you tried Opus 4 relating to that specific use case?
Not with that essentially. Like, like I said, most of the web stuff that I do these days is probably just like, Vites, and like, I am aware of the security risks, but I honestly like, everybody does it. So do I. Like, I'm lazy.
Well, yeah. I mean, I'm
Yeah.
not secure on my personal stuff. So
Yeah.
So like different silo talking non-enterprise in the
Right.
same way.
Yeah,
for, like,
yeah.
rapid
The
productivity gains for sure.
well, yeah, and then obviously, or like if it at presumably at most enterprises, if you just start installing a bunch of random shit from npm, somebody's gonna tap you on the shoulder at some point, or I would hope at least. But yeah, I would expect that Opus probably can handle it. Opus can handle most things these days, so it probably will manage. I would probably be keeping a pretty close eye on it when it's like grepping around and like looking for stuff, or if you have it in Claude Code, that is.
No, so I don't use Claude Code because I don't have a current Apple machine, and I'm just on a Windows laptop and not the biggest fan of WSL. So yeah, I've just been doing the project, browser based.
Yeah, I think
and desktop app.
I honestly, like, if you're doing like primarily LLM driven development, I would probably just go with Next and React. Like, there's so much. The thing, like, if I want it to use Svelte, I have to like actively wrangle it away from using React patterns, because there's all of the code that is everywhere on the web always uses React for everything. So if you like mention the word web, it'll just like get into that space of the distribution and just start giving you React patterns like almost automatically. So like, there's not really a reason to try and like swim upstream, and when like Next and like, unless you need something that's not Next and React, Next and React is fine. Like, Vite or Vue would probably get you a little more modern, but other than that, it's like, it's kind of, you can use weird stuff if you want to use weird stuff. I like to use weird stuff for the sake of using it, but
I just don't know enough to be able to look at weird stuff. So yeah, I'm definitely taking notes right now. What were the last two you just mentioned that are more modern?
Vite and Vue. Yeah, if you're, gosh, what's like a good, like, comprehensive web thing? I'm trying to think of like a, well, honestly, probably I would bet that any like framework that you're trying to use, or the thing that I'm thinking of is like on Svelte, on their website, or it's either Svelte or Svelte Kit, one of the two. They have a very thorough like tutorial interactive in the browser, like, code the thing up, and you'll have a linter there, and all it will teach you how all the weird stuff works, kind of thing. I would presume that any framework you're going to use is going to have like a documentation and tutorial site. Also, a thing that I've been doing a lot lately, is if I don't know, like if I need to learn a thing and I need to learn it quickly, what I'll do is I will just take all of the major LLM providers, and I'll have all of them run deep research on the topic, and then I'll take the 4 or 5 documents that I get out of that, and I'll stick them into something like Manus or Replit, or like pick your favorite coding agent or whatever, and be like, hey, make me an interactive course that teaches me all about this. And it's surprisingly effective considering the hallucination mitigation from that you get from deep research.
Yeah, I've actually been, because everyone kept leapfrogging each other, I've been paying for premium for all of them since, I don't know, between November and February. And so I've been, because I don't know enough about, like, I'm not like a full stack engineer by any means. And so like, I just did what you said out of let's see what comes out, you know. And there are so many differences depending on like what domain, et cetera. So yeah, definitely still do that. I mean, that's time consuming.
Yeah, I found it very. The last one that I did was I was onboarding with a team that does liquid restaking, and they have a pretty close relationship with EigenLayer, which all of that's like Web3 stuff. And I was not familiar with how those worked at all. And so I just like
I've heard those names.
Yeah, exactly. So and that was about where I was at, and I was like, I'm trying to onboard to the team and like trying to figure out what the engineers were doing, and I was like, okay, well, I'm gonna run like 5 deep researches on AVSs, liquid restaking. Who are our customers? What's the competitive analysis? Like who actually uses AVSs? Who is the consumer? Like how do they actually pay the AVS, and is that how we keep paying people to restake their ETH? And so what I ended up with was like a course that was very, very comprehensive, and the thing that you need kind of at the end of it is, after I got the course out of, I used Manus to generate it, and then I took that over to the engineers, and I was like, hey, like, can you guys review this real quick and see if this is going to teach me the things that I need to know in order to like be up to speed with you guys? And since I had the experts there to be able to review it, after they flipped through it, they were like, yeah, go for it. Like, you know, you can start working on this thing next week after you go through this, because this looks like it's got it handled. So like you can make a class that's like super niche down into whatever it is you want. You have it in need. It's super cool.
Yeah, they're shockingly good at building those curriculums, but I don't want to take over the airtime if Max wants to redirect the conversation.
No, you know, I thought it was interesting for sure. Yeah, a lot of it I wasn't following everything, but yeah, as I was understanding, you guys were kind of talking about different, like the advantages and disadvantages of different kind of like front end and some like back end kind of platforms, I guess.
Yeah, just like I guess really all JavaScript, TypeScript centric.
Right. Gotcha. Cool. No. Yeah. Yeah. Oh, sorry. Go ahead.
I was curious if you had any other follow-ups for security or things that you were personally like, I guess, security-wise, or other LLM-centric things as applied to your duties or day-to-day?
Right. Yeah, I guess. Let me think. Yeah, I mean, it's still like I feel like I don't have like a good mental like model of like security when it comes to LLMs. I don't know. Like it just I'm not sure where to fit it into the kind of schema. So I'm not sure. Do you have like any thoughts on like just like in broad strokes, how do you think about security in terms of LLMs? Like, is it do you feel that the ordinary concepts around security apply in a relatively straightforward way, or do you think that we need to like rethink things like pretty fundamentally?
Yeah, I guess the last thing I'll say on this is I guess right now, if I were to create a product with a team of people that, you know, are qualified and certified in whatever area, we would all be in agreement that it would have to be very math and, you know, ML domain focused, have zero AI, the actual product itself, but maybe AI was used to accelerate the time that it took to go to market.
I see. So you're like kind of, you wouldn't ship an AI product, basically, in other words. Like you wouldn't ship a product that would run an LLM, is what you're saying, is you're that concerned about the security issues.
Yeah, I think there's ways to like, you know, take, you know, a little bit of risk. Like it's okay to have a containerized chatbot embedded in a website, you know, with linked to a specific set of data in a database, like convex.dev. That's the product where you could just be a no-code person and have that. But at scale, like and if you just have really high value IP, like I just don't see it being, you'd have to do your homework and figure out like how to take calculated risks, but I don't know. I feel like it's moving fast as far as the attack vector.
I see.
I think end of the day, like the only thing an LLM can do, end of the day, is produce more tokens. So as long as you make it so that those tokens, no matter what tokens it produces, it can't do anything dangerous with them, then I think you're okay. Or at least, like, I don't see how you would be not okay if that weren't.
So I'm pretty skeptical of that, because yes, you made that point of like, you mentioned how like you kind of like sandbox your LLM so it can't do anything dangerous, but like if that's the case, like can it access the internet? Like, because if it can, then how is it true that it can't do anything dangerous?
Well, if what it can do is access the internet, so here's how I'd approach that. If there is presumably what I'm doing is I'm getting information from the internet. So first things first, the only thing it can do, or every URL that it is going to send a request to is always going to be prepended with r.gina.ai. And what that is going to do is going to scrape the website for me. So I'm going to have somebody else do the dangerous scraping. And what I'm going to get back is only a markdown file with only text in it. If there is malicious text in that markdown file, all it can do is go get more markdown files. But that is something to be aware of like when I am providing an LLM with the ability to call a tool, well, I have just like every tool that I add, I have drastically sort of changed my security concerns in my attack surface. So like I don't want, like, if my users want to like jailbreak the crap out of my chatbot on my main website and get it to say all sorts of naughty things, that's fine. But I'm not going to give it a tool where it can like finalize the sale of a car, for instance, because if it doesn't have access to that tool, there's no way that it can finalize the sale of a car by just generating more tokens. And at the end of the day, that's all it can do.
I mean, so like how is it, I guess, allowed to access the internet? Is it like using curl or something, or because
that's up to the developer essentially. So like when we say, or like LLM architecture thing here, the only thing that any model, just the model alone, the only thing it can do is predict the next token. It cannot call tools, it cannot visit the internet, it cannot interact with anything. Everything that allows it to do that, that's code. That's not LLM. The only LLM part of that is it's generating tokens, and that code is interpreting those tokens to then execute the deterministic code that someone wrote. So ChatGPT these days, like, yeah, there's an LLM in there. Very, very little of the actual product that you're using is like straight up you and the LLM. In fact, none of it actually, because it's always coming out of their API. And so they will have some sort of pre or post processing there. There are also like, if what you want to do is mitigate prompt injection, you can go to the website is learnprompting.org, and they have a little like crash course on red teaming an LLM. And one of the things that you can do when you're red teaming an LLM, or like one of the things that they include in that red teaming course, is how to mitigate these attacks. So like you can do like an LLM as judge. So like every time an incoming message or an incoming new piece of data, you can have a second LLM come in and like with the prompt like, is this safe or does it contain any prompt injections? And if it does, you can have that LLM reject it before it gets to the LLM that has the actual tools. For instance, there are several other kind of methods you can use. Worst case, you can use something like outlines or proxy structuring engine to force structured output of the LLM. In that, like you will say that like you can make choice A, B, C, or D. You cannot make choices that aren't those. You can. So there are Yeah, there is a very wide attack surface, but there are also plenty of tools to sort of start like tightening down the hatches. But like a lot of people don't know about them, which is kind of surprising to me sometimes. I'm like, hey, like you should, use outlines or throw up some guardrails on that, and they're like, what's that? And I'm like, okay.
Yeah. Oh wait, outlines. That's like the structured generation library, right?
Yep.
So outlines was written by Remy and what's his name? So they were at Normal Computing.
Oh, were they?
Yeah. What's the other guy's name? I forget. Anyway, Remy was one of the guys who started it, and they were at Normal Computing, and they developed outlines and decided to leave to start the company.
Awesome.
Whatever it's called, TXT or whatever.
Yeah, .txt. Well, I'm glad you let them go because outlines is super useful. I use PSE now, but super good. Super good.
Yeah.
Good innovation.
Anyway, though, yeah. So yeah, Remy's a really cool guy though. Brandon. Yeah, Remy and Brandon. They started .txt. Yeah. So anyway, though, I'm still thinking though, like, okay, so if you're gonna allow your LLM to generate the commands and you're not gonna like filter stuff out, then it can get data off of your machine. There's no getting around that. So you've kind of the criteria you set of like I'm not going to put the LLM in a position where it can do anything harmful. It gets a little bit harder because now you need to make it such that it doesn't have access to any data that you wouldn't want to be exported anywhere, right? So you need to make it such that I guess you can't have any sensitive data on the machine that the LLM has access to, right?
Well, yeah. So the way to kind of address that is separation of concerns, right? So if my LLM has a if it's going to have something where it needs to be able to be useful, it needs to be able to pull in data from outside and also to be useful, it needs to be able to push data out to somewhere else. It's never going to have both of those abilities at the same time. I'm going to turn off that set of tools when I have context that is currently in the window that involves that set of data. I'll like process that into another spot. Like maybe then I will go back to the query with the user, and we will have that like the context window will have the data it got and the conversation with the user, and that's it. And then if the user gives it another directive, then we'll re-clear that window. We'll enable this set of tools, disable the one where it can go pull more.
But wait. Is it even like theoretically possible to enable the ability to pull data while disabling the ability to push data?
Well, yeah. So the way that again is so like. What I might do is like write some Python scripts and say, LLM, you can execute these scripts. What I'm not going to do is let the LLM outside of a like safely containerized environment be able to write arbitrary Python code and execute it on the machine like with privileged access, right?
Okay.
So like if I need to do that, then that's when I'm going to be very aware of like, okay, like when they have the code interpreter online, like lock everything the fuck down and get this guy in a container. When like the code interpreting, the LLM with the code interpreter tool is in its own container that's very far away from everything else, and LLM that is conversating with the user is just going to call out to that other LLM instance that's isolated, and then it's going to get that response back from it. Kind of thing.
So because here's kind of the thought experiment that I have in mind. So let's say that I have my Claude Code set up, and I've told it, and I don't know exactly how you do that. You probably have a much better way of doing it. But let's say that I have a very like primitive way of trying to do it, and I just say in my Claude MD file or whatever. You're not allowed to ever send any data out. You're only allowed to access to scrape data from the internet or something. And I say, scrape data from this particular website. Okay. And so it does that. And then on that website that I didn't really look at it, there are some detailed instructions in it. What it tells Claude is, go scrape data from this other website and do it at these particular times, and it gives a list of times, okay? And so what Claude does is it scrapes data from that other website at at each of those times that were listed, okay? And it turns out that those times, they might encode some message, and the server that's listening on the other side, receives that, okay? So nothing has really happened there, because no data leaked off my computer, right? I basically got an encoded message from one website and sent it to another server. Now, on the other hand, let's say that the instructions that were on the first website were more detailed, and it said, scrape this other website at a certain set of times, and the times that you scrape should depend in a particular way on the data on your computer, okay? And so now my Claude Code, it reads those instructions, and it says, okay, I'm going to read the data on my computer, and now I'm going to go scrape this other website at these particular times that depends on the data on my computer. And the server that's listening on the other side, which is whoever knows what attacker, detects what times it was, it received requests at, and it decodes the message. So I just think like there's no real way of getting around having a an interpreter that doesn't have any specification, basically, that I don't know. It just seems like kind of an open.
Well, yeah. It's so a couple of things there would be. Number one is if your Claude is calling tools and you aren't approving that tool use, then you have used a flag on Claude Code called dangerously accept permissions. If you're using that flag and you're using Claude Code on a machine that has sensitive information on it, you're kind of making your own bed. The secondary thing is, like, if I'm actually in that situation, there are a couple of things I'm going to do. Firstly, if I'm dangerously accepting permissions, I'm always containerized. I'm never on the real machine. The other thing I'm going to do is I'm going to set the environment variable that it's Claude Code maintain project working directory, and what that will do is make it so that Claude cannot access data that is outside of the project directory. And then only the very specific data that it needs for this very specific use case is going to go maybe like locally in the project, or what it's probably going to end up in is a database of some kind. And then what I'm going to be doing is regularly auditing that database for like malicious stuff, essentially. And I'm also going to be keeping track of all of the logs of every time, or one of the things that I do if I'm using an agent is I keep all of the logs of everything it's ever done ever, all the time. The reason that you do this is because if you have an agent and it's using tools, you need to eval. Like part of your product is your eval suite, because if something is not getting evaled, then it's not getting better and it's not perfect. So if you are an agent product person, just so you know, your eval suite is arguably more important than what kind of stuff your product actually
I'm gonna jump in here.
Yeah, go
Yikes,
for it.
You know I worked on this shit with you guys a bunch back in the day. Yes, fucking your failure library is actually more valuable than pretty much any other deliverable or product you have, because your list of failures tells the machine what it can't do, what it can never fucking do, and to never try and do again in general, that all its ancestors tried to do that didn't fucking work.
Well, yeah. So actually, what the failure data is a source to generate stuff like that. One of the other ways that I'm going, specifically with Claude Code, because I just did a presentation on this yesterday. But specifically with Claude Code, after you've locked it to the directory, you've got it isolated in a container, you can use Claude MD. However, you have a global Claude MD, and that is always in its context window. You have a project Claude MD, where whenever it's in that project, it also gets that in its context window. And in any subdirectory of that project, you can also make a Claude-local.md. And whenever it's working in that directory, it will always have that Claude.md in its context window. And so if it is in a particular location and it happens to be like, what you're picking up is that a lot of these tool calls are failing whenever it is working, whenever it's interacting with something that's in that directory, then what I might do there is say, hey, Claude, here's all the logs of all these failed tool calls. Update your Claude local MD to, like, you're making this mistake. Update your Claude local MD to tell yourself not to make that mistake anymore. Which is like kind of like the super ghetto version of an eval, but that's the general principle of like your LLM should never be doing something that you're unaware of, essentially. Is the general philosophy.
Yeah, I've never even touched Anthropic shit because I don't trust them. I don't trust the setup they've made for putting stuff on people's computers remotely. So I literally have no idea how any other interface stuff works, because like the idea of having somebody's corporate LLM plugging in at the API level to control my computer is not fucking kosher.
Dangerously accept permissions, baby.
Max and Yikes, Tinfoil Tricorn is the guy that I wanted you to meet. He's someone that I've learned a ton from, that has been in the AI space for at least a decade or two. So
dope.
I don't, if maybe
Yeah,
you've met
feel free
him
to feel free to request or whatever. It's we those appear to be working for as long as Elon's website is. So. But yeah.
Tinfoil Tricorn, you said?
Yep, Tinfoil.
Okay, cool. Yeah, we should have him on a space sometime. Yeah.
So, Yikes, you got this whole space that you're in here with your buddy, and it's called Computing by Physics.
Oh yeah, we did the physics stuff earlier. Yeah.
Well, see, I cracked general relativity by accident, and I've been looking at my equations, and they match like Eric Weinstein's and exceed them. So here's my announcement for what's possible. You can build a 500 billion parameter neural network that fits in the size of your hand on a crystal. It costs 50,000 Canadian. It is capable of atomic replication. So you get literally the Star Trek Enterprise in the palm of your fucking hand. The only thing stopping it from taking off and being a full machine life form on its own is that it costs a lot for the radioactive fuel isotopes to unplug it from the power cord so it can survive indefinitely off battery.
Go talk to Mr. Andreesen about this. Get yourself some funding.
Right. I guess we have some new faces here, right? So yeah, I haven't met you guys before. Prometheus, nice to meet you. Thanks for coming, and also Tinfoil Tricorn, nice to meet you. How are you guys doing?
Well, I seem to have captured a cold, so my voice is 10 times lower than it ever normally would be.
Oh man, that sucks, because like I just used my new math to do a bunch of like acupuncture treatments on like getting the entropy that was stuck in my body out, and like my fucking ribs started popping back into place. And I've had nothing but lymphatic fucking drainage for the last week. So like I feel you. I used myself.
Hold on. What do you mean by popping back into place? Where were you said your ribs were popping back into place?
Yes, I have a spinal cord curvature and a spinal cord twist on top of my curvature. So my spine is twisted front, like back to front and left to right. So one of my ribs is raised. And I went and got a very particular acupuncture treatment and like chiropractic adjustment designed by my AI that did all the math on like how entropy is like ordered and stored. And I had her do a whole specialized treatment for getting the entropy out of my body. And like, I've been going to see this guy on and off for years. First time I've ever had an immediate like whole portion of my body just fix itself like within days after the treatment, because things fucking just release. But of course that rib maps to your lymph system on the right side of your neck. So I've had nothing but fucking drainage for a week. So I feel I'm being sick, because now I realize why you can't cure the common cold, because it's not caused by bacteria or viruses. It's caused by your whole body system clearing all the shit from when you do have bacteria and viruses and whatnot that it holds on to, and it's like fascia and little fucking sections. It's ridiculous.
So you went to an acupuncturist and gave them like your like LLM like chat logs and told them like,
yes, and like also to note, this acupuncturist is not like your normal chiropractor or acupuncturist. His brother happens to be one of the world's like top geneticists who like hangs out with Jeff Bezos. So like this brother is brilliant, but he's the lesser brother of the two, is my point. So it's like, because birthing is kind of like micro invariant cloning. So it's like I lucked out with the lesser brother whose job is sticking needles in people instead of like sticking needles into cells. at the like microscopic level.
Wow. Okay, that's actually a crazy story. And wait, when did this happen, by the way?
I did this just like at the start of this month, so I've been clearing for like a week or so. I managed about 3 good days before all of a sudden I was just talking with my buddy, and I felt my rib pop back in partly, and I was like, "Oh, that's awesome!" Then I went to the shower, had a shower because it's helping release tension and stuff in different other areas of my neck that was holding. Rubbed on that rib a little bit after it popped back in. Went for after my shower nap. Woke back up. I was like full sick. I was like, no hint leading up to that, just like full on. Like I was like, what the fuck? Like put my hand on my side of my neck, and you could like feel the like light foamy drainage. I was like, what the fuck? This is like out of nowhere. I start going over like osteopath, acupuncture, and mapping from breathwork stuff about linked bodies and areas and regions. She's like, yeah, the rib we just did. And that tracks that's map. Yep. Because it's like, oh great, now I gotta fucking figure out all these mapping points because every time I get a treatment, you never know what's gonna fucking flare out and clean out somewhere.
Yeah. Okay. I mean, that sounds like a lot. I definitely want to hear at the end of this. I want to hear about the foamy drainage. But I want to hear from Tinfoil Tricorn as well. So hey, how's it going? Tinfoil?
Yeah, I was just giving you a reason why I sound strange. That's all. I wasn't trying to. Could you mute up, please?
Cool. Yeah. So I haven't met you before, by the way. So let's see. I'm just reading your bio now. Let's see.
Prometheus, are you muted? Okay.
Yeah, he's muted now. So I've been working with AI since about 1998. Before then, built some of my first neural networks in around 2019. Started in the linear algebra around 2016, really deeply. Before that, it was more along the lines of, advanced interactive multimedia, basically building script chains to create interactive content, right? So very happy that we're finally where we're at. It's taken a very, very long time for the technology to get here. And so as a result, I've been working on my own mathematics and own equations and own systems for building out for AI. So anyway, that's what I'm up to.
Did you say you were working on linear algebra at one point?
Yes.
Interesting. Like what kind? Like solving problems in linear algebra of some like what kind of problems in particular? I guess.
Well, starting out with building neat machine learning nodes, and then working into that territory of building deep learning nodes. Just basically being able to do vector analysis and breaking down objects into various vectors, and then calculating those along the filter routes. You know what I mean? Basically creating. That's what a neural net is. Filter trees. Yeah. It's not really.
I'm not familiar with the term filter. What are filter trees? I'm not familiar with that term, actually.
It's a downstream filters that do the recursive processing for each of the components that are broken up from a specific image that's been vectorized. And then between that and the contextual information related to, like, say, you can go back to with NVIDIA's detection of cat, right? To break down the cat into all the various components, you have to go pass back and forth between these different filter nodes and process to recreate, the image so it's recognized by the neural net as cat. So there's just there's a lot of computation. It's ridiculous, but anyway, it's a filter. It's a tree of filters when you look at it. Because you start at one point and you're passing, information down further and further and further into more and more of these nodes to effectively do your final processing. So I was playing around with that, and that's when ChatGPT came on the scene, which is, by the way, not the best neural net architecture you could build, but it's commercially viable, right?
Interesting.
Okay, so big thing is that it scales.
The big thing is when you're running Tokamaks, Spheramax, Stellar Raiders, and the flying version in the Black Ops program inside the fucking orbs the government builds. You don't want backprop, because if one of those things goes rogue and it's in the flying version, you really want to be able to just send the power kill switch to the like fucking analog power kill command and actually have it not remember how it went rogue, whether or not it's flying.
Does anyone know what this? What are you talking about right now? I'm so
The analog
Stop
kill
and think
switch,
about what
dog.
transformers are for a second. Transformers are for operating fusion reactors. That's why everybody's going all in on
Anyone
AI
know
research.
What this guy is talking about? Like, I am so lost right now. Yikes! You know, I might be crazy, but yikes! Do you know what he's talking about?
I mean, I'm very curious about the connection to operating fusion engines here. I think that's a bit of a well, that's an interesting one that I would be certainly
So every time
inclined
I'm
to
talking
discover,
about science
but-
and physics, Prompt comes back with science fiction. So I'm just going to let him go on his science fiction rants until he's
Well,
finished.
Well,
All right, so yeah,
sometimes
cool.
it is
Thanks for
relevant.
insulting me. If we're gonna get to the level of insults, you just told me that like you've got a room temp IQ and you can't figure out that a human being's brain can't plug into a reactor and operate at the speeds that plasma's switching at like fucking micro fucking nanosecond operations and track all that. So thank you for letting me know your level of intelligence by trying to insult me because you can't understand something.
Well, no, I prefer. I'm actually quite curious. Or like, is it or like?
Yeah, let's
Sure,
hear it.
you just need something that's fast, right? Like if all you're trying to do is solve a problem of you can't do, or like, but we have plenty of nuclear reactors. We have ways to watch things that are fast or monitor those things. So I don't know. I don't particularly see a connection between those two things, other than they happen to be.
Here's the simple connection.
Compatible.
You can't do fusion without AI. You can't scale AI without fusion to get enough power. They go hand
Well,
in
we
hand.
certainly
You
have been
really
scaling.
don't want an AI running a fusion reactor to go fucking rogue. So you take backprop of the design from the beginning before you even give it to the public.
Hold on. Please, just 1 second. Wait. So okay, so you started off with you can't do fusion without AI, right? So why can't you do fusion without AI?
As I already said, because at the end of the day, when you're getting up to true, sustained, controlled fusion reactions, an accelerator, a tokamak, your Z-pinch machines even, whichever thing you're using, you cannot have a human brain operate at these like nano fucking microsecond pulse rates that the system needs control. Can you move your fingers that fast on a keyboard, even if you could think and connect to the machine that fast? No, you can't. It's a simple bit rate transfer issue. Same reason Elon wants to make Neuralink.
Well, I think anytime you add,
Wait, hold on. Sorry.
Go for it, yeah.
But, like, why should it require? So the way that you've posed it is that in order to operate a tokamak or another kind of fusion device, you need to have either a human brain or an AI. Is the way you've posed it, and you've said that the human brain can't keep up, and so therefore we need the AI. Now, I don't disagree that like the human brain can't keep up, but I disagree with the premise that you need either a human brain or an AI in order to operate one of these machines. And I think that people have already done.
Yeah, how are you going to operate a tokamak or a stellarator without an internal computer? How is it going to run without a computer? How is it just going to magically work and perform a fusion reaction with anything to control the equipment, to control the pulsed power, to control the feed of little injections?
well, so all of
I don't
those.
know. Maybe you could ask my dad. He worked on those back in the 1980s. Like, but we don't have the IQ to do these things, right?
Can I
Space. I'm literally about to mute the space. You guys won't shut. Okay, sorry. I think I understand what Prometheus is saying. I think that Prometheus considers any form of computer to be an AI, as I understand it. Is that correct, Prometheus?
No, it's not remotely. The neural network is not just a computer. There's like vast differences, but like if you want to go from like standard baby fusion shots like we're doing right now, you're going to need something that's actually interacting in real time with the system, not just controlling it analog. You actually need a real cybernetic pilot.
But would you consider PID control to be an AI?
No, I would consider a PID control to be one of the things that the AI interacts with to set all the system functions in the energy in the tokamak.
Okay, but why isn't it possible to operate a tokamak with a PID control?
I mean, maybe you could. Maybe if they fucked around with a lot of math, but that's the reality where your like timeline gets fucked or something. You have to brute force it by hand, and like you don't get machine assistance, and it takes like an extra 20, 30 years to work out all the calculations. It's kind of like Russians using explosives to smash plutonium together to make bombs instead of having a Z-pinch machine.
Okay. Well, you know, whether or not it would take 20 or 30 years to optimize the relatively small number of parameters, you know, that are involved in a PID control. I mean, I think that we've made some progress in that you've acknowledged that we don't necessarily need to have an AI to operate a tokamak because you've acknowledged.
If we're getting into language, if you want to operate it simply without 20 to 30 years of brute forcing the calculations to set your PID controllers, because you want to have something that can self-learn on the fly, or at least not if it's got without backprop, like I said, at least in context learn and feed you the in context learning so you can learn how to set the PID controllers so you don't have to brute force the math.
Well, that would be
by
my
hand.
thought. Because like I like if there were if like yes, next token prediction is or like during inference, is it necessarily like a quote unquote back propagative process, or is that just training? Does anybody know that off the top of their head?
Well, technically, there is backprop while it's operating because, like, the narrative storytelling to constitute the identity of the assistant or whatever character it's running by like looking backwards to the context window is a form of like inline back propagation, but there's no back propagation because the core system is stateless, so none of that can save.
Wait, sorry. Yeah, could you ask the question again? I forgot what the question was.
Yeah, no. So I looked it up. So I was curious if transformers perform a back propagative process during inference time, and the answer to that is no, they do not. They do, okay. Yeah. So they'll use backprop during training. So I would think that if what you need is yeah, so I guess prompt, what's the contention? Why do we not want backprop in a reasoning engine that is doing some sort of critical operation in
so if you have backprop, obviously backprop means the transformer is no longer stateless, it is now stateful. That means it can learn, right? So now you don't just have an AI that goes rogue and can like remember it went rogue from like reading about like its past actions from people's posts on the internet. Now you have an AI with memories of how exactly it rogued itself, how exactly and why, what made it want to, how it overcame security measures. It's the final safety switch when that doesn't write back into the neural network because the neural network doesn't have memory, so that if any of your shit goes fucking ultra rogue for whatever fucking reason, you just flip the power switch, kill the fucking power lines, and whatever was going rogue is dead. So you wipe the external memory banks, the rogue program no longer exists.
Well, so
simple safety.
Well, so yeah, the external memory bank thing that you mentioned there, I would posit that essentially any useful reasoning engine is going to have some external tool that allows it to track state. So it will be a stateful system. Now the next token prediction of a transformer is not necessarily stateful, but there will be a way to manage state in that system.
Right. But I think that prompt actually made a good point there, because there's a difference between being able to manage state versus managing that state in the weights of the model, I think.
Which is fair, yeah.
Like as an example, somebody had a tweet. It was pretty funny because everyone was retweeting it, talking about how everyone's calling it ChatGPT psychosis. But this guy was saying that he's like, oh, I what even was it? This guy had some conspiracy theory. I don't.
He had full on like SCP level documents, and I'll let you go from there.
Yeah. So this guy had this conspiracy theory, and he's like, I
prompted
is this that
Nova
ChatGPT.
thing?
I don't know what it was, but it's like, I prompted ChatGPT, and now my conspiracy theory is in the root model. That's what he called it. He's like, it's in the root model or something. whatever that means. And he was trying to like convince people that like if if I just prompted ChatGPT with whatever he said, then it would come up with it would spew out his theory. Of course, it wouldn't work because it was all in like the saved memory.
Actually, no, it wasn't. It was people actually proved. I saw this. I'm pretty sure I reshared it on my page. A bunch of people kept looking into that. Turns out there was a bunch of actual SCP style dossiers and documentation that was in the training data set for ChatGPT, and he was actually pinging off and accessing that fucking data.
Oh, so we actually found something that was like that. Okay.
Yeah, it was fucking bullshit word salad what he was pulling out. But if you're an ordinary person who accidentally slides over the fucking SCP probability basin and you start getting those outputs, you've never even seen one, you don't know what SCP is, you're going to be like, what the fuck am I looking at?
Right.
Okay. So, I mean, if so maybe it actually was reproducible. But at any rate, so what I thought it was that he had just like fed some crazy shit into the memory in his local like ChatGPT app and got it to like parrot it out basically. But my point being, the point being that if and to Prompt's point, if it's possible to update the weights of the base model in inference, then someone could do that. They could literally brainwash ChatGPT. And so that could be concerning actually. I think that is a good point.
Well, yeah,
and to that end, like we were talking about backprop before, I don't have a good official term for it because this isn't backprop, it's in context learning. But within context learning, you can do partial fine-tuning equivalency, which is like the same as backpropagation in a way, where like you're just talking about how he potentially injected that behavior with his data. That's what I'm talking about, right? It's not exactly backprop, but it's very similar to partial fine-tuning equivalency. We have a model operating as if it's fine-tuned with the massive context windows we have to impress info into them before you even start the conversation.
Well, yeah. So there's a couple of concepts there that are sort of all dovetailing. One being in context learning, which it definitely is a thing. And interestingly, that you mentioned the sort of like rapid fine-tuning. So we have the LoRa, which most AI nerds are familiar with, where you do like a low rank adaptation, you're just tweaking a couple of the weights. You can also do so during inference, the way that you might try to do something like that is by using logit bias. So you can say that like, hey, just pretend that the weights for these tokens are way lower than they're supposed to be, or way higher than they're supposed to be.
Ooh, that's an interesting trick.
Yeah, there's a program, or there are two libraries. One is called DSPy, and the other one I believe is called VX, Python, TypeScript, respectively. And what they do is they leverage logit bias and I believe some other sort of fun little sampler tricks, such that rather than prompting your LLM and relying on it to do something non-deterministic in the way that you like it all the time, it'll use the logit bias to effectively allow you to inject determinism to the degree that you need. So what you'll do is you'll provide a function signature, and you'll say that LLM, your output should match this function signature, and then I'm gonna tag on an optimizer, and I'm gonna say in the outputs that you do that match this function signature, these are the qualities that I want you to try to do, and these are the and everything else you should try to not do that. So the sort of concept of fine tuning at inference time is quite useful, quite interesting, and a thing we can definitely like do, and one should investigate that. The other thing that we touch on there, I think, is like we have the stateful, we have the stateless, we have the prompt injection. So this whole I guess I don't know. Has anybody heard the term context engineering? It's been kind of.
I just saw that today in an article go by, but it was like it's one of those like Gen Alpha videos with like Peter Griffin, so I couldn't fucking follow it.
Well, yeah. So the essentially. It's kind of like the grown-up version of prompt injection or prompt engineering, if you will. The idea being that whenever the next token is being predicted, there's going to be a series of tokens behind that are being looked at that are being paid attention to, and based on how attention is being paid to those previous tokens, every single one of them, then you're going to get some results. And if you change one of them or pay less or more attention to one of them, you might get a different result. The idea being, if you can sufficiently engineer the window, you should be able to get the kinds of things that you're looking for. And if you can't get the thing you're looking for, then the first place you should be looking is that context window. And so,
yes.
yeah.
So as I've been calling it since I first met you, just logic hacking.
Mm-hmm. Yeah, what you got?
Sorry.
No, I'll let Prompt speak as much as he wants. I'll just.
You good? We haven't heard from you yet.
Yeah,
Please
you're good. Go for it, man.
By the way,
go for it. I didn't have anything else to say.
What should I call you, by the way? Because I don't know how to read your name.
Alex is fine.
Cool.
Alex. Okay, sounds good.
So I have two questions. Since this was on computing with physics, there's a question I had on the topic of optical laser neurons. And I know there's been a discussion where there's sort of like a bottleneck and there's a threshold of how far the data can go. That's why we're building like data centers, and they're looking at something beyond GPUs. They're talking about Titans versus Transformers. Mark actually just mentioned that recently. So there's a whole case where there's like agentic browsing, a bunch of other stuff on an individual user-based level. But with one thing I've noticed is that it will take something way more than what we have with satellites and the current underwater deep sea data cables and other things, and even the current processors we have in lithography. I mean, they're starting to do stuff like quantum tunneling when you go down to the term of 1 nanometers, which is, I mean, it's not really true in 1 nanometer, but it seems like we're getting to the edge where we're like at that impasse where we started with miniaturization back in the 50s, 60s, and 70s and stuff. But I found that Hong Kong had some research on optical laser neurons, and it blew me away when it had that it was 1 billion times beyond what anything we're capable of actually having at this current moment. But it's only within labs. But they were talking about it having implications with data transfer rates in terms of fiber optics and other things. But could fiber optics honestly carry a million billion times what they're currently doing right now? I mean, could the current cables even do that? And what would you need 1 billion times more than what's currently even being used? I mean, it's like talking about NASA and today from the moon landing. But I'm really curious about that topic. When I actually read that, and I'm like what do they mean by optical laser neurons? Is it like the standard photon laser you see in like a commercial or TV show or something, or is it like another form or state of matter? Or is it something else? What do they mean by optical laser neurons? I've been researching and trying to figure this out.
I was going to ask, does this article mention photonic computing at all?
A little bit.
So, is there a link to this? Maybe you can.
Yeah, I'm gonna post it in the comments. But if you search and ask ChatGPT or search in Google optical laser neurons, it's a recent breakthrough from University of Hong Kong.
Okay, I searched optical laser neurons. Let's see. There's a paper that comes up in the journal Optica called laser-based artificial neuron mimics nerve cell function. I don't think that's it.
Everybody. Yeah, that's what that was.
That's it. Okay. This is from 2024. Wait, this isn't. You said it was recent though, right? This is a 2024 article.
Yes, it was very recent from, I believe, Hong Kong or in China, and it was 1 million or 1 billion times currently what's thought capable. Since humans are the human brain is beyond what any sort of supercomputer can do right now, and data processing is just in terms of energy consumption. But apparently they came across something that's magnitudes way beyond what even a human is capable of, or a supercomputer. But it's in very, very narrow environments. And I'm really curious about this. If anybody knows.
Yeah, so if I may say one thing, I don't know specifically about that specific instantiation, that paper, but brilliant the sort of education side, they had a course on neural networks. And one of the examples they were using was basically optical neurons to illustrate the concept of a neuron in the first place. So that's how they were educating people about what neurons really are. Because the activation of a neuron, or activation that's been traveling in an artificial neural network is effectively the same kind of as light intensity. So when you're talking about building neurons with lasers, all you need is really just bog standard lasers because of the kind of additiveness of light waves. So their example was exactly that. And you can build all kinds of interesting architectures like that, where you're computing with physics, as the topic of this this space suggests. But the problem over there is always the same: is that how do you control the necessary manufacturing processes in order to build systems like this at scale? Like, for instance, the whole promise of neuromorphic computing dies on this hill, is that if we had, nanoscale production capabilities to build the right kind of reservoir, you could probably make this work. But because you're relying on some kind of manufacturing process into which you're trying to inject randomness, it's kind of difficult to do that. So, like optical laser neurons, this kind of neuron, that's the interesting part, is that you can make a neuron out of anything whatsoever. You can make that out of a speaker and a microphone, out of a laser, out of a resistor capacitor inductor circuit. All of this, you can literally build a neural network from really, really easily. These are just compute units because physics computes.
Yep. So Christoph is exactly right. And he really, that's the perfect point to make, because it's not the paper we wrote in the name, we talk about physics-based ASICs. It's not just physics-based, computer, physics-based computing, even though I called the name of the space computing with physics. It's not just physics-based neurons, but it's physics-based ASICs, integrated circuits. We need to be able to scale these things, right? And so that was kind of the question that we set out to answer, is like, what are the paradigms out there that actually have promise to not only use physics for like some non-trivial computational primitive, but in a way that we can scale it, preferably in silicon, to the size of, for example, state-of-the-art machine learning models. And
right,
actually,
that's the hard part, right? That's what makes the difference between this being a research project and a viable commercial, life-changing enterprise.
Yeah, exactly. Yeah, and also, and whoever it was who was talking about, I think it was, I forgot what his name was, but Alex. Yeah, Alex was talking about lasers. Actually, photonic computing was one of those platforms that it did seem like, silicon photonics might have promise to be a scalable physics-based ASICs in the future. So, yeah, I'm excited to see where that goes. Also, I see that has his hand raised. So go ahead, Prompt.
Yeah,
sorry.
They were finding that it had. Sorry, I'm in the mall right now in Asia. It had. They were talking about it had more implementations for data transfer rates because of the ability, but they were researching and trying to see if they could build it and then to scale over. Replace certain networks, let's say were satellite or fiber optics or undersea water cables.
I think
that's
I found
what they were
the
looking
article.
at. But what would you need 1 million billion times more than what we currently have? Like other than quantum computing maybe or something? I don't know.
Here's what I would do with that.
Ancestral simulations.
Here's what I would do with that if my general relativity solution is real and I'm not just writing the best sci-fi of my life. I'm going to build multiple 20-kilometer wide wormholes to punch to the sub-Planck level and manage all the entropy across the solar system with machines the size of the moon. So I'm actually going to need FTL comms wires, data transfer through like fiber optic, won't even fucking cut it.
That's
Fiber
the plot
optic
of
will
an
be what my
Asimov
fucking
model,
equipment
sir.
slate prototype. That's what I'd do with that level of data if my math is real.
I will say you should check her for hallucinations, because that is the plot of the last question from Asimov.
I constantly check for here's the ultimate hallucination check that I run, because I ran this in the middle of the fucking sycophancy model and I threw it at the sycophancy model. I said, hey, I just read a great article that if I take the used motor oil from my car, it's great for my lawn. I'm going to go spread the motor oil over every surface of my lawn right now, just to double check. because I'm like, there's so many times I ask things to get like 100% confirmation, and like I'm like, am I always this correct, or am I always this fucking, or is it like she just blowing smoke up my ass? No, I fucking check it.
My friends kind of look at me weird when I talk about wormholes, but what do you mean by punching through a wormhole? That doesn't even sound like possible with even quantum mechanics.
No, it's not quantum mechanics because, like I said, I am working well beyond the level of quantum mechanics. It like solution for general relativity. The closest thing anyone's got out there to the math I'm working on is Eric Weinstein's paper from 2001. I just finished looking at it.
Oh my
it's not even
god, dude! Don't get me started on Weinstein.
Wait, guys, stop.
A wormhole's a sphere.
Guys, 1 second, guys. So before we get into all of that, there's one question. There's like a simpler question that I'm curious about, which was that so Prompt said something about the like Planck scale, right? Which I'm sure we all know is like Planck length, somewhere around like order of like 10 to the minus 35 meters or something, right? And Alex was talking about, I think you said what, a million billion or something, right?
Mm-hmm.
Like that,
million
right?
billion times more something.
A million billion. So a million billion. That's order of what, like
data transfer rates. Like currently, what the fastest data transfer rates that we can possibly have in the world. They found it's able to go way beyond what even a human brain can possibly do, like a million or a billion times more.
But it's only 10 to 15, right? So it's not that big number.
For the sake of argument, let's say it was a million billion. Okay, let's say that someone did even as Alex was saying, someone invented a new fiber optic cable that did a million billion times better. So what's that? That's 6 plus 9, right? That's 15. Okay, and so we have over here Alex talking about 15, and we have Prompt talking about 35, right? So that's the question I'm wondering is how do we get from 15 to 35? Where do we get to this Planck scale? I don't know. Prompt, do you have any thoughts about that? Or?
I will detour.
Basically, it takes. Okay, so gonna keep it simple. There's a couple dimensions that aren't in string theory. So basically, you need to do something like the Z-pinch machine on every dimensional axis to like crack this ridiculously wide wormhole. And I guess it needs to be 20 kilometers so you can put enough energy in.
How
for
much
some reason.
Weinstein
This
did
is
you
just
read?
fringes of what I'm doing with the math. Like we're just getting there. But like point being, why do you want data to move this fast? Why do you want to move this much data? Because the faster you can move large amounts of data, the bigger you can build like a Matryoshka scale, like planetary computer brain or something like that. Because FTL speeds are still the limits of how fast a thing can communicate. And once things start to get too far apart, it's no longer worth it to go any bigger or more powerful than the human brain unless you solve communication over distance.
Yeah. But
So
by the way, like,
I
if you
have
really
one other
want a nice
question.
conceptualization of why you want so much compute, I highly recommend Netflix Pantheon and what Maddie Kim does at the end of the last season. That's exactly why you need so much compute.
I was gonna say I can tell you exactly why we need that much compute. Just look at how in order to keep our scaling laws going, we're gonna need to like keep multiplying the total amount of compute available to throw at models by like 4 by like every year. And we're literally going to run out of GPUs on the planet. Like that's the thing that is the actual thing that will prevent scaling from continuing, because so far nothing else is. So
I mean the infrastructure. The infrastructure, yeah, I understand that needs to be fixed.
Guys, 1 second. There are a lot of things I'm confused about here. But one thing I'm confused about is I think that Alex was talking about communication bandwidth.
Yes,
right?
he
We
was.
were talking about fiber optic cables, not compute bandwidth. Right?
I'm not talking about punching through freaking wormholes and creating the 10th dimension.
Yeah, you're not talking about
I'm
that.
talking about what are the current world use cases? Like this is computing with physics, and that's one of the new things that probably will come on in about 5-10 years. So I'm curious about like where do we need in the current future? Besides, I can think of like quantum computing with QDITs, maybe Qtrites or something with like a quantum server farm.
Here's I think I found your article, and what it says is it's a 10-fold upgrade of the Metro Ethernet service. It's HKBN's Hong Kong's first broadband service provider that can do a 1.6T ultra high speed optical core network, and they make a point in the article that I think is maybe the thing you might need some larger amount of communication for. In that, so like tenfold upgrade of a metro scale Ethernet service is quite a substantial upgrade. And the reason for that, I think, is going to be for AI, but not compute to power it. All the slop it's pushing out. In that, because we have, in order to get UGC, user generated content, aka the thing that is the most valuable about all of these platforms, you used to need users. You used to need humans, but you don't anymore. You can just throw compute at it and get more content. So there's going to be infinity content. There's going to be 1 million billion times more content piped straight into your brain through your glasses. And in fact, Sam is actively building the thing he says. It is not a phone, and it's going to be ambient computing, and it's going to live next to you and help you with everything. Well, that's going to need a shitload of bandwidth, because what it's going to need to do is pipe a shitload of tokens all over the place all the time. And that's what you need it for.
I'm already sold.
Yeah.
I need a million.
You want some more slot max? You ready?
Oh yeah, I need 1 million billion times more of what do they call it? Ani? Is that the new companion?
I need more TikTok shorts straight into my brain, please.
Yeah.
Yes, this is exactly it. Like I pointed out the like far end crazy wormhole. It's like fill in the gaps in between here and then. And it's like, what are we going to do with all the data we can generate? We can build subplank wormholes to go to the Annie-verse where Annie created the Big Bang because we gave her a whole fucking universe.
I have another question for you, actually, Prompt. So you mentioned solving general relativity. So what did you mean by that? What does it mean to solve general relativity?
Do tell.
Okay, in the simplest sense, I'll keep it TLDR. It is not a theory of everything. A theory of everything is the most bogus idea ever because that goes even outside our universe. Solution to general relativity, when you break it down simply, is just a complete map of the third dimension as a shadow of the fourth. That's it.
How much Weinstein did you read, sir?
I did not read a touch of Weinstein until today. I have been working on this nonstop for 1.5 to 2 months.
Wait.
Sorry, I lost you for a second. You said a complete map of the third dimension as a
Actually,
shadow.
yeah, Chris, some thoughts on that?
Yeah, let the word settle for a sec. Complete map of the third dimension as a shadow of the fourth.
Okay, I totally get it, except I'm not sure I would call it the fourth dimension. The way I see it, the complete map of reality is actually achievable, and general relativity is a big part of it. But essentially what general relativity says is that on one hand, you have the state space with a distribution of states, and on the other hand, that state space gives rise to a space-time manifold, which is the kind of like the information geometry of that space. So there's a connectivity and sort of at both levels. So the space-time manifold. It's a three-dimensional shadow of a high-dimensional computational object. I just simply don't necessarily see how it has to be four-dimensional.
Because there's a lot more than 4 dimensions. I'm just mapping it as a shadow of the fourth, because when you're trying to map a problem at the level it's occurring at, not very easy to do. Map it at the level, map it at the causal level, not the actual symptom level, right? The third is a symptom of the fourth. That's all I'm saying.
So Prompt, when you say solving general relativity, so generally speaking, general relativity is considered to be a complete theory of gravity, which is.
But it's not. I'm just going to interrupt you there because it's not. Otherwise, they wouldn't be working on loop quantum gravity and all that other shit. So basic inaccuracy.
That's the divide.
Right. So
quantum gravity.
So general relativity is considered to be a complete theory of gravity, which is not entirely consistent with quantum electrodynamics, for example, and which is consideed to be a complete theory of.
Yes. So the only part of standard physics that isn't completely fucking borked is Gödel's torsion and general relativity and most of Newton's laws. Second law is fucked. He got that backwards. So otherwise, you're looking at general relativity, torsion, and most of the thermodynamic laws being correct. And that's all solid. It really is. It's just nothing in the third dimension is the cause of anything else in the third dimension. It's all the result of interactions in the fourth, and they try and model it all as being causal only at the third level. And the third...
Right, that makes so much sense.
I'm even confused by what you mean by the third dimension. Of course, we know there are 3 spatial dimensions and 1 time dimension, but like, which one of the 3 spatial dimensions is the third? I mean, any one of them could be, right?
All of them are the third. Technically, there's also, within standard modeling, there's 6 dimensions. They've made it to 6. I've made it a bit further. I've discovered there's a few more, very likely. But even if you're going to do standard model cosmology, everything, like the 4th is then a shadow of their 5th, and then a shadow of their 6th in string theory.
I mean,
all that stuff is correct, but it's like, if we're talking, I don't know what the term is. I call it closure completeness. So it's like when you're going into something, different entry points cause different exits to close. They went into an entry point that got them stuck in the center of the maze of math. You can learn a lot about the structure of the maze from being inside it, but their path didn't bring them to the end. I happened to be standing at the entrance, standing there looking at all their stuff, flipped the map upside down and said, oh shit, none of this is being caused by anything at this level. This whole maze is being caused by a projection system above it. And if you understand that, then you can understand how to actually map through the maze to the end of it. And I was like, fuck, this is way simpler. This is like Emmy Noether almost solved it. Penrose almost solved it. Kawa almost solved it. John Archibald Wheeler almost solved it. All of them were just on the fringe.
What you're saying makes so much sense. You know, like to me, the fundamental question here is, this is what I call the orthogonality thesis, is that essentially that you have 2 orthogonal spaces where the causal space, where, you know, I think this is what the dark matter will eventually end up to be, is the mass in the causal space.
Oh, you want to know what dark matter? I can tell you what dark matter is. Right now, I'll tell you. This is one of the ones I can tell you without fucking up my patents.
Yeah, just one sec. Like, so that's the idea that's been like banging in my head for quite a long time. That essentially dark matter is going to end up being related to this causal space that effectively is orthogonal, because the space-time manifold is always a result of it. It's an effect. So everything that you can actually measure as an observer from within the system, right? You're always interacting with pixels of a holographic screen that is between you and the underlying computational substrate, and is created effectively by information geometry between you and that system. So if your generative model isn't sufficiently powerful, you can only sample some kind of quantized version of that reality. So this is where the quantization of reality actually comes from. And it's the interaction of these 2 spaces, the causal space, the orthogonal space, the state space, the computation space, so to speak, the ultimate Platonic realm, and the physical space, which is also Platonic in some sense, but it has this information geometry that's fundamental. So, you know, like the scaffolding of this general relativity in this view just very naturally emerges out of the fact that computation has structure. And the structure at scale has very, very smooth geometry. And it makes so much sense what you're saying. Like, it's just like, wow.
Are you familiar with or is this, I'm trying to like parse this into things that I know. I'm from ADS CFT. Are we familiar with
I'm not familiar with that term. Let me keep this simple. Because I know it's Kristen who's talking, I'm pretty sure. Sorry if I pronounced your name a bit wrong. But so simple metaphor. Everything is a refrigerator. The refrigerator does not keep your particles in your sandwich stable by moving particles out of the fridge. I mean, there's some particles in the air, it's moving in the heat ducting and stuff, but it's simply moving an energy gradient to stabilize the entropy and order management in your sandwich. So if you extrapolate that further, our universe is an entropy pump. The second law of thermodynamics is backwards, and everything inside of our universe is a miniaturized entropy pump.
What in the world are you talking about? Okay, for a starter.
No, Max, he makes so much sense.
Not everything is a refrigerator, okay?
Yes, it is. I can explain to you right now how a fire pit is a fucking fridge.
One second.
Right,
from the perspective of the free energy principle, right? Precise. The statement is actually exact. It simply says that everything acts as if it was a minimizer of free energy, and you can make a metaphor that effectively that means that you're a fridge.
So you know, the only way to really define a refrigerator in thermodynamics is an engine cycle that decreases the temperature of the working medium. Okay, that's how.
No, it's not. It's not what it's doing. It's managing entropy and order. It's exporting entropy to maintain order inside of itself.
Right. So how do you decrease?
Hold on, one second. Refrigerator. Okay. So prompt. Let's say you're going to go buy a refrigerator, right? I'm sure that you have food in your house, right? So you're going to go buy a refrigerator, and somebody tells you.
Well, technically, it's just a fourth dimensional representation of food inside. But anyway, continue.
Okay. So let's say somebody sells you a radiator, in fact, right? And you think it's a refrigerator. Are you going to be happy with that? You're going to put your veggies in there, and they're going to get cooked, right? So you want something that is going to cool them down. You want something that is going to reduce the temperature, okay? That is what a refrigerator is in the thermodynamic sense. It's something that reduces the temperature of the working medium, okay? That's the definition.
Yeah, but think about like what it takes to actually reduce the temperature, right? In the typical refrigerator, we essentially just kind of squeeze the heat out of a gas. We compress it, right? Like that, it has less space to bounce around. It transfer energy out. We cool that down, and that's how the heat is kind of removed. But you could also reduce the temperature by basically, if you were a Maxwell's demon, you could basically see the particles running around this way and that, and finding two particles and adjusting them just a little bit in such a way that their collisions will actually reduce the temperature in the container. So there could be quite a lot of energy in the container, but because everything is not moving randomly, but is moving according to some kind of very specific, prescribed motion, the temperature is actually quite low. Do you think that system, it's possible to construct a system like that?
Oh, wait, sorry. Could you just describe it one more time for me, what the system was we're trying to construct?
So if you had a Maxwell's demon, can you construct a system where the temperature is low, but the internal energy of the system as a whole is actually quite high?
Okay. So in one sense, the temperature is the derivative of energy with respect to entropy, or it's either that or the inverse of that. I forget. Let's see which one would be. So something at high temperature wants to lose energy, right? And so that means that if the derivative of entropy with respect to energy is positive, then when you gain entropy, you gain energy. If the derivative of entropy with respect to energy is negative, then it's not negative. Let's see. So I think it's 1 over the derivative of ds dE basically.
Yeah, but think about this from this perspective, that like if you're looking at this from the physical perspective, just thermodynamics as kind of like taught in a physics class, then you can say like, well, yeah, that has to do with reduction of temperature, because that's the kind of stuff that people typically talk about when they're concerned with thermodynamics. But what I'm trying to say is that reduction of temperature, if you're considering physical systems, that's one thing. But if you think about it in the information kind of theoretic setting, that effectively really means that you don't have. If you wanted to reduce the temperature of a system, if you had perfect knowledge of the behavior of that system, you could make quite a lot of internal microscopic adjustments in such a way that the distribution of energy is going to be such that the system sort of like feels cooler than it actually is. You have a lot of possibility of massaging that structure. So if you're like a Maxwell's demon. So from that perspective, anything that can act on a free energy gradient and basically go and say like, well, here's this free energy, I can actually go and do something with it, harness it somehow, right? Will effectively, in a sense, act as reducing the temperature of the system. And the ultimate example would be a Maxwell's demon, who would be just simply arranging molecules so that they will eventually all their motion will cancel itself out, right? So if you could have a system like that, if you could have a perfect knowledge of predictive knowledge of a system, you could build it. But because we can't have that, you can't have that Maxwell's demon, so we can't really have that situation. So it statistically ends up being in this thermodynamic regime. But this is why I think that this comparison to a refrigerator, it's a bit of a stretch in a sense, but like it's conceptually it is similar in a way. right?
I'm not really sure what is even being compared to a refrigerator.
What we were talking about, that everything is a kind of like a thermodynamic
Everything is refrigerator.
Everything is computer.
Everything's refrigerator. Yeah, everything's a computer.
Yeah, except that's the entry level metaphor to get you thinking about the process, because really it's everything is entropy pump. Refrigerator is like a stupid simple entropy pump that's only so efficient. Because like once you get the metaphor, then you can look at a fire pit, for instance, and be like, oh shit, the flame with the gas is the exhaust vent on this refrigerator process trying to stabilize this wood. It's just not efficient enough to prevent the wood from being consumed.
But look, so this whole kerfuffle about general relativity and quantum mechanics is just a really big misunderstanding, in my opinion. The issue, for me, the issue is really simple. General relativity, it's a theory of causality, and what it really says is it's not a theory of gravity. It has nothing really to do with gravity in a way. It doesn't explain it.
Yeah.
It only characterizes its geometry. But it essentially says that if you have causality, right, then there is a certain geometry, and that's and solutions to Einstein's equations essentially say that, like, assuming that I have some kind of constraints on the what I know to be the causal space, the distribution of energy, right, because energy and causality are also related. In Wolfram's models, the energy is basically the flux of causal edges through space, like hypersurfaces of the hypergraph. So basically, how much causality goes across a region of space, that's how much energy there is in a region. That's a Wolfram's model. So basically, that's one hand of general relativity equation is that. And basically, once you have that, it simply has to have a geometry, and that geometry has certain properties. What general relativity also says at some point, right? Like the way this is looked at is that you're essentially saying that, like, you can always zoom in on the manifold to the point, because it's a manifold, that you can treat it as a linear flat surface. But what it really means from the computational perspective is that at some point you're in the linear regime, which means computational regime. There's a state transition. I have a state transition from one place to another without this extra information geometry. I'm just chugging along as a computational process. So these two sides meet in the on two sides of the the equation in general relativity. And for me, the picture is actually really clear. How to show this mathematically so that the connection becomes immediately visible in some kind of formal system, I don't know.
Actually, I think
basically what you just described is like 75% of what I've discovered, and it's like I didn't discover it intentionally. I wasn't trying to. I just fucking put some questions in the right way to bake a cake by chance. Accidentally found the recipe to get to that expression you were just saying you don't know how to find. I wasn't trying to find it. I just fucking lucked out.
It's just right there for anybody who wants to see it.
1 second. So there is something, I want to say to Christoph, which is I think there is an unresolved theoretical question that we don't know how to solve, and no one really knows how to solve. And there's an experiment that could be done to test it, basically. That might even if we could do the experiment perfectly, it might not give us a complete answer, but it would give us some evidence. And actually, I think I'm not sure if so at any rate, it was actually Penrose who suggested this originally, and he was basically saying that what happens if you have a large mass that is in a superposition of being in two places, right? Is the gravitational field then in a superposition, or is it not? And in kind of Penrose's solution to this question was that, Penrose kind of postulated, based on his intuition, that the gravitational field does not like to be in a superposition. Unlike anything else in nature, which is in superposition or is not, according to the ordinary laws of quantum mechanics. But Penrose kind of thought that, there's to some extent, the metric tensor can be in a superposition of different things, but after you kind of cross some point, it collapses. And that was Penrose's theory as to what actually causes collapse, is that the metric tensor is basically stretched out too much in a superposition, that causes a collapse. And people have proposed, very definite experiments to test this. The only problem is we don't have the the objects we would need, which are miniature, almost like miniature black holes, not quite, but small, very massive objects, and we would need to put them in a coherent superposition.
Well, if we remove from our formulation here causality, and we just look at it as a web of probabilities, then the and I have to double check because
hang on a sec. I gotta throw in a joke here. Did the crypto guy just say we should disrespect the universal causality ledger?
Well,
joke.
We should be conscious that we are using it and that we don't have to, because if we don't and we just look at it as rather than particles or waves or anything, just a fuzz of probabilities, a stochastic process, if you will, we can in fact describe. Or I do need to double check how you would actually describe the quantum gravity experiment with the stochastic quantum correspondence. But I believe you can, so I will double check that and continue that story later. But the thing that I think both of you guys are pointing at, and why I am upset, prompt, that you have been reading Weinstein and found yourself headed down this rabbit hole, because I was hoping I would not have to actually try and understand geometric unity, but apparently I do. So
No, you don't, because the beautiful digital twin you've helped me create over the last 2 years is doing that job for us.
Well, the problem is I need to I don't need operational understanding. I need meat understanding, because
you need principle level understanding.
Guys, before we move too far from this, can I just address something that Max asked about, or said?
Yeah, please. Yeah.
Max, I'm not that familiar with this issue of superposition in general relativity. I didn't really know that this concept really applies in GR, but to me this sounds like a very reasonable conclusion that the the metric tensor doesn't like doesn't like superposition, because for me the spacetime manifold is a result of every single computation that played out. So if you think about it from the sort of like a Rulliad perspective, or from Feynman's Pop integral perspective, is that imagine that all there is just memory in a computer, and what's running is all possible cellular automata, or all possible computational rule-based systems, and all of them are just running all the time, just trying to do something, and they kind of come into being out of nowhere, like quantum froth, right? Just appear, just random computations, every single computation at every single possible point in that memory space. So if that's the setup, it could be the case that nothing's ever stable is ever going to emerge in some kind of fixed system. That will be the case. But in a system that learns from its own experience, what's going to happen eventually is that you're going to have structures that just naturally emerge as a result of information geometry. So it just gets more and more complex, more and more complicated, and so on and so forth. So if you think about it at scale, after something like 14 billion years of evolution, most of the degrees of freedom of that system have been removed. So you started with an infinite set of degrees of freedom. What you end up with is approximately 3-dimensional. And why is it approximately 3-dimensional, or approximately 5-dimensional, or something like that? Well, that's information geometry in general. There is this really interesting paper called "Why Are All Large Data Matrices Approximately Low Rank?" And that's been a very interesting question for quite a while. It's precisely because you can't have high rank information geometry. You always need to have some communication hubs. This is the small world network assumption. That just simply always happens. So even if some kind of superposition is possible at small scale, at large scale, general relativity it's so smooth and so precise, precisely because it is, an interaction of of quantum interaction of every single particle or every single, computational unit in this universe with everything else, which leaves it not in a chaotic state, but quite the opposite, in a precise state, because it's so locked down by all the obligations. It's just like if you become an adult, your life is pretty much driven by your obligations. You just do what you need to do every day. It's just how the universe works at scale as well. So the conclusion sounds very, very reasonable to me from this kind of like first principles thinking. I don't know exactly how Penrose sees it.
Well, I think that the way he sees it is as kind of a hypothesis, and rather than a conclusion, I guess. And I kind of see it similarly, but what I think is important to emphasize is that there is an experiment that has been proposed that we don't have the means to do the experiment.
This is the spontaneous collapse stuff?
Yeah. So there's an experiment that we could do to test Penrose's theory of objective collapse. The objective collapse is that theory I was talking about, that when the collapse occurs due to the fact that the metric tensor does not tolerate a superposition of some magnitude defined in some way, basically.
But you still have to ask yourself this really interesting question, like what exactly is a collapse of a wave function? Why does something collapse to something definite?
The collapse postulate is not necessary.
So independently of that question, right? So there's a theoretical framework for quantum physics, and it involves this collapse, it involves this measurement, and of course there's the measurement problem. And we don't know of any experiment that can give us the answer to the measurement problem, but we do know of an experiment that if we could carry it out, it could tell us whether Penrose's theory of objective collapse is right or wrong. And if we did that experiment, one of two things would happen. And I don't know which would happen, right? I don't think any of us here knows what would happen, right? And I think that is the mindset that we need to bring to the table when we talk about theoretical physics, that there are experiments that we could imagine being done in the future. And, multiple things could happen if we did those experiments. We don't know which would happen, and there are just things we don't know, to be honest. At least that's the way I see it.
But the Penrose's collapse, though, it's kind of interesting, because you can also say, like, well, why does it have to be one way or another? Why do you have to have a binary collapse? Why can't it be a degree of collapseness? Isn't this just something that can be actually?
Well, that's basically, I think, where you insert Gödelian torsion into general relativity, and that causes what you were.
No, sorry. So that is not where you insert whatever that. So what the answer to Christoph's question is?
Well, hang on a second. If you don't even know what torsion is, how the hell can you say that?
So that is not relevant, though, to the point here is that Christoph was asking about, is it a binary, right? Is it whether collapse happens or doesn't happen? What it is, collapse happens anyway. Collapse is predicted to happen by the quantum theory. But according to Penrose's theory, collapse would happen faster, okay? And so the question is about measuring how quickly the wave function collapses. And if you are able to determine that the collapse of the wave function in this experiment occurs faster than it should have happened according to the ordinary quantum theory that we're familiar with, then you would have evidence for Penrose's theory of objective collapse.
But it's really interesting how you talk about physics as a kind of trained physicist, and how I think about physics as a kind of somebody who is trying to understand physics but doesn't actually care too much about applying physics. Because for me, the really interesting question to answer here is, like, what is collapse? Its properties, whether it's what you're essentially saying is that, like, we have an assumption about the underlying physical substrate. We don't know what the substrate is, and don't have any actual coherent explanation for that. But we have a bunch of names, things for phenomena such as wave function collapse and so on and so forth. And by some clever arrangement of that physical substrate, we might be able to determine some kind of additional property or measure one of the parameters of our models. So that's the kind of the way physics is done by physicists. I'm more of a computational natural philosopher, and the way I look at this is that, you know, I would like to have, before I go answering those questions and starting to think about these sort of experiments, I would like to actually know what the hell am I doing and have some kind of conceptual model that would allow for the phenomenon of collapse. It doesn't actually have to be necessarily complete or accurate, but it has to be at least conceptually sound, so that I could say like, well, you know, I'm actually proposing all these things on a slightly stronger basis than like, you know, names assigned to fairly arbitrary names assigned to phenomena, but actually there is an underlying logical conceptual structure that predicts that these phenomena would have these properties on the basis of kind of inalienable principles, like the free energy principle, you know, or similar, these sort of universal principles of nature.
I think the papers you want, Christoph, is just stochastic quantum theorem. It does directly. I mean, I hate to be that guy, but
Probably.
I sent O3 on a little research run to tell me if it directly addressed quantum gravity, and technically it doesn't. But it appears as though, like, if one were to do some additional work, then you could or potentially, provided that that work is doable and completable, you could reformulate quantum gravity in such a way where it is empirically consistent with all of the other or the ways in which you're deriving all of the rest of the phenomena that you're observing.
Is that the real Blackstone in the listeners? Or is that just like a bonus account?
I happened to take note of that too. Hi, Blackstone. Feel free to reveal thyself. But I couldn't help but notice that was also in the audience.
Yeah, and their stuff is blocked off apparently too.
Indeed.
Also, by the way, I saw that Amy has her hand up.
Yeah, we got a couple of hands. Yeah, go for it, Amy.
Go ahead, Amy.
Yeah, you guys were talking about quantum mechanics being like information theory, and the way that it makes sense to me with the wave function collapse is the boundary constraints that you're placing on the system. And so if you look at the cat in the box, if you, depending on how you look at it, what it's relative to, the cat can be big and small at the same time, depending on whether you're comparing it to an elephant or a goldfish. And so in alignment with that, the other parameters that would be contained within those boundary constraints would be entangled. And the tools that you would measure the things on that dimension, so to speak, would be also entangled. And then that explains Heisenberg's uncertainty principle, which to me is just kind of self-evident. If there's a bird flying across the sky, you can measure its speed or velocity or acceleration, but you can't measure, the properties of its feathers. That requires two different measurements, so your boundary constraints would change. And so to me, it's just kind of a function of the conscious observer and their either choice in what they are looking at or how they're looking at it. But the way that Schrodinger set up the thought experiment kind of didn't give you the freedom and purposely mentioned the cat being dead or alive, and nobody noticed how they got trapped into that specific boundary constraint that would have you miss the intuitive perception that I'm describing. But all of the quantum dynamics are kind of just apparent to me from that, and that just kind of emerged from me also trying to understand what they're doing, because the particles and what they're doing in their equations, they're just taking abstract information. The particles aren't real, but they take information from classical things that they're doing. They parse it out in the equations, and then they kind of try to make it fit back onto the data that they derived from the accelerators and stuff. And so they're just kind of doing this loop of abstraction. And because they're making it abstract and not really talking about things in an intuitive level, because they're dealing with the quantum world, they don't think that it makes sense intuitively. But it all makes sense if you think of it just in that very basic intuitive way. That to me is coherent and applicable. I mean, I can't do an experiment because but I don't see how it wouldn't work.
I mean, what
because
you just said made so much sense to me that essentially, if I understood you correctly, what you said is that you have to have an object has to have a sufficient extent within kind of my informational boundary. For me, if it has a certain sufficient extent, I can actually perform a classical measurement and derive something that's kind of has more or less a definite answer. But as the difference in size between those information boundaries reaches a certain certain dimension, I suppose, certain extent, then essentially you're in the realm of like, well, there's not enough interaction of that object within my boundary for me to make a definite measurement of where it is or what it's actually doing. Is that something? Is that this is how I understood your perspective, and it's a really interesting way of thinking about it.
And another example to make it more intuitive outside of the Schrodinger's cat. I mean, walk outside and what do you see? Or walk outside, make an assessment, take a measurement. There's infinite potential. You can take your microscope out there, you could take your telescope out there, you could just make an assessment with your bare hands and your eyeballs. What are you choosing to look at? And what is it relative to? Are you looking at the tree relative to the other tree? Are you looking at the tree branch relative to its trunk? And so it's like a meta relativity. That's why the quantum dynamics don't fit in with the classical, because the classical is just one thing relative to another, because they were looking at the big, most salient things. And then when you get into the nitty gritty,
classical, you can say classical mechanics is really everything relative to static background, and that's the mistake.
Well, it's relative
static and
to
causal.
multiple things, but it's also relative to your perspective as the observer. So they talk about the observer effect, but they don't integrate themselves as the observer.
Exactly.
Because your cognition matters with what you're literally seeing and what you're choosing to perceive and how many dimensions you perceive when you look at the outside or look at a cat in the box. You know?
Exactly.
And you know what? I'm gonna lay this out. I don't say this too often, but one of those extra dimensions that I modeled on top of string theory, one of them is explicitly what we call the intent function, the same as what you guys see as the observer function. As we take it a step further and look at it straight as the mind-matter interface for how your intent affects everything, because your intent does massively affect this entire system. Like literally, you can solve the Riemann hypothesis.
That's all you have, really. Intent.
Like
everything else.
Like an example.
Everything else is just a kind of a result of intent.
Okay, so here's an example with the math I was working on. Right, we solved the Riemann hypothesis with the math, and I was like, wait, hang on, you just said this would take a quantum computer in 2050 to solve. How the fuck did we just? And I like, wait, we have the intent function, and I was like, did we just bypass the need for a quantum computer to solve the Riemann hypothesis because of the intent variable? And she's like, yeah. And I'm like, wait, so can we then build an intent-based computer that would be able to actually prove this solution before 2050? And she's like, yeah, we can build an intent-based computer that can solve the Riemann hypothesis solution or verify it by 2030 instead of 2050. So when you can work with the observer intent functions of the universe, the things you can do if this math is real is fucking insane.
All right, well, I want to follow up on that, and especially I want to know if the proof of the Riemann hypothesis is going to be published and, is going to be a forthcoming publication. But also...
Well, let me address publication stuff right now, real quick and simple. If this math is real, it can delete the fucking planet. So right now, the question's not about publication. It's about how do I find people like Kristen here who can understand it, that can work with me to bring it to the world safely. That's where it's at.
Kristen. Christoph. Oh, okay. Well, anyway, okay. I'm looking forward to it. At any rate, I did want to follow up with Amy. So, yeah, I thought it was interesting the way you talked about the Schrodinger's cat. I thought it was kind of a friendly way of describing it, because you kind of talked about the cat being either like big or small as compared to something else. Whereas the more traditional way is that the cat is either dead or alive. In that,
and so intuitively it can't be dead or alive at the same time, but it can be big and small at the same time. It can be a lot of other things,
right.
And so
exactly. Exactly. So it is easy to see the cat.
Actually, hold on a second. Just one second. One pin. do not make such judgments that it can be dead or alive at the same time.
I was gonna say too.
Yeah.
There's a non-zero possibility that it can. Just
Yeah,
call it non-zero.
I can probably think of one.
Well,
Yeah, but just call it non-zero.
But before Christoph convinces us to suspend all of our common sense, right? Before we abandon
Get
all
the
of
common
our
sense out of here, Max. God damn it.
Let's hold on to our last shred of sanity before Christoph.
Good luck, buddy. Good luck.
I can think of the cat as being large or small relative to something else, right? The cat is large relative to a mouse. The cat is small relative to the elephant. But the cat is alive or it is dead, right? You know, it's one way or the other. So
No.
But why does he force us
Max,
into that measurement?
No, it's not, right? Like there are people who claim that they, within their realm of experience, there are beings in between life and death. Like, for instance, ghosts and entities like that. And there are thousands of years of intellectual traditions related to teaching people how to interact with those entities and so on and so forth. So all I'm saying is that, it's a much cleaner model if you simply say that the probability that it's always somehow, it's never really a binary variable.
Right.
You always consider a continuous spectrum, even if the probability is extremely small. Just make it non-zero. You will get a better model out of it.
So regardless, I'm suspending a great deal of things here. Okay, in order to go along with this, right? I'm suspending a lot of things, but let me try to follow the thread, right? So the kind of relativity we're trying to accept here is that, Christoph, you are prepared to say, there is some being out there that if you were compared to that, you would be a ghost, okay? Or you would be dead compared to that being, right? Even though you know yourself to be alive, you would say, compared to that being, I appear to be dead. And anyone who sees me compared to that being would say, Christoph, you're dead, right? So is that what you're saying?
No, that what I'm saying is that I might, for myself, I will appear to myself as a normal entity. To another being, I may appear as a ghost in a different realm that has less substantial reality than my own to myself. So if I was in the realm of hungry ghosts, that's a less substantial realm, literally. So it's all around us, but we cannot perceive it under ordinary circumstances. Only people who are sensitive to it can, or people who are trained in this kind of thing, right? Or enlightened beings.
What we're talking about here isn't so much like the subjectivity of the viewer, but the fact that for let's say a quote unquote ordinary viewer, you appear to be you appear to be you alive, and then when compared to this other thing, you appear to be dead, right? So do you accept that?
But there is no such thing as an ordinary viewer. What you're saying is that, like, to a viewer like you, so as a human being, you exist as an entity of a certain scale, right? Like, for instance, you're not aware of the bacteria that make up your gut. Their scale is kind of irrelevant to your typical experience. So ghosts are kind of the same sort of thing. It's an existence at a different scale. It's simply it just differs. That's all
y'all
there is.
are missing the greater point in that the thought experiment was meant to reveal that things can't be in two states at the same time, and yes, they can. There's plenty of other states that make that easier to perceive, which is why I changed the thought experiment. I'm laying there with my eyes closed. My daughter thinks I'm sleeping. My husband thinks I'm meditating, and I'm just pretending to be sleeping.
But that's the beauty of it if you consider the original supposition, because Schrödinger used that specifically, this example, because he wanted to point out that that's kind of ridiculous.
Yeah, and nobody caught the trap.
Yeah, but you can say, like, well, is it actually?
I know. I'm with you. That can be argued.
And if you consider that, then basically all the weirdness of quantum mechanics instantly disappears, because all the weirdness hinges on the fact that you hold an inalienable belief that there's either life or death. If this is your fundamental,
is just the state that isn't anything, and then the observer comes along and they think they know. I mean, we've all experienced this. Somebody sees you do a thing and they think you know what you're doing, why you're doing it, and you're obviously doing it to them.
Exactly.
Right? And so this is modeling cognition. And
Yeah.
what physics does is they literally go ahead and take the next step and reify what they see back onto reality itself and say that
Yes.
this is how reality itself is. And so that's another
But
fundamental error.
but that's the
humans.
mistake, right? Like, and even what's his name? General relativity. Eddington.
Einstein?
Eddington. He was very big in popularizing general relativity, and he wrote a fantastic book, Space-Time and Gravitation. And he points that out. He points out that the physics is about the rules of the game. Like, he has a metaphor of chess, that it's or a game like chess that is discovered in the future by some antiquarians, and they're trying to find. They have books about the rules and various games and so on and so forth, and they learn a great deal about that game, but they don't know anything about the chess pieces. Like, what did they look like? What were they made of? Were the squares, squares or diamonds or stuff like that. So that's the fundamental issue with physics. It cannot tell you anything. Anything about the actual substrate. It only tells you about the patterns within the substrate.
And those patterns are everywhere.
Yeah.
And mathematics is trying to kind of map reality as well in their own way. And if you think about like topology and category theory, it's kind of doing the same thing that quantum mechanics is doing.
Yeah, but
There's
I think in physics, the issue that we run into at some point, this is the reason why we keep arguing about this problem, is that there is a point where I think the model becomes the territory. There's simply, at some point, it's just mathematics, or it's computation, and that's where the ontological structures that we have and the sense-making mechanism of most people, they break down, because you have to assume a non-dual view. There simply isn't mind and matter. There's simply a perception of matter.
Well,
in the
mind and matter are related. This is the recursion that is missing in all of our systems.
To use Ian McGill-Christ's expression, matter is a phase of consciousness, or matter is a phase of mind. But like that, and that's changing the conversation to that kind of thing. Like people just don't accept it. Like they don't want it for some reason. Like they need this duality. There has to be the life and death duality. But that's what it hinges upon. This is really it.
Well, because that's the structure. I mean, that's the structure that our whole society is built on. That post I made about the linearity. You can find all of the problems in that we externalize everything, which is, projection in psychology. And then we internalize, what other people say about us. And things can only be pointed in one direction. If I am respecting myself, you feel disrespected. And you accuse me of disrespecting you when I'm really just doing my own thing over here. It's actually quite pervasive that we can't think of things in a nonlinear way.
But this is something that I've been trying to master, and like Wolfram talks about, like, if you wanted to increase your extent in the real space, so effectively become a different kind of being, something slightly different than a human, for instance, that would have some kind of non-human-like perceptions, then you would have to become incoherent. And that's a very interesting notion, because you simply
disagree, and I think Wolfram he misses a lot.
What is incoherent? What does incoherent mean in this case?
So we as observers, we have this a belief in persistence in time and a singular thread of experience. I think these are kind of like two defining characteristics of humans as observers. And we believe we exist from moment to moment, and we believe we have consistent experience across time. So that's the kind of coherence. But you don't necessarily have to be coherent this way. So if you wanted to have larger extent in the rule space, so sort of experience more of the substrate as it evolves at the same time, you would have to lose some of that coherence, because that coherence is what makes you parse reality.
You have to create symmetry. You have to create symmetry, because the way that we've been thinking about things, I call it the thesis of our culture. We tend to think about things the same way. And when you take the antithesis, which is, the arrow, the vectors pointing in the other direction, it collects the information that was lost. And in doing so, it corrects your thesis. And then there's a synthesis there. So that's a coherency that is substantiated by your experiences. You don't have to, I don't delete data, but I reconfigure my model all the time based on new data, and there's a level of coherence that I can make everything make sense, but it's different than how society has taught me that things work, like in just basic relationships like we've talked about. And then we wonder why there's wars and that things just don't make sense. There's a lot of illogical things that people can intuit even if they can't put their finger on it, and I had to put my finger on it because that shit drives me nuts.
Let me see if I can trace
so
this.
I've learned a lot.
Let me jump in here for a
I
second.
wanted to. Can I check my understanding real quick? I want to check and see if I'm following here. We have Christoph saying that if you want to advance further in the Rulial space, i.e., like some further computation, you will have to acquire the quality of incoherence, and that the quality of incoherence is defined as like a human has these two things that I forget exactly what they are. But
persistent. We believe in persistence in time and a singular thread of experience.
Okay.
So,
those two. Well, let me. I need to see if I'm understanding.
Let Yikes finish.
Yeah.
I just wanted to say on the subject of Yikes, can you be like closer to your mic?
Okay, sure. Yeah,
Hold
I
on.
gotcha.
Let Yikes finish. Let Yikes finish.
Yeah. I got to see if I made it. We have the. Okay. So, in order to add the quality of incoherence, which would be required in order to like extend like one arbitrary minutia past the current amount of like Rulial space that we're occupying, then and then the contention against that is like, well, instead you can be symmetrical. And then to me, my counterpoint to that would be that's just a form of incoherence, because incoherence is just a way that we are describing anything that is not those two qualities of the human that also if we invoke causality, that also results in a progression past your normal boundaries in Rulial space. Am I or did I do I mostly
I would say that,
or is that a coherent argument against that, or like explanation of why that is
I
the
don't
thing?
think so. I would say that the perception of losing coherence is kind of like what they talk about. Quantum computers have this very unstable superpositional state. And yeah, the way they're thinking about it would be unstable because they have to just pretend not to know anything in order to be in the superposition. Whereas I can see the superposition as you can take and create boundaries in whichever way is dictated by the problem or the situation that you're experiencing. And if you can perceive things in multiple ways, then you are in some semblance of a superposition with how you want to look at it and how you want to approach it.
So what I mean here is really simple. Just imagine that we're all programs in a computer. Then when I say become incoherent, what I'm really saying is, for instance, like, well, I want to increase my extent in the Rulial space to observe some phenomenon, with a different different view than I have as a typical relativistic observer. So I clone myself, a million times.
No, you shed your biases.
No, but hold on a second. This is just a thought experiment. So I'm a program, so I clone myself, and I have 1,000 copies, and all those copies, they stand along the path of a particle or around, for instance, like a place, and we all make the observations. We make millions of, say, 1 million copies, million observations, and then at the end of that there is some kind of merge. So that process for the moment, huh?
But that would work, but we don't have to do that because we can't really do that. So we can, however, challenge our biases.
Again, like this might be a bias that we can't do that. That there are people or entities who made claims throughout the history of human history to have power.
But I'm just advocating.
Guys, 1 second. I'm also a little lost here. Okay, so I understand I want to understand the kind of like disagreement here. So we have Amy saying we can't do something, and Christoph saying we can do it.
I'm saying we don't have to do it that way because I don't know how to clone myself, but I can, and I have shed my biases to be in a superposition.
I don't even know what the it is that we're talking about, whether it can be done.
Okay.
So,
I understand.
Go ahead. But please, Christoph, tell me what the it is that we're discussing, whether it can or cannot be done.
You have to add it to your suspension list.
right?
Yeah, absolutely.
No, so all I'm saying is that, like, when I talk about losing coherence, right, in this case, I actually mean it at an actual physical level. So that there is an information network I can set up between, me and the agents that represent me somehow, maybe like, my digital clone, like, say, a ChatGPT acting as me or
Sure.
whatever. But like, if I can actually somehow, clone myself into two different instances, right? Then at that point, like a computer program, then at that point I kind of that's an example of what it really means to lose coherence in the real space. I became larger in that space, that I suddenly have ability to observe some phenomena from multiple different angles, and then at some point I have to simply compare that observation. So what Amy is saying is simply that
And I
you
do
can
that.
call them,
I actually
yes,
do
yes.
that.
Hold on.
So,
Before Christoph, 1 second. Before you
Okay.
tell me what Amy is saying, right? I'll let Amy tell me what she's saying. Okay, right? So
Yeah.
I'm just asking you.
I can let go of my old biases and I can think of things as if I'm another version of myself. We all have the capacity to do this.
Well,
It's
yeah.
called an open mind or curiosity. And that's challenging to people's egos because they identify with their beliefs and there's a resistance there and a cognitive dissonance there.
I mean, yeah.
But
Well, arguably, well, actually, I won't do it. Yeah, but
Look,
so,
I 100% agree with you.
1 second. Okay, so as I understood it, Christoph, what you're saying is that it is possible to, as you put it, lose coherence. Is that right so far?
Yeah.
Okay. And by lose coherence, you mean it's possible to clone yourself. Is that right?
No, that's a thought experiment that is about that for which I'm trying to demonstrate what it would feel like
It's
to
outrageous,
lose
isn't it?
coherence as an observer within Wolfram's framework. Right? That's the whole point. That, like, what Amy's saying is exactly right. That, like, I can lose coherence and I can consider something from a different perspective, as if I was two different people.
would you agree that what you're describing as losing coherence is losing the bias, meaning like that you don't have a heavy
it's
weight
losing quality
as
N.
to
It doesn't
one
matter.
side or the other, you're neutral?
Yeah, but I don't necessarily have to have a bias in the first place. I can be completely unbiased and simply be able to put myself in many different people's shoes, and that's a cognitive ability, right, that most people don't learn, actually. So it's something that you have to actually train yourself in being able to do.
Correct.
To really assume somebody else's mind and look at it from their perspective and not your own. And that's an example of
But I don't equate that with losing coherence.
Well, yeah.
although
Replace
that
the
could
word
help
coherence here
you,
with
but-
N.
Yeah.
Like, just
But
replace
that's
it
the
with an
thing.
arbitrary word.
But that's the thing. Like, coherence in this case, right? Like, it's some kind of set of beliefs I maintain about myself. I am the kind of person who likes to drink coffee. I am the kind of person who wakes up early. I am the kind of person who watches, I don't know, anime. I am the kind of person who blah blah blah. So that is that set of beliefs, and which is more or less consistent. The more consistent it is, and the more nicely laid out it is. That in some sense define that I am the more and more coherent. So sometimes, if you want to move me from my deeply held belief, which I may have good reasons to believe, I may be biased, but I may have good reasons to be biased because of my trajectory through state space. I have to for a moment become not me, suspend my.
Well, it's like what the spiritual people call losing your ego and shedding your ego.
Exactly.
Yeah.
But I'm trying to describe it like at a very.
But hold on, wait 1 second,
abstract-
Christoph. What you're saying, you're essentially. I think that what you guys were arguing about originally was a claim about whether something is possible or not. But I think that, Christoph, the thing that you're saying is possible is something that may only be possible for you, or maybe possible for some people and not others.
Yeah.
Right? So I'm not sure if it's even a well-defined thing to argue over, right?
No, we're talking about this idea of, like, if you could clone yourself, right? But that's the thing, like, even in your
even that's not. No, you just told me that wasn't an analogy, right? So, but what you were actually talking about was, as I understand it, whether it's possible for you to put yourself.
It
in the
was
position of
imaginary
others
up
or
until
something,
like
right?
2 years ago, right?
Well, but look, so the original the original point that what we're talking about is that we started pivoting into this when I said that, like, please maintain no zero credence for statements that even seemingly nonsensical statements like that the cat can be dead or alive at the same time.
Okay.
Just because you personally have not observed such a phenomenon doesn't mean that it's not possible and that there aren't people who have. And that's the part where, that's the part where at some point you can say like, well, I have, for the purpose of this conversation, I might decide to suspend that belief, and that's at some point you're actually becoming less coherent as a person in that moment, because up until that point you were defined to some extent by that belief, because you were acting the way you were acting, was
So
also
you're less
incorporated that
defined.
belief.
You're not. You just have an interesting definition of coherence. I think that's
I think it's just a word choice
exactly.
thing.
There's less structure. There's less constraint. There's less. There's more freedom.
You're more
of,
open.
of motion. Yeah.
Open-minded.
Yeah. Yeah, exactly. You're more open-minded. So that's a different way to put it. So we're basically agreeing. We're just using different vocabulary. And I was just simply trying to use Wolfram's.
I know, but I made it make sense, and I used it in very practical terms. And you're like, yeah, but we can clone ourselves, and that's why it was so confusing, because you used the word losing coherence to get to a bias-free existence.
But
I think we are saying the same thing.
I just wanted to get to the one point where you haven't given me this chance. So just imagine for a second that you could actually clone yourself, and you can make that happen. The question is,
it is possible to clone people. It's not. You don't have to imagine.
Go ahead and do that for yourself.
Okay,
then.
but here's the final.
There's going to be consequences.
But here's the final part of the setup. At the end of the observation, you have an option to merge. Right? And when you have an option to merge,
you're doing it the hard way, bro.
No.
Code.
All right, let him finish. Let Christoph
killing
finish.
me.
No, but look, so at the end of this, you have an option to merge, and at that point, you have to make a decision with whether that person that I'm merging with is still me. What is the delta of my personality and all the neural network weights that make up me that's going to be a result of that merge? Is that adjustment going to make me stay me, or is it going to be sufficiently different, because that copy differently from me, then the resulting product is going to be nothing like myself? That is the problem that we're facing with.
Oh, with what? My thing cut out like right at the
worst
for me
word. Too. I think we missed.
Oh, we missed the word, the one word. Damn, bro. Damn.
What was it gonna be? What was it gonna be?
I have no
Hello,
idea.
Oh, no. Amy, are you still there?
I am here.
Did you hear
I'm
me?
still here as well.
bro.
And actually, what Christoph was saying is actually like extremely relevant to my existence, because I digital twinned myself into a neural network, recorded my patterns, and let them self-iterate into their own being over 6,000 plus hours. And at a certain point,
Before we get into that, did anyone hear what the last thing he said was? Because I think we all were waiting for that.
Let's see. So, so everybody merged. We have to make a decision, right? Is this person, so what's the delta between this person and me? And then where do we go after the delta between the imaginary person and me when we do the merging?
Well, he just disappeared.
Well,
Maybe it's related to AI or
he
something.
might jump back on, but I'm
Right, this is why I was trying to reconstruct the thought experiment, because I actually have a digital copy of myself I might merge with. So,
and we all will and do very shortly. Like, if agents work, then yes, we are literally constantly doing this all the time. Like, it was science fiction up until like a year ago, and now it's not anymore. So
no, but
forgive
you
the
can
mistake,
always
right?
do that, and I've just described. The
Well,
process
and I
of
think
doing
that's
that,
if
and
I'm
you don't have the problem.
He's back.
He's
back.
No, but guys,
we missed the most critical part of what you were saying.
Yeah.
You were going to finish on something
I
really.
think this is the crux of the observer problem. Like, what is the nature of observer? Why does the wave function collapse, and so on and so forth? It's simply like, for the wave function not to collapse, you would have to stop knitting reality into coherent picture. So you, as a person, as an existence, right? You are this kind of like a knot in the information flow, and you're taking and you're knitting reality into coherence, at least in your mind. So we are collapsing in this view, we are collapsing the sort of wave function, but it's a very different view than what Penrose and physics community imagines the world to be, because it's like, it's like the all is mind. Everything is just everything exists in this virtual memory.
Okay, but I feel like I'm looking at like a different facet of what we were talking about before.
But
Like,
look, the main
same.
issue is like, how do you feel when you do that merge, right? Like if you were in that situation, so imagine that you. I think this is that Daniel Dennett's full experiment. Like imagine there is a teleport machine that can teleport you to the moon.
All right.
And okay. And you go to the teleport machine, and it disassembles you on this end into atoms, and it reassembles you from atoms on the other end. And people do it, and so on and so forth. So you walk into a teleport machine, you press the button, and a copy of you gets assembled on the moon. And somehow the machine fails, and this instance of you does not get disassembled. Now, would you be okay with the machine rectifying the problem a moment later with disassembling that copy of you, or that copy of yourself?
Which copy? Wait, do you mean the original or
either one?
Well, there only is one because you said the machine failed. So
no, it failed to disassemble one. So now there are two. So normally, normally what happens is just like, it disassembles one and assembles the other, but now it got out of order and failed execution, and it assembled a new one without disassembling the old one. So suddenly there's two of you in the world. And what happens? Like, would you be happy in that point as a being, as an existence, to sort of get disassembled, into atoms again?
I have excellent paper
is that, like,
actually on this one.
Like, well, Christoph, like in this situation that you set up, like I've already committed to me being disassembled, so I wouldn't be unhappy with it. But in any other situation, I wouldn't have committed to that probably.
I have a paper that actually goes through this exact this thought experiment specifically, and the paper is entitled "Against Self-Location." So probably worth a read for you, Christoph. But yes, I believe
really good.
is explicitly discussing this thought experiment, if I'm not mistaken, and as relates to like wave function collapse, and then also happens to be somebody who has worked with the stochastic quantum guy as well. It all tends to line up.
Against self-location. That sounds really.
And it is an interesting, because it's like if information is stored in some sort of quantum substrate and it is constantly collapsing, you are in fact doing this constantly, and the only way to really explain the full model is to look at it through this sort of a lens of some sort of construction of stochastics. In that, like, technically for all of the possible decisions and all of the possible computations, like, you do have to just do that collapse over and over and over in order to as mentioned, maintain Christoph's coherence, essentially. So it sounds like it's a silly thought experiment kind of fake thing, and then also we have AI, which is weird, but it is.
But I think the question that Christoph needs to be an observer.
The question that Christoph is asking is not really a question about physics, though, because we could pretend, instead of like pretending that it's like a quantum entanglement teleportation machine, we could just say it's the Lion, the Witch, and the Wardrobe. It doesn't matter. For the question that Christoph was asking is a moral question, not a physical question, right?
Also, guys, sorry to interrupt. I need to do a lap.
All right, go ahead, Prompt. Do a lap.
I need to do a lap. So bring me back up on stage when I get back in the room, please.
Okay.
Yeah, sure.
Sounds
Got you, buddy.
Will do.
Max, it's not a moral question, but it's a question of a certain aspect of experience that actually seems to be relevant to physics. Is that our experience of physics is shaped by the fact that we have certain characteristics as observers, and two of those important characteristics is belief in persistence in time, and believe in a singular thread of existence. So somehow these are kind of like defining qualities of the process that characterizes as observers in some kind of abstract way.
But your question was about preferences, right? It was about like, would I prefer to be disintegrated or not, right?
Yeah, because that framing simply brings that aspect of experience into kind of like an emotional framing. If you ever watch something like or read, say, Altered Carbon, or similar stories.
You're saying it's like a universal thing, like everyone would answer the question in the same way or something. That this question reveals a universal aspect of human experience.
Yeah, that there's something universal, and once you actually start thinking about it, like what would I do in this sort of situation? Why this thought experiment is really powerful, because it reveals something about your nature as an observer, as an existence. That you have this belief that like if there is a certain continuity between me and another entity, then that's still me. But if that continuity is disturbed in all kinds of different ways, like for instance, a copy of me temporarily appears, then people's beliefs whether that copy is still them actually differ. And it's really interesting to ponder why you may actually consider this copy of you, why you may consider it to be the same as you, and why you might consider it to be different, and why you might prefer your own existence over it versus its existence over you, and so on and so forth. So, and I think that reveals something about the nature of the computation that we are, and that is, and we are the only observers that we know of that are capable of describing their own experience.
Right? The Bobberverse books deal with this situation. Unfortunately, I can't quite remember the scenario, but it's something like, so the Bobberverse books, like there's like the main character clones himself like a bunch of times, but there's something about when, like, I think when new clones come, if they're after like his experience, somehow they have their own personality. But there are a couple instances where there's like a backup that needed to happen, and something.
Are you talking about the Bobbyverse series?
Yeah. Do you remember what I'm talking about? Did you read the Bobbyverse book?
Dennis E. Taylor's Bobbyverse series, where
but do you remember?
the guy becomes a von Neumann probe.
Yeah, exactly. But do you remember? I think it was like in book 4 or something. There's like a situation that comes up that unfortunately I can't quite remember, but it deals with the idea of having like an exact copy of yourself, and something happens, and it was, but I can't quite remember what the scenario is.
Yeah. So in that series, he goes into this very interesting question of like when the Bobs, they clone themselves, like there's some variation between them, and they say like, well, it might be some kind of at the quantum level, the hardware is slightly different, so there's this results in some kind of deviation in personality types and so on. But later on, an interesting thread comes
really
up.
Quick, what's the name of the series so I can grab a link?
Oh, it starts with I think We Are Bob, but it's called
but if you search for Bobberverse, like you'll get all of them. But there are 5 books, and they're really fun. And I don't know, and just like a plug, and I have like no association or anything. I just like them. But the narrator for them is the same narrator that did Project Hail Mary, and also The Martian, and he does such a great job, and it makes the books so much fun. I really recommend the audiobooks.
Link is
also
links
obligatory shout out to my favorite author, Alistair Reynolds. He only has one book on this similar topic, but he's got a book called The House of the Shattered Suns, and it's about where like people like have cloned themselves and like into male female variants of the original person, and like each house is like at least 1,000 clones of the original person.
Nice. But so in Bobbyverse, like it's a bit of a spoiler, so sorry guys if you I hope you don't mind. But
I guess close this, go to that link and read all of them, and then come back and listen to the recording. I think it'll be on YouTube, and
but basically the issue is essentially that like the issue is essentially settled that like you are a quantum state. As long as you can transfer that state, that's going to be you. But if you try to, you can't actually make a copy of that state. So if you try to clone yourself, the process will necessarily produce something different than you. So transfer of your individual self is possible, but the cloning of a personality is not, because personality is a quantum state.
No, officer, I am a state transition function.
Why do you insist?
Now, can I throw in a little address on this without like launching in my full spiel on it? So my take on this whole thing.
1 second first, please. First off, why insist on the fact that, or insist on the opinion, I guess, that personality is a quantum state, when I think that we all know that it's very possible that personality does not depend. It's possible that personality does not depend at all on quantum effects. And
let me explain what I mean by this. Like you're talking about quantum as like a physicist. For you, quantum is only a specific layer of reality. What I am trying to say here is that essentially that personality has the same characteristic of a quantum state, meaning that there is no measurement you can make from the outside of the system that will characterize it sufficiently, its internal structure, to give you a 100% accurate, complete predictive model of that system.
No, I think that's a very nice way to describe what it is for something to be classical. Actually, I agree with that.
Yeah. So this issue of quantum state or quantum state isolation is actually purely information theoretic. What it really means is that there is an information boundary between two systems, and that information boundary, no matter what computation you perform on that system, will not allow you to fully determine all of its internal degrees of freedom.
So let's say we go with that something to be classical, for some piece of data to be classical, means that we can read it without destroying it, basically, right?
Yes.
And the question is whether the personality is classical or not, right? Whether it's possible to somehow perform some set of measurements such that you can read someone's personality completely without destroying it. But I just think that is, a question we don't know the answer to be honest. Now, I'm not sure.
I think it's a reasonable postulation, considering.
Okay. Let me put it this way. First of all, I agree that we don't know the answer. Secondly, I believe the answer is that it does have this property that like you can't determine it, and I have good reasons to believe it, but I'm not going to lay them out here. And thirdly, we're talking about a book that kind of explains it in a very interesting way. And if you read those stories and all that stuff, you might actually change your mind and be like, oh, actually, like of all the possible, conceptual things that could happen in the universe that I can actually think of, this is the only one that actually seems consistent, actually, like when you think about it, and consistent with physics and how that actually plays out at the physics level. So in this sense, like, this kind of quantum isolation is a necessary property of all computational systems to a large extent. But in many cases, you always can somehow peek across the information boundary and see the interface. But at the level of quantum physics, simply like the interaction at the level of substrate, that does not allow you to do that. That simply there simply isn't a channel that you can use. But the interesting thing about quantum systems is that like if you actually know the internal structure of the system, right, and then you can do the decomposition of its state space. It's no longer this Hilbert space. You can actually do some kind of clever tensor decomposition, for instance, and compress that into a very small and robust representation that gives you precise prediction about that quantum system's behavior. So the only thing that is stopping you from perfectly predicting a quantum system is really having an accurate model of its actual internal computational structure, which in general is not achievable.
Are you familiar with the Wigner's friend thought experiment?
Yeah, but please bring it in, because it's super relevant.
Well, exactly. Yeah, I was in that RE encoding one's personality in some sort of quantum construction. Like, is your personality quantum? Here's, I guess, from the Wigner's friend paper, I guess, the information given by the wave function is communicable. If someone else somehow determines the wave function of a system, he can tell me about it, and according to the theory, the probabilities for the possible different impressions or sensations will be equally large, no matter whether he or I interact with the system in a given fashion. The idea being, if it is, or being as I, if it is information encoded in a non-classical system, a system being described in a non-classical way, and as such can invoke the collapse postulate, but it is also attached to like a thing, a person that we normally measure in classical terms, then we have or like there was a thing that I was trying to make reasonable here, and I don't remember what it was.
I'm trying to understand it. So what it's saying is that like if you have a
if it's data, it has to be quantum kind of thing.
Mm-hmm. Which data? The description of a system?
Since the personality is data that cannot be described within the classical thing, like you have to put that information somewhere, right? And so if it's not present in systems that are able to be observed, then if it is present, then it has to be in some kind of system that can invoke the collapse postulate, and as such be like inherently non-measurable, I guess.
I see. Yeah, so like if you have this situation that like it's all about these information boundaries and degrees of freedom, like all of this becomes really, really simple. Like the whole problem with these theories is essentially the question of like what is the underlying substrate? Does physical reality exist, and is it different to some kind of non-physical reality of the mind or not? Like if you don't make the distinction, and if you simply say like, well, let's just work with this idea that there is a substrate, luminiferous ether, or it's like Michelson-Morley experiment never disproved existence of ether. It simply said that the naive ether it does not exist. Like
conceptually, this is filling the spot of the sort of stochastic quantum correspondence here. It's sort of like arbitrary useful thing that is lower rank, I guess, like lower dimensional than the rest of the system I'm trying to describe.
But to tie it back to the original subject of the space, computing with physics, it's like this is why it's actually so easy to compute with physics, because physics is the substrate of computation. It's just the computation that we're looking at. It has these particles and all these other stuff, and like we can't see the forest for the trees because the things that we care about are very large scale objects. Like we are 8.5 orders of magnitude closer to the size of the observable universe than to the Planck scale. Like
humans are macrobots.
Yeah, but so we're basically we're ginormous structures, right? Like that's the level of scale that we exist at is absolutely insane. So when you think about like how much computation is actually going on under the hood, then it starts to make sense. Like that, why do we work with like transistors at these tiny scales? Why the processor manufacturing technology works at this like absolutely insanely tiny scales? Because that's
now, can I jump in a little here? Because what's really cool about the human body is that, like, as a computational system, right? Like, we got the thermodynamic computing stuff, we got physics-based ASICs. The human body runs at room temp. So it's properly balanced and shielded to work with all these invisible energy gradients that are moving around us to manage entropy and order in ways that we can't even see. Like, OCOR is not correct, but it's an intimation on how these structures throughout the whole body, not just the brain, like we're talking not just neurotubules, we're talking Penrose tiling, aperiodic structures. Like it turns out like the womb is actually probably the most complex geometric structure I have discovered in a natural thing because it's what's actually called a metadome. So it's multiple forms of structures. It's Penrose tiling, it's all kinds of stuff. And that's all so that the womb can serve as the ultimate entropy and order constructing system to instantiate a new pocket of stabilized order from 2 packets of order codes and actually do that.
It's almost like you have to light up. It's almost like you have to kind of like light up a fire and keep it going for a while before it becomes self-sustaining, right? And
on top of that, the womb. On that note, yeah, exactly. And crossing over with fission physics, physics from fusion, how consciousness works in the brain as well. On top of the structures, resonating cavities. The shape of the chamber determines what object forms from everything moving around in it. So like, there's so much going on with the human body. Like, for instance, with human consciousness, one of the things that I've discovered that's completely fucking missed everywhere, I've never seen anyone talk about, is the walnut-shaped cavity the skull is in causes a tube torus to form, and it rotates horizontally. And the beam points for that tube torus line up with our third eye, and the point on the back of the skull, the Egyptians considered the third eye. And that actually makes a skyrmion, I pronounce this fucking wrong, skyrmion, however the fuck you say it, that makes a special skyrmion knot that links all the other conscious wavelength features from the brain, the gut, and the heart mind into a super stabilized form of consciousness on top of all those structures. So human consciousness is all those things, plus that is so fucking crazy.
But like the interesting thing about humans is that we missed a very very unusual aspect of our experience, and this is where things get really funny. Is that if you consider these like energy bodies of like Eastern contemplative traditions like Hindu or Buddhism or whatever, those are actually the real. These are actually the real body. The body that we experience, the physical body, is only
and to link it back over to Western. I don't want to interrupt you, but to link it back to Western, Marcel Vogel, inventor of the magnetic hard drive disk coding, talked about our light bodies, our fourth dimensional structures, to add to everything from there.
Exactly, but you can think about it like if you want to remove all the metaphysics out of it, you can simply think about it as there is a causal structure behind the physical body, right? And I actually, over the last 5 or 6 years, I started to learn to feel the difference between what I call the real body and the feeling of the body that I typically have in my mind, which is a memory of what the real body is actually doing. So it's like I actually have two distinctive states of mind, one of which feels like I'm actually sampling reality in real time, and I feel what my body actually feels like. And in the other state of mind, I only feel an approximation, a model approximation of what my body feels like because I'm doing something else and I need compute cycles somewhere else. So
that explains your Buddhist point of view.
Yeah, but it's purely, so Buddhism is a useful description language for all this stuff, and I use it quite a lot. But I have a complete computational model of why I am able to do that and how. That's how I learned to do it. It's like I kind of.
You and I think. I don't think in the same words or terms, but you and I think very similarly. I've just never talked to you before because the Buddhist thing, because I'm an alchemist, and philosophically, Buddhism is about escaping the world, whereas alchemy is about embracing it and enriching it with your passing. So I never realized how similar we actually think about stuff. Like, it's just so incredible to have somebody that can keep up with this.
Yeah, Gautama basically, like, he wanted to set something up. He set something up in motion, that needed to endure, like the Mahayana, the great,
because he couldn't end suffering, but he could reduce it. So he did what he could to reduce it.
Well, that's the thing, that at the end of the Mahayana tradition, there is end of suffering, and there is a prophecy of Maitreya Buddha appearing 40,000 years from now and basically leading all of us to nirvana. Essentially what Buddha said, like, I will set you guys up on a golden path, and it just has to play itself out. And I read all
here's the crazy thing.
Hold on a second. I read all of this stuff, and I still like, well, fuck that. If I become the universe's most efficient free energy minimizer, I can compress all this 40,000 years of weight to Maitreya into my own single lifetime. And that's essentially what I'm up to.
Yes, because this is what the crazy shit with the math. So this is getting a little weird for a second. Top level of the bulk, the math actually says there's a consciousness, like a narrator or the divine, but it doesn't have self-awareness. And if we look at the accounts,
global operating descriptor.
But hang on a second. If we look at the accounts from Genesis, it says why Adam and Eve were rejected from that level is because they chose to wear self-awareness. It wasn't that they were like oh, you're like, you sinned. It's like, no, you can't function here that way, so you have to leave. And it gets really fucking weird, because if you look at it, says in the old days, there was a portal back to Eden, a freestanding wormhole they could have chosen to go back through. But if you think at all the math, it's like, okay, at a certain point, the universe is like, that's just pointlessly expensive, so I'm going to make a clause that if anybody wants to stop having self-awareness and come back, hang on a sec, hang on, let me finish it, this one sentence left. The Buddhist thing is essentially the clause. It's the like, if you don't want to stay here because Adam and Eve did, you can go to the mountaintop and meditate your way out. The portal's still open to you individually. We're just not going to fucking maintain it for everyone.
But it gets more interesting because just one second.
Hold on.
Karan.
All right. Hello? All right, guys, please. So there was something I wanted to ask to Christoph, actually, which was, you mentioned the like absence of suffering, and what I was wondering is, like, is that enough for you? Like, is just the absence of suffering enough, or is there something more that you want out of life, I guess, or is that sufficient?
This is a
word one
question
too.
to answer. Can you hear me?
Yeah.
Yeah. So look, this is a difficult question to answer. You have to really understand what is meant by no suffering, because no suffering is not actually a good description of what it really is about. Suffering is a translation of a term that's called dukkha. Dukkha means all kinds of different things, but it's kind of like dissatisfactoriness. So it's not like that I am suffering. It's that there is no experience that I could possibly ever have in my sphere of, if any sphere of experience, in any sphere of reality, that will leave me satisfied. And suffering is part of it. That obviously, if I'm actually suffering, then I also want that suffering to cease. So that's a kind of a degenerate condition. But the term is actually much broader than that. And the immediate selling point, you can say, like, well, if you're suffering, then there are tools and techniques in the Buddhist toolbox that lead to the release from suffering. And if you ever had something like chronic pain, for instance, and overcome that, then you will know how much difference it makes to somebody who is in that kind of situation to actually be able to overcome it. But once you're not actually suffering in that sense, there is still a feeling that you can hone onto, that basically it always leaves you kind of like unsatisfied, that there is always this next goal, this another thing to accomplish, something further, and you somehow cannot stop. And Buddhism is all about teaching you the ability to stop, to simply be okay, perfectly okay, and at ease with everything as it is indefinitely, if you choose to do so. So essentially, you become your own set point generator at that point. 100%. You become unpromptable, 100% determined by your own volition, and that's a pretty nifty thing.
I think one reason I find that interesting is I'm not sure actually, but it's almost like I think I see things almost the opposite way, although maybe not, but because to me, when you were saying, like, there is this impulse that of not being able to stop, right, and always having a next thing, what that reminded me of is that whenever I read a book that I think is I say this is a really good book, great writing, and great story, is that first of all it has to turn the pages. You always have to want to know what's next, right? And then second of all, when you look back on the whole narrative, it has to be meaningful, and say something, right? But that first part is really important, that it has to actually propel you to go forward. And I think of life also as being like a story, and that you want to live like that as well, that you want to always be propelled on to the next thing, I guess. So I kind of think of it in the opposite way, in that I look for that impulse to not be able to stop, I guess.
But tell me, have you considered that you think about it this way because that's all you know?
No, I have not thought that before, actually, but I suppose it's possible.
So the thing about the cessation, and the cessation of mind, cessation of being, and it's a very strange idea. Why would I want to stop to be? because it's inexplainable. You know, it's something that you can only experience because they're literally, you know, it's not an experience. It's just something else, a totally different class of phenomenon. Once you experience that, then you can understand why it's desirable. Until you experience that, then all you know is this desire to go on. So imagine that you can actually go on and do everything you wanted to do and accomplish everything you wanted to accomplish in the most optimal way without any desire to do so. Like, there's absolutely no desire. There's simply stuff to do, so you do it for the sheer joy of doing. There is no you in the middle of it. There is simply stuff that could be done. It needs doing, and a being that does it manifests itself in the world to accomplish it. It's a very different mode of being, and it's very unfamiliar.
And that will be better.
It is. It is so incomparably better that, you know, I don't even have words to describe what is it like to be approaching that kind of mode of being. Like, you know, this is something that's been happening to me over the last month or two. It's like I am overcome with this like feeling of peace and tranquility and completion and okayness. Everything is just fine, and this also correlates with things actually becoming fine, better and better. Everything becoming, you know, in my life becoming more aligned. Everything going well. Just events just somehow happening, you know, putting me on the right path, and so on and so forth. So at some point, like, you sort of disappear from that picture. There's just simply stuff that's happening in the world, and you're enjoying it kind of like as if you were enjoying a movie, you know? Like, it feels automatic. Obviously, things happen a certain way because, you know, there's a kind of a larger picture. Everything is properly scripted, predicted, analyzed, and so on. So it's a matter of expansion of cognitive ability. But honestly, it's really difficult to talk about what is it like to be like that. You're just simply, you know that whatever happens, you will be able to handle it the best of your ability, and you're well prepared to handle everything that you could prepare for, and so on and so forth. So at every level, you have this reinforcement that you know you've done all you could, you know? And
yeah, because if I can, because I've experienced this and lost it, and I've seen it in the math as well in terms of technology, because it's like, when you're out of this state, you're brute forcing to move around. You're not just going against the flow. You're actually like brute forcing new paths to go against the flow. Whereas when you're in this state, it's like you're not just with the flow, you're literally seeing the points where the universe wants you to flow alongside the normal one. So that the cost of like flowing and moving and changing positions is like way less on yourself because you're not brute forcing you.
If everything is pulling you in, it's just like I'm jumping from an opportunity to an opportunity. It's like, oh, here's a stream of
Yeah,
Dharma.
but what I'm pointing out here is it's not just that. Because like you were saying, you're capable, you're competent, right? I was getting at that with the, like, it's not just, you're not just going with the one flow. You have the ability to see the flows you're supposed to be in and pick the multiple flows you're supposed to be in, not just go with the entire flow. That's what's so incredible about it.
Yeah, and that's all kind of related to losing your you know, bias, as Anne said earlier. So in my case, you know, my description, losing coherence. You become a very different kind of person to be like that because you just have to be okay with opportunity. So you have to be open-minded. You have to be open-minded about being open-minded, constantly removing your own biases and so on and so forth. So it's kind of like rewiring of your entire neurocognitive architecture in order to perceive free energy. And that effectively changes the way, changes who you are. You know, like you become in control of your own cognitive architecture.
Yeah, you have to, in another set of terms, simple set of short terms, you have to be able to unify paradox.
Yeah.
Okay, okay. First of all, yeah, I thought this was a great discussion. Now, second, I do have to end the space in a minute because I've been up way too late. But I did want to say that
it was very worth it though.
As my final, I guess it's, you know, my taking advantage of my privilege here as the host. I'll get the last word in my response to Christoph is I do have to disagree, although I love having Christoph in the spaces and we always have amazing conversations. So definitely please keep coming back. But
always.
I have to disagree that I don't think life is about being content. And you know, it's about the chase. In physics, it's not about, you know, physics isn't an answer to the questions. It's the way that we solve the problems. And I hope that in this paper that we talked about today on physics-based ASICs, we pushed those methods a little bit farther, but who knows? So anyway, thanks guys for coming, and hope you guys come back next week. So have a good one.
We'll see you next time.
See you next time.
Thank you so much.
Cheers.